One, two. One, two, one, two, one, two, one, two. Hey, 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 hey.
You've been a little different lately. Hope my feelings didn't push you away. Starting to feel a little bit crazy. Starting to get just a little afraid that I went too far and you're not on the same page. That I showed my cards and now you're trying to walk away. I'm doing all that I can to show you who I am. Am I just a friend? Cause this love is feeling one-sided. Whoa, one-sided. Oh, whoa, one-sided. Oh, one-sided. Oh, whoa, one-sided. Don't hold back, just be honest with me, cause I don't wanna waste any more time. It's the least that you could give me. Just look me in the eyes and tell me it straight that I went too far and you're not on the same page. That I showed my cards and now you're trying to walk away. I'm doing all that I can to show you who I am. Am I just a friend? Cause this love is feeling one-sided. Whoa, one-sided. Oh, whoa, one-sided. I'm doing all that I can to show you who I am. Am I just a friend? Cause this love is feeling one-sided. I'm doing all that I can to show you who I am. Am I just a friend? Cause this love is feeling one-sided. 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 Oh, one-sided. Oh, one-sided. One-sided. One-sided, 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 one-sided. Call me up when you're sober, when you've showered and changed. You give it up like it's over, but never give it away. And I don't wanna fall for you this time. I can't find the truth in all the lies. If I could, I would, believe me. If I could, I would need you. I don't wanna fall for you this time. Call me up when you're sober, when you've showered and changed. You give it up like it's over, but never give it away. And I don't wanna fall for you this time. I can't find the truth in all the lies. If I could, I would, believe me. If I could,
Blue.
Yes. Okay. So where do we want that audio?
We want that to go out to stream and in the room.
And then okay. Can you put that audio that you're getting now, please, in the room?
Yeah. Just playing again.
That's you. Your microphone.
That's my microphone. Yeah, that's boring.
So when I'm able to do it on the scan converter, I could
Kill that. Before that happened.
Hey there, good morning.
Hello, Rudolph.
Hey, hello.
How are you?
Good, how are you?
I'm very good. We got your audio and video in through, so all looks good. Are you a chair or a presenter?
Chair,
Okay,
the virtual
perfect.
chair. Like on, there
Okay.
should be also Rudolph on site, like Rudolph with PH, Triebel.
Um, I have some gentleman here. I'm not sure if he's Rudolph. Are you Rudolph as well? No, I got Davide here.
Oh, Davide is the speaker, right? So,
Yes, got him here.
Hi.
hey Davide,
Hey.
how you doing?
Good. How are you doing?
Good, good, good. I got mixed up with the time zone, so I was ready to go at 7 a.m. And I was like, oh, it's
wow.
the other way around. So,
All right. So we're gonna keep doing some a couple of tests here.
sure.
I'll let you know when the other Rudolph joins.
Okay. I have a quick organizational question, if you don't mind.
Trying to forget me when I can't forget you. How can I, when every single truth and lie keep coming back to haunt me, yet make me want you to? Is it hard to let me go? If the truth hurts, to live on alone. It is sometimes better to be honest. Make me try to hold. Please free or let me go. Please let me or let me go. Please free or let me go. What if I was misinterpreting the signs, putting all the fault on you when it wasn't true? Now I try to live out every other night, thinking of the times that I started falling through. How could I have ever been so out of mind? I am part to blame and all this too, tearing you away from the part of me and you. Was it hard to love me or let me go? 'Cause the truth hurts, I get to live on alone. It is sometimes better to be honest, so I can try to go. Please let me or let me 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 go. I just wish that we were honest. Didn't play it wrong. Please let me or let me go. Please let me or let me go.
dinner yesterday. Actually, I enjoyed it a lot to see so many people again and talk to many interesting people. So it's really a long time that I didn't do that. Yeah, so really, that was good. My name is Rudolf Triebel. I'm the chair of this session, and I'm chairing this together with another Rudolf Jutikov from UT Austin. I think he's there. I can't see him, but I think, there he is. We have a keynote speaker today, and it's my personal pleasure to actually introduce David Scaramuzza, not only because he's, of course, a brilliant speaker, but is also a good friend of mine. We know each other for quite some time already. We started together at ETH Zurich in the group of Ron Siegwart. Since then, he has moved to the University of Zurich. He's now a professor there, and he did all kind of really exciting work in the area of agile navigation for microdrones. He has received a number of awards. He received the ERC Consolidator Grant, and a Google Research Award. He was also had received an early career award of the IEEE RAS Society. His team also developed the visual inertial odometry method that is now implemented in the Oculus Quest VR system. He's the co-founder of Zurich Eye, which is now Facebook Zurich. And he has also authored a lot of papers. I just looked it up yesterday. He has a Google Scholar Age Index of 78, which I think is impressive. So yeah, I'm really happy to have you, and let's welcome you on the stage.
Thanks a lot, Rudy. It's really for me a pleasure and an honor to be here with you today. We worked with Rudy like 10 years ago on self-driving cars, and that was actually a very exciting time. Then in 2009, I decided to switch actually to drones, and that's how the whole journey began. So I think we can start with the presentation. Is it gonna go full screen, or how does it work? Huh? Oh, okay. Okay. Sorry, I arrived yesterday, late afternoon. Okay, so today I am going to talk about agile autonomy, learning to fly in the wild. And basically I want to tell you the journey that we have been doing over the past few years. And the work that you will see today is done by my amazing students at the Robotics and Perception Group at the University of Zurich. One of them is actually here with us today, Yulong. So what do we do in my lab, if you don't know anything about my lab? So we work, thank you, much better. We work basically on vision-based navigation running fully on board, and we demonstrated on autonomous flying machines. Typically, the main sensor we use is standard cameras, but also we work on event cameras because, as you will see towards the end of this talk, they have a very low latency and very high, very low power consumption. So what we try to do in my lab is to push the limits of what is feasible with vision-based navigation. And we are interested in drones because drones are among the most agile machines. So they allow us to work on research problems that are really, really difficult. When did we start working on vision-based navigation? Actually, we started 12 years ago during the European project S-Fly in 2009. And what you see in that video was what we believe was the first demonstration of visual SLAM-based navigation of an autonomous quadcopter. And the person you see there is Laurent Kneip, now professor at the University of Shanghai. And actually, all the other people you see in that video all became professors, which is very nice. What we demonstrated here in this video was basically the first vision-based flight. So we have a quadrotor taking off from the floor, and then it's supposed to reach a point which is inside the house, all using only a single onboard camera. At that time, though, we didn't have enough computing power to do all the computation on board, so actually we used a 20-meter-long USB cable to actually stream the images down to a remote laptop, which is sitting on the floor. So this project was actually also very successful, not only because we were able to navigate drones for the first time in GPS denied environments using only onboard cameras, but also because two big results came out of this project. First of all, the PX4 autopilot, which is now used in over 1 million commercial drones worldwide, developed by Lorenz Mayer, Mark Polyface Group, and also the Intel drones. So after this project, Intel bought a company which was a partner of our project, and they actually are the ones behind all the acrobatic maneuvers of the Olympic Games done by Intel today. Inspired by this project, in 2015, the next video. Okay. Inspired by the F-Fly project in 2015, DARPA launched a program called the FLA, that stands for Fast Lightweight Autonomy Program, that focused exactly on navigation of drones in GPS-denied environments using only onboard cameras. Here you see the final demonstration, where our drone takes off in the wild, navigates among obstacles, trees, then it tries to find an entry place in order to find a target that was instructed to search before the mission started. And here I was also lucky to participate in the team led by Vijay Kumar at the University of Pennsylvania. So there seems to be a problem with the clicker. Can someone click? Okay. And where do we stand today? Today we are in 2021, and we can say that vision-based navigation is mature enough to be found also on other planets. And what you see here, of course, is the first flight of Ingenuity. But nowadays, vision-based navigation is also available in many products, like the DJI drones, the NASA, and also the Skydio drones. Which begs the question, so you tell me where I should stand for the clicker. I think the clicker is not working. Okay, which begs the question then, what's next for research in robotics? So I think what's next is basically building machines that can outperform humans, and not about only flying robots, but about any robot in general. So what we are working on in my lab is to understand how we can one day fly drones as good or even better than human pilots. In fact, if you look at the performance of autonomous drones compared to human pilot performance, autonomous drones are still much behind the human pilot performance in terms of speed, versatility, and robustness. And look at this video, where a human pilot is navigating this drone in an unknown course. They can actually cope with the motion blur, the huge delay that are involved, like 220 milliseconds, and they're able to navigate very, very agile. These maneuvers are still inaccessible to standard flying machines. But of course, you may ask, why bother about navigating agilely? And the reason why we bother is because if you think about the battery life of drones, it lasts only for 20, 30 minutes. So if you can navigate faster, you can actually cover longer distances. Of course, when you can navigate faster, you also consume more power, but there exists a sweet spot, an optimal speed, that actually still makes it convenient to actually navigate faster. And navigating fast, of course, is essential, crucial for many applications that range from search and rescue to delivery and exploration. But another reason why we should bother is because trying to perform as good as humans, or even outperforming humans, is actually a very difficult research challenge. It's like a moonshot. And I believe it raises a lot of fundamental challenges for robotics research, in terms of perception, planning, learning, and control. And so what we are doing at my lab is that we are trying to push the limits on what is possible to achieve with vision-based onboard navigation. There has been related works on agile flight, and an exercise that we did is that we tried to map some of the dominant works on two axes. The horizontal axis denotes speed and agility, And on the vertical axis, we have works that use prior knowledge about the environment, like prior maps, or external sensors, like GPS or motion capture systems. So pioneering work was done by Peter Abil back in 2006, where he used reinforcement learning, but external sensors like GPS and off-board cameras to stabilize a helicopter. Then there was also work by Adam Bry, the founder of Scadio, together with Nick Roy, on navigating fixed wings in a garage using onboard lidars and prior maps. And then also other works done by Vijay Kumar, Nathan Michael, Daniel Mellinger, Lou Pashin, and Raffaello D'Andrea. But so what distinguishes these works is that they were super agile, but they were using either prior maps or external sensors. On the other side of the spectrum, we actually have works that use onboard sensors. But as you can see, they're actually less agile. Now, when you look at the performance of human pilots, they don't rely on external sensors, neither on prior knowledge, but they're super, super agile. So that's where we want to be, or ideally, we actually want to beat even human pilots. So that's where we want to get. And we want to do that relying only on onboard perception and computation. So what you see here is our most recent drone. It's built from off-the-shelf components. It weighs less than 1 kilogram. It has can generate a maximum thrust of 70 Newton, and it has a thrust-to-weight ratio of 5, that means it can experience accelerations up to 5G, which is not possible even for humans to tolerate. And then, as you can see, it has an NVIDIA Jetson TX2 for neural network inference and flight control algorithms. And then we use one or more cameras depending on the tasks that we want to solve. Typically, we use interior sensors because they are very robust, and so far they've been maintained. Now, how will we know that one day we will have achieved the human level or superhuman level performance? How do we know? The only way to know is to set a very ambitious goal. And I think this should be done in research in general. You know, think of AlphaGo, Gran Turismo, and other things where actually machines beat humans. So we set for ourselves, for our lab, a very ambitious goal. How will we know we have achieved the human level performance? And so one task we chose to work on is autonomous drone racing. Because in autonomous drone racing, humans compete against each other in a lap time. So we started working on autonomous drone racing 5 years ago, and we have participated in a bunch of competitions, starting with the IROS Autonomous Drone Racing Series, and the last one we participated was just before the pandemic, which was the Alpha Pilot competition organized by Lockheed Martin and the Drone Racing League. And here you see our final performance. We used a vision-based quadcopter that was able to reach speeds up to almost less than 30 kilometers per hour using only onboard vision and computation. And we actually ranked second out of 400 participants. How does autonomous drone racing work? So now I want to use autonomous drone racing to tell you why it is difficult to navigate machines agilely. So typically, the way you solve autonomous drone racing consists of solving 2 steps. The first one is, for example, to compute a global time-optimal trajectory, which basically is a trajectory that minimizes the time from the start to the finish. We have done work on that was published at Science Robotics this year, and we have also open sourced the data and the source code if you're interested. The second step now is to actually execute this time-optimal trajectory while being robust to disturbances. And that's where the key challenges arise for robotics. Why? So the point is that this time-optimal trajectory is optimal as long as you can execute it with centimeter accuracy. As soon as you deviate from this trajectory, it is no longer optimal and will actually lead the drone to underperform. So now the questions are, what causes deviations from the optimal trajectories? Well, first of all, inaccurate models about the sensors, of the actuator, the battery drop. Another problem is unmodeled aerodynamic effects, motor-to-motor interactions, turbulences. Also drifting visual inertial odometry, especially at high speeds, there is a lot of motion blur and very few features, so you need to actually tightly couple perception and action. and also imperfect gate detections, again, because of motion blur, and also because you want to make sure that the drone always looks at the next gate. These are things that are not obvious. They're obvious for humans, but they're not obvious for robotics in general. So how do we tackle some of these problems? So one way to tackle these problems is to actually look at the synergy between perception and action that exists in quadcopters. So quadcopters are under-actuated systems, so you cannot hover in any orientation, and that's actually the key problem. Now, suppose that the drone over here uses a single camera to hover. And in order to hover, you need to reliably detect and track some features in the environment here on the floor, denoted by the yellow star. Now, say that this drone needs to reach a certain goal. Since the drone is under-actuated, it will have to orientate its thrust vector towards the goal. But by doing so, it will lose the visibility of the features that it needs to hover. So I hope with this simple toy example, you understand how complicated it actually is to control drones vision-based. This is not an issue that happens with cars or ground robots. There is no issue with that. So how do we solve this problem? We solve this problem by creating a synergy between perception and action in what we call perception-aware planning and control. And we started working on perception-aware planning and control now for about 4 years. And one framework that we are very happy with is actually the Model Predictive Control Framework, abbreviated MPC. So typically, you had also a tutorial on MPC by Byron Booth. Typically, if you want to control drones with typically what you do, you have to plan and control. So the nice thing about MPC is that they bridge the gap between perception, between planning and control. Now, typically though, when you do MPC with drones, you tend to satisfy mostly action objectives, like for example, satisfy the under-actuated system dynamics, minimize the trajectory tracking error, and maybe also minimize the actuator saturation. Now, what we do for our drones to make them perception aware is that we add some perception objectives. For example, we want to make sure that the point of interest is always visible at all times. And we also want to make sure that we minimize its motion blur. So typically what we do is that we design a perception state, we add it a quadratic cost, and then we add it to our cost function that we minimize. We are able to solve this minimization at 100 Hz on board. This is thanks to very efficient solvers like Akados or Kasadi that actually use a real-time iteration. So this algorithm can run on board at 100 Hz. Now, I explained you how to generate global trajectories, how to do perception-aware planning and control. What about detecting gates, for example? So if you use a handcrafted gate detector, we already know it doesn't work. So we have been using now more and more neural networks to do that. But instead of instructing a neural network to detect gates, what we are asking the network to do is directly to predict the relative pose of the next gate together with its covariance with respect to the frame of the drone. And we do this actually end-to-end. And since you need tons of data, we are doing this in simulation, because simulation is fast, it's cheap, and especially it's very, very safe. Now let's put all these pieces together. What do we get? Let me show you the final result of this, so also what is happening in background. So what you see over there is the track that we want our autonomous drone to navigate through as fast as it can. In purple, you see the covariance ellipsoid generated by the network. In red, you see the prior map, and in green, you see the updated map. So yes, we also have a common filter that actually builds a global map of the gates, and they get adjusted as soon as the network detects the next gate. As you can see, my students are also moving the gates, and you can see that the drone can adapt to changes in the environment, which is actually also what we want to do. But as you can see, the performance that we reached is not really human-level performance. We were navigating here up to 8 meters per second, while humans can navigate, at least 6 times more, or even 7 times faster. So what does it get to get there? So actually, I think that the real problem lies in the architecture of perception, planning, and control. What you see here is what all autonomous commercial robots, from ground to drones, still use nowadays. we have a perception and state estimation as a module. Then the output of this goes into the planning module, and the output of this goes to the control module. What is the problem with this architecture? That is very successful. Scadio drones, the Ingenuity drone are all using this architecture. Well, first of all these building blocks are designed independently rather than co-designed. Another problem is that it's very sensitive to inaccurate models of the sensors, of the actuators, of the environment, battery voltage, aerodynamic effects. It's also very sensitive to imperfect perception. It ignores, the way it is written here, the perception induction coupling that I just told you about. And also it suffers from high latency due to this sequential structure. So what we started to work on over the past years is try to think on whether we can actually directly map perception measurements into control commands by a single neural network or by a network of subnetworks, so by keeping modularity. So this is actually what we have been working on and what the story I want to tell you now about for the remaining time. Now, how do we train such a network though? So one framework that we are very happy about is actually to use privileged imitation learning, where the idea is that we have an artificial expert because we don't want to use a human as an expert. We don't want to emulate human. We want to be better than humans. So we have an artificial expert that has access to privileged information about the environment. So it knows perfectly the robot state and the environment state. And then we distill this knowledge into a neural network. But now the key questions are, how do we get enough training data? Which begs the question, can we actually learn in simulation? What would be the artificial expert? And what sensor and control abstractions would actually reduce the simulation to reality gap if you use simulation? So to answer these questions, I'm going to talk about 3 different tasks, because it's difficult to talk very abstractly without focusing on something. So the 3 tasks I'm going to focus on now are drone acrobatics, navigation in the wild, autonomous drone racing. Yes, we're going to go back to drone racing. So let me start with drone acrobatics first. What you see in this video was published at RSS last year, and it shows a quadcopter that is doing autonomous acrobatic maneuvers, relying only on onboard perception and computation. And the beauty about this work is that we use a neural network controller that was trained entirely in simulation. Here you see the simulator that we used. We actually, at that time, we used Gazebo, which was a non-photorealistic simulator. We were able to simulate 50 hours of actual flights in just 4 hours, and then we deployed it to the real drone without fine-tuning. Now, the biggest problem when you train only in simulation, though, is that there is a simulation to reality gap. Look at the simulated images and look at the real images. They're very different. So how do you make it work? Well, the key idea is actually not to train directly on raw pixel informations, but rather on appropriate sensory abstractions. We found, actually for us, for this task, the appropriate sensory abstraction was actually to convert images into feature tracks. So optical flow vectors, KLT features. And we showed that actually by doing so, you minimize also, you reduce the faster time distance between the models in simulation and in the real world. This is not a new discovery. Already other papers like, for example, the paper by Vladlen and Colton and other papers already found that if you use intermediate representations, networks can train faster, achieve a higher task performance, and generalize better to previously unseen environments. So for our task, we used feature tracks as the key sensory abstraction. Now, how did we train it? Who was our artificial expert? For the task of drone acrobatics, our artificial expert was a nonlinear model predictive controller that has access to the robot state and the environment. And then to actually deal with the asynchronous nature of the data coming into the neural network, we use the temporal convolutional neural network. To To validate our approach, we actually performed many experiments that you find in the paper. We flew different acrobatic maneuvers. They all look similar, but actually they are loops with different diameters and different also rotations. Like sometimes also the drone was going backward, which is actually super difficult for humans, but for a machine doesn't make much of a difference. And then what did we find out? So we compared our learned neural network controller against a traditional drone control architecture relying on standard visual inertial odometry plus MPC. And the main finding was that the learned end-to-end control policy outperformed by up to 25% the traditional baseline, both in trajectory tracking error and also in success rate. We'll come back to these results later. Another thing that I want to report about is navigation in the wild. What you see here is an autonomous quadrotor that navigates in the wild, meaning in forest environments, ruins, in snowy terrains, and so on, relying again only on onboard computation and onboard cameras. And it even outperforms commercial drones like Scadio here that bumps into obstacles. And for the first time, we were able to fly much faster than state-of-the-art methods, up to 40 kilometers per hour, which is at least 3 or 5 times faster than state-of-the-art traditional baselines. Again, the algorithm running behind is actually a neural network. And this neural network was again trained in simulation, but now is in a completely different environment because the task is no longer acrobatic maneuvers where there are no obstacles, but now you want to navigate among obstacles. So we use the Flightmare simulator developed by my student Yu Long Song, who is there. That relies on a real engine, which is basically like a video game simulator. There we imported 3D models, and then we flew the drone in simulation. In order to make it robust when we would transfer to the real world, we actually trained on noisy depth maps. And we show again that by using depth maps, you reduce the sim-to-real gap. Because in fact, if you would actually train directly on raw pixel information, it would be very difficult then to transfer to the real world, just because you would need much more actually data than you would need if you use depth maps. Now, the depth maps were generated from left and right stereo pairs, and then we did blob matching using SGM. Why doing that? Why not actually simulating depth maps? Well, if you simulate depth maps, you will not be able to simulate occlusion artifacts, which are typical of stereo vision systems. So that's the only way to get occlusion artifacts. What about the artificial expert? In this case, we used a Monte Carlo sampling method. We basically sampled thousands of trajectories, and out of these thousands of trajectories, we picked the best ones. We scored them. Actually, we picked the best 3. We scored them. And actually, these trajectories are the ones that the neural network tries to imitate. But actually, we don't directly map now sensory data to control commands. Rather, what we want to do in order to reduce the sim-to-real gap is now that we use a nonlinear model predictive controller then to track this trajectory. So then now the nonlinear MPC then will generate the control commands out of the output trajectories. We validated this in many simulation experiments, both in the wild as well as in office-like environments. So we randomized the number of obstacles, their density, the diameter of the obstacles, and so on. And then we compared our performance, measured in terms of success rate, against 2 state-of-the-art popular approaches. The one by Xiaozhe Shen at Hong Kong University of Science and Technology, which you see there, that actually does receding horizon planning. It's called the Raptor. Very good. It does incremental mapping, and then it tries to find the traversability paths around it, and that would be the one in orange. Then we also compared against the reactive approach, the one by the group of Rusted Drake, that instead it doesn't do incremental map building, but actually for every new local map, it decides where to steer the drone, and that would be the one in blue. As you can see, using our neural network controller, we were able to actually achieve much higher success rate. As you can see, the success rate decreases depending on the speed. So at higher speeds, of course, the success rate is actually larger because you're approaching the maximum speed that you can actually fly. which depends on the sensing range and the latency of the processing pipeline. But still, at 10 meters per second, which was actually almost 40 kilometers per hour, the success rate dropped to only 60%, while for the baselines actually went to 0%. Another thing I wanted to report is that not only was the neural network controller much more robust, but it was also much faster than the traditional baselines. As you can see, it's between twice and 6 times faster than the traditional baselines. It takes only 10.3 milliseconds on a PC and 2.6 milliseconds on the GPU. And we validated this work in many different environments, like snowy terrains, also foggy environments, and it was able to generalize. And the reason why it generalizes so well, remember, is because we don't train directly on raw pixel information, but rather on depth maps, which are a good sensory abstraction to reduce the sim-to-real gap. And now, what's next? So I've talked about these tasks, and now let's go back to autonomous drone racing. Now, what I'm going to show you, it's very ongoing work. It's unpublished, but you're going to be the first to see that. And if it's possible, it would be great to get sound for the next slide. Otherwise, it doesn't matter. But so now we have been trying to deploy these algorithms that we used for drone acrobatics and navigation in the wild for the task of autonomous drone racing. We started with privileged imitation learning, but we realized that there is a ceiling that you hit. And we want to go much farther. So we now started to work more and more on reinforcement learning, and Yulong is actually one of our reinforcement learning experts, if you have questions here. I will not give any detail here, but I'm just going to show you the video. We are working both with onboard vision, but sometimes we switch to offboard vision like Vicon in order to understand what the challenges ahead are. We are also inviting more and more human pilots from anywhere in the world. We also had one of the top 5 human pilots from the Drone Racing League coming to us and racing against our drones. The person you're going to see racing there is our Swiss champion and one of the world-class human pilots. He's only 15 years old. His name is Marvin, and he's now going to compete against the machine that was built by Yulong. So now we play the video. There should be sound.
Pilots, arm your quad. Get ready on the tone in less than 5. Beep!
So, okay, thanks a lot. So as you can see, the drones are flying very fast. To build such an infrastructure, we are renting a huge space, 30 by 30 by 8 meters, 7,000 cubic meters of flying space. We also have a 40 camera-based Vicon motion capture system to track the drones that in this space can fly up to 70 kilometers per hour. We use the Vicon both to record ground truth, so supervised learning, but also as a backup pilot in case things go wrong, and they go wrong all the time, especially when you start to do online reinforcement learning on the real drone, you will have to crash a lot. You can imagine in this confined space still, the braking distance is actually very, very large, so you won't be able to recover the drone all the time. So that's why agile robotics is super difficult. We started working on some work, and you can see it there, some of the papers that we output. Maybe you can go again full screen if you can. Thanks.
Pilot.
Let me go to the takeaway slide.
Pilots, arm your quad.
I've been talking at the beginning about traditional control architecture, and then later I moved to learning-based. So let's look at both of them side by side. What we can actually see is that the traditional control architectures are very sensitive to imperfect perception. They suffer from high latency, as I showed you. However, they generalize quickly to new scenarios and conditions, and they're also very transparent, easy to interpret. On the other side, we showed that the learning-based solutions are more robust to imperfect perception. They have much lower latency. However, we need tons of data to train them. I showed you how to train them in simulation, provided that you use the appropriate sensory abstractions and also control input abstractions. What about interpretability? How to decode uncertainty? We're also working on that. And we have a general framework to compute the total uncertainty of a neural network if you're interested in that paper. But now, we are also looking farther into the future. And who can better inspire us than nature? So what you see here is a sparrowhawk from a famous BBC documentary. It's even too fast for the projector. So in just 4 seconds, this drone takes off, slalom among trees, passes through a narrow gap, and then it makes the little bird magically disappear. So birds are extremely agile, more agile even than human pilots. But why is that? One reason why they're so agile, besides the fact that they have morphing wings, is actually the fact that both birds and humans do not rely on frame-based cameras, but on a different type of camera, which is event-driven. And now you see the reason there. Look at this plot. The problem with standard vision is that for every frame or stereo frames, you need to account for the processing latency, which is the time to process these frames. And then there is the sensing latency, which is the time you need to wait until the next frame or couple of frames arrives, which is given by the frame rate of your camera. So these two terms actually cause a very large bound on the maximum agility of the platform that you can possibly achieve. From this idea, can we actually create a low latency, low discretization perception pipeline that doesn't suffer from this limitation of standard cameras? And the idea is to actually use non-conventional sensors that have much lower latencies than standard cameras, maybe even asynchronous, and these are event cameras. What is an event camera? An event camera is a camera that measures only motion in the scene. And you see an idea there. I'm moving my hand, and you can see that the camera triggers information only in correspondence of edges, because edges are the ones that typically correspond to motion in the scene. The color denotes the direction of motion. Now, this camera is not just a motion-activated sensor. It's much more than that, in fact. The generation of these events is not synchronous, like in a standard camera, but it's rather asynchronous. Look at this animation. Okay, thank you. So here, the stimulus is a rotating disk. On top, you see the output of a standard camera, and at the bottom, you see the output of an event camera. And what you can see is that the stream of information is continuous in time. It doesn't break at regular intervals. It's always continuous, and it's only dictated by when pixel detected motion. So these pixels of an event camera are actually smart pixels. Each one has a microprocessor behind. Whenever a single pixel detects a change of intensity caused by, for example, relative motion or blinking patterns, that pixel will trigger an event. And this generation is completely asynchronous in time, which makes it possible to actually generate low latency, high bandwidth perception control architectures. That's where I want to move on now. Let me show you some of the amazing results that you can get with an event camera. What you need to understand is that event cameras enable continuous time visual measurements in the blind time between two frames. And you get the idea here, where we were actually able to track features between two frames, just using events. And this is actually, for example, very useful for state estimation pipelines, like, for example, Visual SLAM. Here, we are going to show you in this video a camera being moved like a lasso, like a cowboy, very fast, because this is actually a scenario that is currently inaccessible to standard cameras. What you're going to see now, when the video plays, so on top left, you see the video by a standard camera, and on top right, you see the video by an event camera. They look different, but in the case of the event camera, during this motion, actually the images appear much sharper. And by the way, we don't have images. We have only events in continuous time. So we were able to actually detect features and track them in the blind time between frames. And then we could actually feed this to a traditional visual inertia SLAM pipeline, and we were able to estimate the motion during such very high-speed maneuvers. So event cameras make it possible to access scenarios that are currently inaccessible to standard cameras, like, for example, high-speed motion scenarios. Another cool application of event cameras is, for example, to dodging dynamic objects. This paper was published in Science Robotics 2 years ago, and here we showed that by using an event camera, on board, with onboard processing, we were able to dodge objects thrown at the drone with relative speeds up to 10 meters per second and with a latency of only 3.5 milliseconds. Using a standard camera, we would have required at least 10 times more, 35 milliseconds at least, because you need 2 frames to estimate the position and velocity of the object relative to the drone. And on top left, you see, on the top right, you see the events that were generated during these maneuvers. So we have an algorithm that can tell apart events generated by the moving object and by the static background. Looking further in the future, what can we say about the future of event cameras for robotics? So what we are also looking at is on event-driven control on neuromorphic processors. So the motivation is that agile maneuvers require low perception latency, but also high controller bandwidth. Just to give you an idea, the low-level controller of our first-person view of human-piloted first-person view drones, it's run at 8 kilohertz. So from this idea, can we possibly map as individual events directly to control commands? But then how do you actually execute it so fast? So there are processors that exist that are called spiking networks on chips, like the Dynaps, the Spinnaker, the Intel Loihi, and actually we are making progress on that. And the advantage of using these processors is that they allow low latency perception and also high bandwidth control. Let me show you a preliminary result on that. So the paper I'm going to show you was done in collaboration with Intel. It's an ICRA paper of this year, where we had a very simple task to mimic the 1D rotation of a disk by a human. So we have a human rotating a disk around 1 degree of freedom, and then we have a dual copter that tries to mimic the rotation of this disk. And here we used basically a spiking network that is running on the Intel Loihi processor with below a millisecond latency. Let me show you a cool result of that. So it's super fast. Actually, the only limitation now is the mechanical latency of the platform, no longer the processing latency, because actually it's much faster. So quadcopter are even too slow for this kind of chips and sensors, even. And this leads me to the concluding slide. Basically, where did we want to be? We want to be over the bottom right corner, but at the moment, basically, we are still below human level performance. But what are the main takeaways from this talk? Okay. Basically, I talked about agile flight as a new research topic. How long does it take to solve it? I think it will take at least 10 years to solve, to reach human level performance. And I think it's important to remember that the reason why it's so challenging, because it raises fundamental challenges for robotics research in perception, planning, learning, and control. I've also talked about learning-based methods, and I showed that they're more robust in terms of imperfect perception, and they have lower latency than traditional architectures. I've also talked about the simulation to reality gap, and I showed that it's possible provided you use the appropriate input-output abstractions. And then I shortly talked about event cameras. And what I want you to remember is that they reduce the perception latency. Also, they have no motion blur. And if coupled with neuromorphic chips, so they allow low latency, high bandwidth control. And with this, I want to thank you for your attention, and especially I want to thank my great team and the sponsors. Thanks a lot.
Yeah, thank you, Davide, for the very exciting talk. Are there any questions in the public for Davide?
Jan.
There's one.
So Davide, you make a big point out of that you, on the one hand, want to have much lower latencies, much higher sampling frequency, and reach human performance. But humans actually have a generically an extremely low sampling frequency. Vision is roughly at 30 hertz. Okay, tactile is faster, but that doesn't matter here. Mm-hmm. And at the same time, the visual delay alone is between 100 and 180 milliseconds. If you add the motoric delay, that's another 80 to 120 milliseconds, depending on where you send the motor command. So what are we missing actually there? Couldn't you all make it work with a much stronger feed-forward component?
You have a very good point. So actually we measured the latency, behavioral latency, and the brain latency of human pilots. We invited 20 human pilots, and we have an CoRL 2020 paper on that. And we measured it to be at 220 milliseconds, which is actually even larger than a car driver latency, which is around 150 milliseconds. The reason being that they have to navigate in 3D, and we speculate it's a harder challenge in that sense. But you're right, so this already shows that our algorithms can run much faster than humans. So what does it take to get better than humans? Robustness. So actually humans are extremely more agile at making more robust predictions about the future, gaining from experience. And that's where actually we want to work on, basically on more robust perception and predictions about the future. That's where I think the key issue, bottleneck is. And so this requires a big effort from the whole community. So we are all working on these problems, right? More robust perception and prediction for autonomous driving cars, and flying cars and drones. So at some point we will get there, but it's exactly what I think is actually needed. That's where humans, despite their high latency, are much better than machines.
Okay, there's another question down here.
Great, thanks for the great talk. I have a question. So in the maneuvering, so the how is it
the acrobatics?
Acrobatics, exactly. In the acrobatics one, you had you directly compute in the simulation the trajectory, and you directly send it essentially to the system. Whereas in the wild manipulation, you had another step behind it, right, to probably compensate for the mismatch of your simulation. So what is your general take? Do you think it's better to, make the simulations match directly the system, or would you think that this additional step is a kind of a good way to?
I don't have a concluding suggestion there, because I think it very much depends on the task, and so I don't want to be too hard on one thing. So the acrobatic maneuver is very reactive. Okay, we want to decide how to steer the drone image by image. So we don't need to make predictions like in a receding horizon manner. While in the navigation in the wild, we already know it from state-of-the-art traditional controllers that if you do receding horizon, traversability path prediction, you can actually make better more robust decisions. So there we also try to do directly to regress control commands like we did in drone acrobatics, but actually the performance was not very good because you want to make more prediction into the future. Just to give you an idea, also there we tuned the prediction horizon. I didn't have time to talk about that. Our prediction horizon was 1 second because we are flying up to 10 meters per second, and the network predicts 3 trajectories together with scores. Each trajectory is parameterized in terms of 10 waypoints. Okay? And by the way, also to deal with ambiguous situations, for example, if you have a tree right in front of you, do you go left or right? So if you just train the network to predict a single output, a single trajectory, you will probably guess that the right one would be the one in the middle, and then you will collide. So that's why actually I didn't have time to talk about that. But actually we have a multi-hypothesis prediction, where we actually we predict 3 possible trajectories together with their each individual score. Then we select the trajectory to execute depending on the vicinity to the previously executed trajectory and the score, which depends on the collision probability. And then we execute this one with the monetary predictive control. So actually it's for robustness and that we choose to go for this receding horizon, and also to reduce the sim to real gap, because it would actually, we realize it would take even longer, more training data to go directly to control commands.
Yeah, thanks. Very good.
Okay. I think we have one question from the chat. Rudolf, are you?
Yep. So Gerhard is asking, could you say a bit more about the nonlinear MPC methods used here?
This is the same MPC that was used in that slide over there, which we also open sourced, where basically we have several waypoints. We want to basically minimize the trajectory tracking error by satisfying the under-actuated system dynamics. We also want to minimize the saturation of the actuators. And then we solve this basically with ACADOS. And the reason why it works so fast, because many people usually ask me, but how do you manage to run MPC so fast? It's because we use a real-time iteration, which basically means that we are actually executing the maneuver while the optimization is still converging. So we use intermediate optimization results, and we start to execute it with this initial guess, while the optimization is still ongoing. Okay. The code is open source.
Okay, let me ask one more question. What's your opinion about the role of hardware development for machine learning in robotics? We had this discussion, I think, in one of the Blue Sky sessions. I'd like to know what you think about that. So how does one influence the other, and what's the future there?
I think that the key problem that we will hit at some point is the power consumption. So we are going towards more and more expressive networks. And so it will not be difficult to achieve a human level performance in anything. The real problem will be that at some point we will consume too much electric power. So in my department, Professor Giacomo Indiveri is actually pushing a lot on spiking networks. And I mean, a very nice example that he always makes is, with the spiking network processors, doing the same task of a standard ANN, you only need to change the batteries every 7 years, with a standard ANN every 3 months. So I think that would be the key thing. Okay.
Thank you. Okay, any more questions? Look at the chat.
Can I ask a question?
Yeah.
Can I ask your opinion also about this neuromorphic chips and its development?
So at the moment, they are not as expressive as standard artificial neural networks. Also, what I haven't told you there is that actually we are mapping standard CNNs into SNNs. But in that case, we were not actually retraining on the chip, which is actually what you would like to do to further fine-tune in order to get even better performance. So backpropagation was not available for some time. It was not very, very easy to do. Now there are algorithms that allow you to do that. So, but everything is very new. Okay, so I'm excited to see it, but I think there is still a lot of research that has to go into that. Okay, but I think now what the spiking network community has to show really is that you can solve the same level of tasks that you can solve with ANNs. We all understand what the promise will be. Activity-driven computation, meaning for every single event you can generate an output, which is amazing. We all understand the low power thing, but now you need to really work on expressiveness of these networks and show that they can do the same as standard ANNs.
Okay, yeah, one more question here.
So is the reason of using the nonlinear MPC to conquer the gap between sim to real? That's the main reason?
Yes, we show basically in the paper that with respect to regressing direct control commands, we have a lower sim to real gap. That's correct. It's an output abstraction, basically.
So do you have any thoughts on doing this training in simulation and using a more learning-oriented MPC, not even MPC, learning-oriented methods in the real world to conquer this sim to real gap, or not even sim to real gap if you directly train in the real world?
Yes, you can also do that, of course. What we are doing now is that we are going towards more also learning low-level controllers as well.
Yes.
Still, there is a lot of work to do there. Also, again, in terms of data collection as well, tons of data that you need, because eventually the bottleneck is always that there will always be a mismatch between reality and simulation if you want to beat humans. So now humans learn by reinforcement learning, right? And then they can immediately learn these aerodynamic effects. So you give them a new drone, in a few hours, they're able to perform race tracks very quickly. So they seem to actually be able to learn all these aerodynamic effects. And that's something you cannot simulate in the real world. I mean, we are trying. We are trying. We also have an RSS paper where we try to learn the residual torques and forces acting on the quadrotor. And then we add them to the standard first principle model. But still, there is always there a gap. And there we want to actually now overcome this gap.
Okay. Yeah, so the reason why I ask is because if humans also learn in the real world by watching the drone executing the trajectories in the real world, is there any possibility that the drone, the AI, can also learn out of those real world deployment trajectories?
Yeah, that's exactly where we are going to. Yes, that's exactly where we're going to. Remember, the humans typically, the humans we want to outperform are the ones that rely on FPV, first person view, not the ones that are relying on a line of sight. And so they see the whole trajectory from a third viewpoint, but only from the first person viewpoint.
Yeah.
Okay.
Thank you.
You're welcome.
Okay, I think we have one last question from the chat. Rudolf, are you?
Yeah, so Wei wants to know if there's a robust way to deal with the event camera sensor fault to make sure that the drones don't crash on fault.
Excellent. Actually, I have a slide for that. Is it possible to go back to the slide? No. Okay. So we have an ICRA paper where basically we put onboard cameras, an event camera and a standard camera, and then we induce a rotor failure. So rotor failure is one of the biggest problems of commercial drones. Of course, there are not many commercial autonomous drones out there, but in Switzerland we have had more than 5,000 autonomous flights for delivery between hospitals in 4 years, and there have been 2 crashes. One of them was caused by failure of a motor. So what happens when a motor fails? If you don't have a good position measurement, then the drone actually drifts away and then eventually crashes. Now, if you have GPS, it's fine, but what if you are in the vicinity of a structure? So now you should rely on, for example, onboard sensors like cameras. Now, standard cameras, basically what they will experience is motion blur, because when a rotor fails, the quadrotor starts spinning on itself because of the principle of conservation of angular momentum. Now, with the event camera, you suffer from no motion blur. So actually, we showed in that paper you can consistently track features and estimate the full state of the drone despite this very fast spinning motion. So we think that this could be actually a viable sensor to be used to make drones safer.
Very good. So thank you again for the speaker. I think we have to move on.
Thanks a lot. Thanks a lot.
Okay, thank you. And actually, let's see. I would like to take a moment to say a hearty thanks to all of the organizers of this year's CoRL 2021. Alexandra is right here with her wonderful daughter Nina, who deserves a lot of thanks also. And so let's give a round of applause to the It's a huge task, and they've been working for many, many months on it. And my job today is to give you some information about the plans for next year. And slides are working their way up there. So there was I asked some questions yesterday about your wish list for next year, and so a lot of ideas. And someone asked for a new hemisphere. So I'm happy to say we're going to try and make that work. And the location here has got a beautiful scenery and rich culture. It's a very metropolitan city at the same time, very contemporary, and it is it's in Auckland, New Zealand. So I'm really excited about this. I want to say the plan is to push it a little bit later, and so it's going to be in December 15th to 18th. And the reason is because that's when their summer session starts in New Zealand. So it'll be warm weather, it'll be nice, and hopefully you can plan to stay a little longer. And we have a fantastic conference venue. It's a brand new building that is the business school there at the University of Auckland. And so we'll be situated in there. We are going to have a welcoming reception at this beautiful museum. Now, I can't promise Caravaggio's and Velázquez and Manet next year, but we are going to give you a banquet with Boeings and Airbuses and various Fokker airplanes. So there's a museum of transportation, and we're going to be hopefully in there dining right underneath the aircraft. And the location, if you see in the upper right, those green areas are metropolitan areas with lots of cafes and bars and restaurants and nightclubs. So we're very close to a whole center of action there. So there'll be lots to do at night and even during the day. So if you have to sneak out from the conference to grab a pint or something, so that's been very well planned. There's lots of the food there. It's very cosmopolitan and lots of things to eat. Very rich nightlife, and the New Zealanders are known for their ability to party late. So we'll have to do our best to keep up with them. The organizing committee, I'm proud to say we have a terrific committee so far, and we're still growing it. Karen Liu from Stanford is going to be the program chair, working with Donna Kulich of Monash and Jan Peters, who from TU Darmstadt. Jan was here, so he's here right there. Hey, Jan. So they're going to be working together on the program, and Minas Larry Kappas is going to be the local chair. So if you really would love to get involved with this, please get in touch with me. I'm Ken Goldberg, and goldberg@berkeley.edu. I'm happy to take, we really would be welcome you as volunteers or to get involved in some way. And if you have suggestions, please let me know as well. The idea is we're going to also have a very compressed reviewing cycle. We're cut between two sort of immovable limits, which is we want it to be after RSS for some full submissions, and then we want to get decisions out to you before ICRA. So that's a very tight window. So we're going to do our best, but that also means we're going to be counting on you as reviewers to turn around papers pretty quickly. So we're going to do our best on that, so bear with us. We'll give you plenty of notice. Please start planning your papers now. We're looking forward to receiving them, and I have to say, this community is fantastic. I've been such a pleasure and such high-level discussions. The interactions have been fantastic every step of it. So I'm really looking forward to seeing you next year. And let's see, do I have a final? Okay, there we go. Thank you all.
Should I talk or not?
Helping, we got pushed back a little bit. Just hold. Okay, I think we're ready to go.
Cool.
Yeah. Okay, now we're going to next session, next oral session. First of all, I'd like to see whether my co-chair is still there. Rudolf, are you there?
Yes, I'm here. Are we streaming live already? Oh, there we go. Okay.
Okay, good. Very good. Yeah, so we have 4 speakers in this oral session, and they're all here in person. The first speaker is called Xiaoping Su from the University of Toronto, and he's going to present his work on seeing glass, joint, point cloud, and depth completion for transparent objects. Where is the speaker?
Hello, everyone.
Ah, there. It's not, he's online. Okay, very good.
Yeah, I'm online. Yeah. Okay, I guess I can start now.
Yes.
Yes. Hello, everyone. I'm Haoping Xu, a PhD student from University of Toronto. Today, I would like to talk about our paper, Seeing Glass, Joint, Point Cloud, and Depth Completion for Transparent Objects. Transparent objects are commonly seen in kitchen, lab, and industrial scenes. All of them have the potential to be manipulated by robots. One particular use case we are interested about is automating the chemistry lab. Existing methods like this robot arm from Professor Andy Cooper's group can already perform material discovery experiment using Bayesian optimization. Yet they mainly relies on position-based control to manipulate transparent glasswares, as vision system cannot handle them reliably. Why, you may ask? Unlike humans who can easily detect and locate transparent objects in a picture, RGB sensors see a scene like this differently. When comparing the raw depths from the sensor with the ground truth depths, the transparent objects are almost completely invisible in the sensor's view. The difference is more significant if we deproject the depths into a point cloud. This difference is mainly due to the transparency nature of the glassware as well as the highly reflective surface. Existing methods like ClearGraph and LIDF takes the RGBD image as the input and train a network using a synthetic dataset to aim to fix this problem and predict the whole scene's depths. Additional methods like LIT and keypulse use only the RGB images and predict the object depths using a model-based approach. That is saying you have to know the object's CAM models in order to do the predictions. To recover transparent object depths, we propose TranspareNet, a novel joint point cloud and depth completion pipeline, taking the RGBD image as well as the object mass as the input. In the pipeline, the point cloud completion network firstly generate a sparse depth prior, and then the depth completion module takes the sparse prior RGB image and object mask to predict the final object depths. With our joint pipeline, one goal is that the distorted transparent object depths discarded by existing methods can be effectively utilized via our point cloud completion modules and can be used to guide the generation of the sparse depths prior which can be used later on for the depth completion module. Well, when we compare it with ClearGrasp, you choose to mask out the transparent object depth showing on the right. Transparent net can recreate the object depth with high accuracy, and when compared to existing methods, it outperforms the state-of-art LIDF on ClearGrasp dataset. To train our pipeline, transparent object datasets are needed, yet existing datasets have their limitations. For example, some datasets have limited real image collections, for example, ClearGrasp, and others lack of the depth informations, and many only includes empty objects, whereas in real life, filled glassware are commonly seen. And finally, most of them are collected in a slow manual creation method. Because of that, we'll create our own data set with sufficient size, close to real objects filled with different contents. And most importantly, we propose a fast automated creation pipeline, which allows swift expansion of the data set to include additional objects. Currently, our data sets have 6 different objects. Each of them may contain 6 colors of liquid as content, and they are placed in 4 different backgrounds. For our dataset creation process, with the eye-in-hand RGB camera mounted on the robot and an April tag-based annotation method, we gain about 10 times speed up compared to ClearGrasp methods. And also, we reduced the human interaction requirement by around 2,000 times. Currently, each image takes around 3 seconds to be collected and annotated, and human interaction is only required once every around 500 images. The eye-in-hand camera can scan the scene from various viewing angles and distance automatically by carrying by the robotic arm. And for each image captured, the object pose are derived from April tag pose, and a virtual scene is created by placing the CAD model to the corresponding object locations. With the recreated scene, annotations including instant segmentation mask, ground truth steps, and object pose are generated and recorded. Additionally, our automated creation pipeline can quickly gather other datasets to expand the scope. For example, we add 2 additional objects to our datasets with around 4,000 images using less than 4 hours. This allows the community members to tailor the dataset according to their applications by including the targeted objects. With the dataset, we train our point cloud and depth completion modules separately. Let's first look at our point cloud completion network. For this part, we reframe the depth estimation problem into a point cloud completion problem. To do that, we first isolate both raw and ground truth depths for each individual objects and deproject them into incomplete and complete point cloud pair, and then use the pairs to train the point cloud completion network. And the network's output is being projected back to the depth space and then merge with the raw depths to create the spots prior. The point cloud deprojected from the depths differs a lot from common point cloud datasets like ShapeNet, where our point cloud completion module is pre-trained on. Because of that, it needs to be pre-processed in order to maintain the point cloud completion module's performance. Namely, we do a recenter and rescale process before feed it to the network. For our point cloud completion network, firstly, the incomplete point cloud is voxelized into a 3D grid where each cell's corner weight is sampled from the points lying inside a cell. And the half-filled grid is populated using a 3D CNN network. And a coarse point cloud is sampled from the filled grid by sampling the points inside each cell using its corner weights. Finally, a MLP takes the coarse point cloud as well as the populated grid features to do a final refinement and predict the completed point cloud. To evaluate the point cloud completion network's performance, we project the depths back to project the point cloud back to depths and evaluate it using the following three metrics: root mean square error, mean absolute error, and absolute relative difference. Point cloud completion module alone can recover depths with high accuracy from the raw sensor reported depths. When we only consider the non-zero depths reported by the network, its accuracy even outperforms our combined transparent net pipeline. Yet, due to the 3D CNN low resolution, the network's predicted depth is very sparse with many missing depth areas shown here. Because of that, the sparse depths overall performance is considerably worse and cannot be used directly, so we treat it as a prior for the depth completion module. Now let's look at our depth completion parts. Our depth completion module takes the sparse depths from the point cloud completion module and the RGB image and use them as the input for a refinement-based encoder-decoder network. And we use a decoder modulation branch and take the mask as the branch input. This is aimed to focus the network attention to complete the depths only within the transparent object regions. And finally, we will output the final depths. Our depth completion module alone, trained on Cleargrass dataset, outperforms Cleargrass and LIDF, which is the current state of art on the Cleargrass dataset. And when we combine the point cloud and depth completion module together to form the transparent net pipeline, we find for the network trained on our own dataset, it outperforms both Cleargrass and our aforementioned depth completion module alone in all three types of scenes, including from 1 to 3 transparent objects. Here are 3 examples from our test set. The red brackets showing in the figures show the regions where transparent net outperformed the depth completion module alone. Overall, we find that transparent net has a better performance for closed up and occluded objects. However, our methods still have a hard time in certain complex scenes. Here are 3 examples we find. Mainly, the scenes are the filling cases are associated with highly overlapped objects. In summary, transparent object depth estimation is a challenging task, requires ongoing research. In order to solve this problem, we propose an automated dataset creation pipeline and collected a dataset with 15,000 images with the potential to scale up to additional objects quickly. And finally, we proposed transparent net, a joint point cloud and depth completion module, which is the new state of art on Cleargrass dataset. And finally, I want to thank my co-author Iru and help from Sagi Apple and my advisor Alan Astru and Iru's advisor Animatch and Flory.
Presentation.
Thank you, Oping.
Any questions here? Having a look at the chat. Yeah, so I might have a question. How much does your approach depend on the shapes of the training data set? So how would you extend that to maybe different kind of objects that are not in the training data, especially the depth completion, right? I guess that depends a lot on the shapes of the object that you have.
Yes. Currently, our dataset is mainly focused on the glasswares commonly seen in the lab. So I would say it's kind of semi-focused on that. But when we test it on the Cleargrass dataset, which include additional objects, for example, like a transparent heart, it still performs relatively well. I would say it's not very dependent on the object shape. And additionally, if you are mainly working on objects that is not close to a container, you can always use our pipeline to expand the data set.
Okay, thank you. There's one question here.
Hi, so how would your network deal with non-transparent objects? Because I guess in reality you would have both transparent and non-transparent objects.
For the non-transparent objects, we will basically doesn't do any completion on their depths, because the depth sensor alone can obtain a good enough depth for the for non-transparent objects. So it basically will be masked out.
And you've done some tests on this, or?
We haven't do any test on like a mixing with like transparent and non-transparent objects yet. Yeah, sorry for that.
Yeah, thanks.
Okay. Are there any questions from the chat, Rudolf? Is she still there? I don't see any. Okay, in that case, let's thank the speaker again. The next speaker is Samuel Clark from Stanford University, and he's talking about diff impact, differential rendering, and identification of impact sounds.
Hello, I'm Samuel Clark, and I'm here to present our work on differentiable rendering and identification of impact sounds, a project we call Diff Impact. I want to start off by trying to illustrate to you your own mental intuition about impact sounds. Here I show an adversarial example for inferring materials from vision only. One of the glasses here is in fact plastic, and one of the seemingly steel forks is plastic as well. So now I'm going to play this clip, and if you listen carefully, you'll hopefully be able to classify the materials of these cups. And if you listen especially carefully, you may even be able to classify the materials of the forks. Great. So if we could have heard that, if you could successfully classify the materials of the glasses, what you could imagine how you could have done this, and it's going to have a dollar sound. So if you could successfully classify the materials of the glasses, what you likely just mentally did is called source separation. When the glasses were each struck with a fork, you never heard the impact sound of the glass itself, but rather heard the combination of sound of both the glass and the fork. Yet you were still able to mentally attend to the sound of the glass to classify it. And perhaps you could have even done this if there were noise or conversation occurring in the background of the recording. So, could you also go to the next slide for me too? Okay. So if you go through more thought experiments like this, you may realize that humans generally have a very powerful intuition for mentally reasoning over forward and backward problems relevant to impact sounds. So how can we give this kind of capability to robots? Well, first off, let's look to prior work to examine foundations we could build upon for structuring our reasoning about impact sounds and doing this kind of inference. Existing model-based methods for rendering impact sounds fit physically interpretable parameters, which can be more easily transferred between tasks or used to extrapolate or hallucinate unheard sounds. But these either require controlled recordings, such as striking objects with small pellets, or they are not differentiable and thus can only optimize over a few parameters at once. On the other hand, deep learning-based methods, mainly coming from human speech synthesis applications, can learn from data in the wild, but the parameters they learn are uninterpretable. More recently, in 2020, a team at Google debuted DDSP, a differentiable audio renderer designed for musical instrument sounds, which they showed could learn interpretable parameters from data in the wild. But these parameters were relevant to music and not as relevant to the physical properties of rigid objects evident from impact sounds. Diff-impact brings the advantages of differentiable rendering to impact sounds, using the techniques of model-based methods to achieve sample efficiency and physically interpretable and transferable parameters, yet being fully differentiable to learn from data in the wild like deep learning-based methods. But at this point, you may be wondering why we care about physics-based models with interpretable parameters. If we can extract physically interpretable parameters about objects, tools, contacts, environments, etc., we can easily reuse the parameters to extrapolate and simulate new impact sounds using new combinations of parameters of contact conditions, objects, and environments. Oh, sorry. To see how we can extract these physically interpretable parameters from controlled recordings, let's consider the physics of impact vibrations. It turns out that an impact sound can be broken down into two main components: the extrinsic forces acting on an object, or the impact force profile, and the intrinsic acoustic model of an object, that is, its impulse response. The convolution of these two components is the most fundamental aspect of an impact sound. Other components, such as background noise and reverberation, are also big contributors, but for the sake of this presentation, I'll mainly focus on the forces and the impulse response. If we can decompose an impact sound into each of these components, we can infer important properties of objects and how they were contacted. Then, as I showed earlier, we could even specifically swap out the impact or object parameters to simulate new sound in a new acoustic environment. But decomposing an impact sound into these constituent contributions is an ill-posed problem, since we're essentially trying to perform a deconvolution. The key idea behind diff-impact is that we can bias the decomposition of impact sounds by using physics-based models to provide both a helpful model bias and extract physically interpretable parameters. So I'll start by focusing on how we parameterize the impact force profile with a physics-based model. The first thing to know about impact forces is that they are generally not ideal impulses. They have different sharpnesses to them depending on the velocities, shapes, and hardnesses of the colliding objects. So we use a Hertzian half-sine model of contact forces, which can be parameterized with the timing of the impact, the scale or magnitude, and the time constant tau, which represents the sharpness of the impact. More specifically, we use a Gaussian approximation of this model, which has the same parameters but has smooth derivatives. We model an impact force as a linear combination of m impact events, each parameterized by the three parameters I just illustrated, to create a time sequence of multiple impact events. So next, I'll explain the physical model behind the object impulse response. Rigid object vibrations are well modeled by modal vibration models, which are based on spring damper models of a network of particles within the objects. As shown here, each object has multiple modes of vibration occurring simultaneously, with each mode vibrating with a different frequency, initial gain, and damping. So an object's impulse response can be expressed as just a sum of exponentially decaying sinusoids. Diff-impact models this by assuming the impulse response of an object is a finite impulse response, which is a linear combination of n modes, where each mode has only three scalar parameters: a frequency, a damping, and a gain. So I've explained the physical models we use for the impact force profiles and the object impulse response, which we convolve together to get an impact sound waveform. So the main thing that's left to do is explain the loss we're optimizing against. For our loss, we compute magnitude and log magnitude spectrograms of the original ground truth audio, and then compute the same for the audio synthesized by our model, and then take the L1 difference between the two. So now let's see how this plays out on an example of a studio recording of striking a ceramic mug multiple times. Here's the original recording. We're all going to say a prayer here. So, to model and extract parameters from this real recording, we start by initializing a random series of impact forces and a random impulse response, which are convolved to get a running estimate of the synthesized waveform. We take the spectrogram of this and then compute the L1 loss against the ground truth spectrogram and adjust the parameters of the upstream models during the gradient descent optimization. Here I'm going to kick off that optimization. And here we have estimates of the extrinsic impact forces and intrinsic object impulse response, which result in the following synthesized clip. Now, our full model is a little more complex than this, and I'm happy to explain in more detail if you find me at the poster session. For now, suffice it to say that we also parameterize models for the background noise and the reverberation and combine them into the final audio, so you can extract those two components of the impact sound recording as well. We evaluate our model in 3 different applications. First, showing that we can learn from controlled recordings in a studio, just like existing model-based methods. We next show a passive learning use case where DiffImpact can outperform existing deep learning-based methods to enable a robot to learn acoustic models of objects passively from data in the wild. And finally, we show an interactive learning example where DiffImpact can equip a robot to learn separated acoustic models from impact sound recordings it collects in a noisy robotics lab. First, I'll show examples from the experiment on controlled recordings. We wanted to show that DiffImpact can match real impact sounds, and that because of its physics-based model bias, it can infer physically meaningful quantities about the impact. We took recordings of hitting everyday objects with an impact hammer to record both audio and ground truth impact forces on the objects. DiffImpact then fits a modal response for each object and makes an estimate of the impact force profile over time using only the ground truth audio as supervision. Here we show how well our model can re-render the sounds made by the ceramic mug. Our model is also able to infer relative impact forces that closely approximate ground truth using only audio as supervision. Here's the ground truth recording. And here's DiffImpact's generated output. Our next experiment shows how DiffImpact can enable a robot to learn passively acoustic models from in-the-wild impact sound data with many imperfect impacts through an end-to-end learning task. We first curated a dataset of audio from ASMR videos where the creator is finger tapping different everyday objects. We then used DiffImpact as a rendering layer in an autoencoder for impact sounds. Our model and all baselines were given the ground truth magnitude-only spectrogram as input, then were trained to reproduce the sound from the spectrogram using ground truth audio as supervision. We compared our autoencoder based on DiffImpact to other autoencoding baseline frameworks which were designed for musical instruments or human speech audio. For our evaluation, we performed human studies where we showed our participants the original ASMR video redubbed with audio synthesized by each of the different models, then asked them to choose which redubbed video looked and sounded more realistic in a forced choice. So here's an example of a redub video where the ASMR creator is tapping a ceramic plate. Here's the video with the original audio. The audio from our DDSP Sarah baseline, which is from a differentiable renderer with models designed for musical instrument sounds. And the audio from WaveGlow, a flow-based model-free deep learning architecture designed for synthesizing human speech. This baseline better approximates ground truth, but you may notice some high-frequency noise in the audio. And finally, here's DiffImpact's audio, which has much cleaner transients and impact sounds than the alternatives. We hope you agree with the participants in our human studies that DiffImpact produced the most realistic redubbing compared to the alternatives. For our final experiment, we showed how a robot can use DiffImpact to learn acoustic models of objects interactively by striking them together in a noisy robotics lab. To collect impact sounds of objects, the robot strikes different household objects with different household tools. If you remember back to the thought experiment with the wine glasses at the beginning, when the tool and the object strike each other, the resulting sound is some composition of both the sounds made by the tool and the sounds made by the object. But soon, I'll show you that the robot can use DiffImpact to separate the sounds of these objects from each impact it sounds it hears. Then use these separated sounds to better classify materials and infer properties about them, just like you did in the thought experiment at the beginning. Here are the results from separating the sounds from a steel fork striking a ceramic mug. The fork and mug make very similar sounds, but DiffImpact is still able to capture their differences. Here's a video. Now in the microphone's recording, note that there is still some robot motor noise. In order to separate the sound sources, our model composes its sound by fitting acoustic models for both the object and the tool, as well as the background noise, combining all these elements to produce the final sound. So we can just turn off the background noise to generate the denoised version. And we can turn off the mug's contribution and isolate the fork contribution to get only the estimated fork sound. And here we do the same to isolate the mug sound. Along the way of synthesizing the sounds of impact, diff impact is fit an acoustic model for each object. Here are diff impact's synthetically separated impact sounds from each object. Here's the ceramic mug again, the polycarbonate cup, the steel bowl, and the wood holder. And here are example separated sounds from each of the tools. Note that these sounds have all been separated from a clip of each tool striking a much louder object, which dominated each recording with its impact sound. Here's the ceramic chopstick, the polycarbonate spoon, the steel fork, and the wood spoon. At the beginning of this presentation, you imagined mentally separating impact sounds to classify materials of the wine glasses. Similarly, our model separates sources of these pairwise impact sounds, and here we'll see an example of something this can do for manipulation robots. We first constructed a classifier to classify materials from sound and trained it using a publicly available dataset of purely synthetic impact sounds. Here's the classification accuracy we get from trying to classify materials from the original audio. Here's the accuracy from separated object and tool sounds from each object with our model-free source separation baselines. And finally, here we have the accuracy from using sound separated by diff impact. Diff impact similarly outperforms our baselines for being used to regress Young's modulus from separated sounds. Estimating such properties before manipulating an object can inform the robot about how it can safely and effectively manipulate the object. Finally, to summarize the key takeaways here, diff impact uses physically interpretable parameters which can be used for simulation and extrapolation. It's differentiable, so it can learn from recordings in the wild. And then it can solve many dual forward and backward problems with just one framework. And then use these results for important downstream tasks in robotics, such as material classification and stiffness estimation. And with that, I'd like to thank both my co-authors and the others who made this work possible. It took a village, and open things up for questions.
There's a question here.
So how important is it to initialize your model in the right vicinity when you do the differentiation? I mean, you have all these different modes, right? The harmonics and so on. So I guess there are like a lot of local minimas that you can run in.
Yes, that's very true. It was important to initialize, and I did have to tune some hyperparameters. For example, if you make the gain on the filtered noise too high initially, then it will just try to fit filtered noise to whatever sounds it hears and stuff. So that was a little sensitive to initialization. Fortunately, it wasn't too sensitive, such I didn't have to spend a few months tuning hyperparameters, and I was able to use the hyperparameters for all this, the same hyperparameters for all these recordings. But yes, their initialization is important.
One more.
Can you comment on the sample efficiency of your methods and also maybe potential transfer without having to interact with every single kind of object?
Yeah, I'm glad you asked about that. Actually, so I showed 3 experiments. The first was the analysis by synthesis experiment, where I showed a 3-second clip. That was trained only on that 3-second clip. So it overfits, but the impulse response is the impulse response. Then with respect to the ASMR data set, each of those was about a 5-minute long clip of a bunch of imperfect impacts because she taps it slightly different each time with her fingernail, fingertip. Then finally, the source separation, I had 4 objects by 4 tools, so 16, and I had 2 samples for each object. Each audio recording was less than 2 seconds, so about 60 seconds of total data just to fit all of those acoustic models of the object. So that was part of the advantage of this differentiable model-based renderer, was the sample efficiency.
I think people on the chat don't hear you.
Could you say something about
Yes, so the person on the, do you want to go?
Yeah,
go ahead.
I just need, because people on the chat need to. So the question is about the geometry of the objects. How much does that influence the method?
Yes, that is very important. As I showed in one of those slides, I showed the modal vibrations. So those heat maps were of the gain. So if you strike in different locations on the object, you're going to excite all of the modes at different gains, so initial values. So since we didn't have that data we didn't have labels for where they were struck, we just assumed that the object had one unified impulse response. That's not necessarily intrinsic to our model, though. It's all a matter of the upstream parameters that get passed to it. So our model has provisions for modeling those, and such as like an implicit model or something like that. It's just a matter of passing in the gains to our differentiable modal impulse response generator.
Follow-up question or no? Good. There's one more there.
Hi, do you think this model could be used like in the opposite direction to have a robot touch slightly with some kind of tool objects and help classify the materials?
It could touch two objects and
No, whether the robot with some sort of tool can like hit objects and based on the sound use it to classify materials of the objects.
Yes, I think if the robot had a known tool, I mean, here we just had we did like a cross product of these tools and objects, and especially if the robot had a known tool or even just its own end effector and had an acoustic model of that, then it could more easily just separate out the sound from that. And yeah, so a new query object would be that much quicker to classify. Maybe you wouldn't even need 2 trials or something like that.
I have a similar question to the one over there about the geometry of the objects.
Mm-hmm.
So you represented the spectrum as a, say, sine series.
Mm-hmm.
And of course, normally the modal vibrations come from the Laplacian eigenfunctions on the domain of the object. So if you're solving it on a drum, for example, you get the Bezel functions arising. So could you use some kind of photogrammetry? Would the performance of the model be improved if you use some kind of vision technique to kind of build a model of the object and then found the Laplacian eigenfunctions to try and get a more accurate picture of the spectrum? Would that help?
Yes, I think it would. If we did assume that we did try to model these different impulse responses, yes, I think that could definitely help. That would be challenging because, I mean, contact detection from video is hard in the first place, let alone pose estimation while you're holding it. So we kind of stayed away from the hard problems in vision and focused on the hard problems in audio. And I think that is the next step, to go back to the hard problems in vision, which we hope are kind of jump-started by these kind of interpretable parameters being a bottleneck.
Cool, but it's a really cool project. So yeah.
Thank you.
Yeah, thank you. I think we have one more question from the chat. Rudolf?
Hey, we already talked a little bit about the impact of the shape on the method, and there's a question from Dylan touching that. Can you comment a bit on the ability of these models to identify certain object properties, for instance, the size of the object or actually the shape itself?
Right. So I think that is... So we extracted a bunch of physically interpretable parameters, which just, model the impulse response through these modes and everything. And I think there are some analytical techniques that you could use to directly work over those. What we showed in our paper, however, was just that using these tools, we could clean out the sounds better and use like kind of more black box methods, just off the shelf regression networks or classifiers to do something like scale detection. So theoretically, you could train a scale detector network on a bunch of data, and then perhaps diff impact could be used on the data that had essentially been cleaned through the algorithms that diff impact offers. On the other hand, I think down the road, it would be interesting to use the physically interpretable parameters to directly estimate some of those important properties through analytical techniques. For example, if we know the damping of each mode, given the frequency, theoretically, under the Rayleigh damping model, we should be able to predict some important features about the density and also the alpha and beta value of the acoustic alpha and beta values of the materials. So I think that is something that could be used, but right now there's a really large sim to real gap in audio simulation. So we have to figure that one out first.
Okay, thank you, Samuel, again for the very interesting talk. And we move on to the next speaker, which is James McDonald from UC Berkeley, and his work is entitled Guided Imitation of Task and Motion Planning.
Great, thanks. So yeah, today I'm discussing work that describes an approach for using task and motion planning to train goal condition policies for robot manipulation. Let's set the stage. In recent years, we've seen an impressive expansion of both robotics and AI into automating industrial settings. These are still limited to scenarios like we see here, though, environments where you have very low variability in the configurations the robot might encounter. The tasks themselves are mostly small variants off the same basic motion, and the tasks only need a few steps in order to be accomplished. We'd want to extend these into more dynamic scenarios. So for example, here we see an Amazon fulfillment center. This gives us something that's still controlled, but is going to encounter much more diverse sets of scenarios. And so we need to account for more diverse sets of tasks. We also will want to be able to reason over extended sequences of actions in order to accomplish these tasks. You could consider placing an object down low versus having to climb the stairs to place it up high. How might we go about approaching this? Let's look at some of the existing approaches we could try. And as you may have guessed, the first one I'll talk about is task and motion planning. So here I'm going to use a simplified problem to highlight the concepts, and later I'll build back to more meaningful domains. This is our initial state. We're going to have a cylindrical robot with a gripper and some objects, and the goal is going to be grab the green object and move it to a target while avoiding collisions. Now, there are a lot of ways to go about task and motion planning. Here are the citations for the approaches we adopt, and you can refer to our paper for further details. But roughly speaking, we're going to break it into two parts. The task planner is going to operate on a logical representation of the world and produce a sequence of discrete actions to accomplish the goal. Grab the object, place it on a target. Now, these aren't simple subroutines we can just call. We need to turn them into an actual trajectory. So the motion planner is going to start the grasp action, and it's going to go through and produce a sequence of controls to reach the first waypoint. And then I'll do the same thing for the place action. And finally, we have a set of controls that can accomplish the goal. This is where we're going to enforce things such as collision avoidance and kinematics constraints. This isn't a one-way street. Let's add an extra obstacle into the mix and assume the task planner produces the same plan as before. Now, let's also assume the motion planner goes through and tries to refine the grasp. But let's say we're running something like local trajectory optimization and get stuck in a bad optima. The planner is going to say, hey, I can't get around this collision. And it's going to pass that information back to the task planner, which is going to update its logical state to account for the collision and then replan to avoid the obstacle and keep going. And now the motion planner can find a valid trajectory. So to recap, we have two nodes, task and motion planning, and they pass information back and forth until we find a valid trajectory that reaches our goal. So the nice thing about this is because the motion planner only has to operate over short horizons, it can solve problems that have high precision, complex geometric constraints. And then the hierarchy allows us to tractably extend this to problems that may require even dozens of actions. So let's see this in action on a toy problem. Here it gives us a nice smooth motion to grab the object, place it on a target. Now this is all great, but there are some big issues. The first is that task and motion planning is very slow. Actually computing the plan takes a long time, even though we can do it. And in order to transfer the plan from your simulation into the real world, you need to have precise state tracking. So what are some of the other things we could try? Well, this is a conference on robot learning. What if we train a policy? So we've all seen impressive applications of deep learning in recent years to perform complex manipulation from high dimensional observations such as camera images. And because forward inference in a neural net is very quick, this gives us something that's very fast to execute in practice. So to see what this might look like on our toy problem, here we ran proximal policy optimization to train a policy on the same task. Now notice that it's settled into this kind of nudging and bumping along motion instead of grabbing the object and placing it. This is after we ran extensive reward shaping to try and encourage it to first grab the object and then place. What we found was we could get it to either grab it or place it, but not both. This was after training for 10 hours across 60 workers and evaluating several different algorithms, as well as performing hyperparameter tuning. Now I want to be very clear here, we're not saying that this is the best you could do on this problem, but it highlights that what was a rather trivial problem for the planner to solve is actually quite difficult to train a policy for. And the issue here is that because we no longer have the constraints on the motion, we just have a less precise form of control. We're going to build up small errors over time, and we're going to be limited in the horizons we can operate over. So to recap, task and motion planning is nice because it gives us a precise motion and we can execute it over long horizons, but it's slow and we need to precisely track the world state. Training a policy gives us something that's fast to execute and we can operate from more general observations such as images. The motion is less precise and we can't operate over the same horizons. This is where we come in. We propose a way to combine these two and get the best of both. What we're describing is imitating task and motion planning. And now that isn't as simple as that. The first thing we might hope to do is run our planner a bunch, collect some data, and use that as supervision for a policy. First issue is this is just going to take a long time. We've already said planning is slow. If we want to get enough data for supervision, we're going to be waiting a while. But we've already broken our planning into 2 nodes. So we can distribute it further and run parallel asynchronous copies of each planner so that we can be working on dozens of problems at once. This amplifies our throughput to the point where we can run imitation learning online. We can then use the partially trained policy to further improve planning. We do this by at each step of the plan, first rolling out the policy, and then initializing our trajectory optimizer around that rollout. As the policy improves, the optimizer needs fewer and fewer iterations to converge. This reduces the overall planning time. This has an added benefit as well of helping us to combat trajectory drift in the system. For that, I'm going to refer to our paper. So where does this get us? So here's where we were with PPO before. Now we're training a single neural net to imitate task and motion planning. And notice that we've already seen a qualitative improvement. It is learning how to use the gripper to grab the object, place it on the target. And this reflects a roughly 2-fold increase in the success rate using only 5% of the training compute that we gave to PPO. Okay, this is nice, but there's still a long way to go. We're nowhere near what we were seeing with the task and motion planner before. So the issue right now is that transitions at high-level actions create sharp discontinuities in the control space. So here we see the trajectory as we move from the end of a grasp action into the start of a place. At the end of the grasp, you need a lot of small adjustments to orient your gripper and grab the object without knocking it away. Once you're holding the object, you can then take large steps towards your goal. This means the policy has to learn to map almost holding the object to these small steps versus holding the object to these large ones. These are very similar observations, and it creates this sharp discontinuity that's very difficult for a single neural net to capture. This isn't the only place this happens. We also see what happens if we change the goal. The controls for the grasp action are the same because the object hasn't moved, but the place action has to diverge to this new location. So how might we go about handling this? Well, we build in action-specific subnetworks, things that will account for each type of action we can see without worrying about the transitions. And concretely, what this looks like is we have a hierarchical policy. We have a high-level policy that takes the goal and the observation, and it produces the action to take as well as the associated parameters. We pass these down to a set of low-level policies, one for each action we could encounter. Because these policies only have to worry about one type of action, they don't have to worry about the transitions, they don't have to worry about the discontinuities. We can then use our choice of action to gate the output of these policies and choose our next control. And we run this end-to-end at every time step. So now, instead of training one policy, we bifurcate our data and train 2. And this gets us the rest of the way there on this toy problem. So now we have a success rate of over 99%, and with the same compute we had before. Okay, so we're ready to move on to harder problems. The first thing we're going to do is we're going to have 3 objects now. And the goal is going to be to train from RGB images to place them onto randomly assigned targets. Here we can reach a success rate of 83% after training for 2 hours across 30 workers. If we give the policy access to object positions as well as a LiDAR style sensor, it can place 5 objects 88% of the time with the same amount of compute. Let's move to a more meaningful domain now. Here we see the RoboSuite pick place benchmark. The goal here is to move the 4 objects on the left to corresponding bins on the right. The controls are going to be the 7 robot joint angles as well as the gripper, and the observations are going to be the object positions and orientations as well as joint angles. Our learn policy can place all 4 objects 88% of the time onto their targets after training for 4 hours with 30 workers. This is a bit of an idealized scenario though, because it's a simulation, we don't have a lot of the noise we might encounter in the real world. So we ran some experiments to test how robust the policy actually was. The first thing we did was we corrupted the observations with Gaussian noise. This dropped our success rate down to 64%. We then turned to RoboSuite's built-in dynamics randomization wrapper. So this is going to affect things such as joint stiffness and dampening, the contact solver, as well as corrupting object body offsets. So this is both where you perceive things to be in their orientation, as well as relative orientations of robot links. This dropped our success rate down to 34%. So this is a noticeable drop off, but we would like to highlight that in our review of the literature, we only found prior attempts that focused on solving one object variant of this problem. We're still solving the 4 object variant here and able to do it 34% of the time. Furthermore, because we're training from object positions and orientations, we would expect those body offsets to have an outsized effect on the performance. So if we remove them and only randomize other physical quantities such as contact solver, joint stiffness, inertia, and so forth, our success rises back to 73%. We're now ready to move to our hardest domain. So this is the RoboDesk benchmark. Here we again have a robot with 7 degrees of freedom and a gripper. And the observations are now RGB images and the joint angles. Our goals are going to be 9 very different tasks we're going to want to accomplish. We're going to want to train a single policy that's able to accomplish all of them. We're also going to give it 7 more generalizable motion primitives. So I want to highlight where these motion primitives are not specific to the tasks here. They're general things like move to, grasp, and place. So single policy, general primitives. The 9 tasks here are going to be open slide, lift blocks, stack blocks, so forth. Training from the default camera that you see here and the joint angles, we can reach a success rate of 68% after training for 10 hours across 30 workers. Now, one of the issues here is that the robot easily occludes the objects, so we added a camera onto the end effector. With this in place, we were able to reach a success rate of 79% with the same compute, and we can break that success down across the individual tasks here. Now, I want to highlight again, this is a single policy. We're not training an individual policy for each task. So to summarize, we propose a system for efficiently imitating task and motion planning, use that to train a hierarchical goal condition policy, and then evaluate in a 2D pick place a high dimensional manipulation problem with 4 objects and a multitask problem from RGB images that we can successfully deploy our policies. Thank you, and yeah, see us at the poster session afterwards.
Thank you, Michael. Maybe one quick question.
Hey, so in the beginning, you made a very good case that there in the pick and place task, there's 2 separate phases, right? But then in the later work, you show that you run these at every time step. So I was wondering, if you run these at every time step, isn't there a chance for this to oscillate rapidly between different sub-policies? So have you ever considered trying to predict how long a given sub-policy should run and then just like let it run for a handful of time steps and checking if it's reached this phase transition?
So that's something we actually were worried about. And one of the cool things is we found we didn't need to do that. So there's a lot of similar work out there that has waited for the policy to converge before transitioning. But what we found was we could actually run it end to end and not have any issues. We were a bit surprised by that, actually. It was a kind of cool result.
Cool, thanks.
Okay, I think in the interest of time, we have to move on. So thank you again. And our last speaker in this session is Mohak Bardawi from NVIDIA and University of Washington. And the title of his talk is STORM, an integrated framework for fast joint space model predictive control for reactive manipulation.
Hi, I hope everyone can hear me well. So hello everyone, I'm Mohak Bhardwaj, and today I'll be presenting our paper STORM, an integrated framework for fast joint space MPC for reactive manipulation. This work was done when I was an intern at NVIDIA SRL in 2020 and then continued at the University of Washington. So as robots operate in complex and dynamic real-world scenarios, they need to demonstrate fast reactive behavior and to adapt to changes in the environment, as well as recover from unavoidable errors. However, reactive control of robots poses many novel challenges. For example, this is an instance of the Franca arm in our lab at UW performing a ball balancing task where the aim is to center the ball on the tray. This is a complex control problem where the robot must ensure smooth and safe motions under perception errors and modeling errors, such as the frictional and inertial properties of the ball and the tray, while also coordinating large degrees of freedom and optimizing costs in both the joint and the task space. And there are a range of motion generation techniques that could be employed for such a reactive control problem, and each of them make different trade-offs. To understand this, let us consider a simple point robot shown in red, trying to find a collision-free path to a goal in green, and a barrier-like obstacle is sensed in the middle. A class of approaches based on single-step optimization would try to solve this by following the gradient of a cost function that combines multiple objectives, like minimizing the distance to the goal while staying away from obstacles. Now, while these approaches are highly reactive and can be used over 500 hertz, they can sometimes get stuck in local minima due to conflicting gradients from different objectives and often require task-specific heuristics to succeed. On the other end of the spectrum are approaches based on full horizon planning that would solve the same problem by constructing a graph of robot configurations and then searching it for a near optimal path. While this exhaustive search can make these algorithms computationally expensive, they do provide some completeness guarantees at the expense of reactivity. And oftentimes in real-world applications, these approaches are combined with the higher level planner used to provide waypoints to the lower level controller. And this works really well for goal-directed navigation tasks. However, consider a scenario like this. This is an example of our framework applied to a task where the robot needs to react very fast to dynamically moving obstacles while also looking ahead to avoid getting stuck in local minima. All the while coordinating 7 degrees of freedom with constraints such as joint limits and self-collision avoidance. Now, this is a very hard problem for a traditional planning and control pipeline. However, there do exist a broad class of algorithms under the umbrella of model predictive control that offer a good trade-off of computational complexity, reactivity, and horizon within a single optimization framework. So briefly, MPC interleaves planning and execution by using a simulator to optimize a local policy over a finite horizon at every time step, and then executing an action from the policy. And this strategy allows MPC to potentially escape local minima if your horizon is long enough, while also being able to react to changes in the environment. And within MPC, there is a subclass of sampling-based methods that leverage Monte Carlo sampling to optimize this local policy. And in recent times, these methods have shown great performance in real-world dynamic tasks, such as off-road driving, dexterous manipulation, and model-based RL, due to the fact that they can use non-differentiable cost and dynamics and are easy to integrate with learned functions. And great progress has been made in improving individual components of the MPC stack, such as learning better dynamics models, combining it with reinforcement learning, as well as using expressive policy classes. So a natural question arises, could we simply apply state-of-the-art sampling-based MPC out of the box for reactive manipulation? Well, we argue that while these individual components provide many benefits, integrating them together in practice poses several system-level challenges. To understand this, let us take a closer look at the overall sampling-based MPC stack. So at every time step, sampling-based techniques proceed by first sampling actions from a policy. For example, in the case of manipulators, these could be joint accelerations or velocities, and the policy could be an open loop Gaussian over them. This is then followed by rolling out our dynamics model or simulator with these actions. So in the above example, we visualize resulting end effector trajectories from these rollouts. And then these trajectories are scored according to a cost function. So here the good rollouts are in green and the bad ones that intersect with the obstacle are in red. Then we update the policy based on a sample-based gradient of the cost function to increase the likelihood of the good rollouts and decrease the bad ones. This is done for a fixed number of iterations or till convergence, and then an action from the policy is executed on the robot, and then the process repeats from the resulting next state till the robot eventually reaches the goal. So what makes reactive manipulation an especially hard domain for sampling-based MPC? Well, in practice, when we deploy these systems, several bottlenecks appear in each of the subsystems, both in terms of computational complexity and optimization. For example, random trajectory sampling can cause the motions to be jerky and not directly executable on manipulators. And naive pseudorandom sampling often leads to poor coverage of the action space. And since manipulators have large degrees of freedom, long horizon rollouts can be expensive. So here a trade-off between speed and accuracy becomes absolutely critical. And certain cost terms, such as self and environment collision checking, can be a computational bottleneck, especially for complex tasks requiring large horizons and large number of trajectory samples, which can amount to thousands of queries. And also the algorithm here needs to optimize for multiple and often conflicting objectives. And maintaining computational efficiency often forces us to use very simple policy updates. Finally, in order to react to dynamically changing environments, we need to run this entire pipeline at very high speeds, often 100 hertz or more, which makes computational speed absolutely critical. So in this work, we take a step back and explore the question of what are efficient trade-offs and design choices that allow us to leverage existing tools and scale sampling-based MPC methods to real-world reactive manipulation. And we present a first step towards answering this question in the form of stochastic tensor optimization for robot motion, or STORM, which is a GPU-accelerated MPC framework with core algorithms for reactive real-world robots. We integrate key systems-level contributions to different subcomponents that enable us to obtain desired behaviors. These include using smooth quasi-random sampling to guarantee smooth action trajectories, a completely tensorized forward model, and FK, novel cost functions that encourage desired behaviors and constraints while being computationally efficient, and this includes a fast GPU-based collision checker. Finally, we use MPPI augmented with covariance adaptation as our control backend. The entire system is designed to be modular so that individual subsystems can be improved independently, and we run the entire stack on GPU to achieve an over 100 hertz control rate. I will now highlight a subset of our contributions, and detailed explanations of all subcomponents can be found in the paper, and I'm happy to discuss that during the poster session later on. Okay, so first we incorporate two different ways of doing collision checking, which do not rely on gradients. So the first is using shape primitives for the world model that assumes that the obstacles are of known shapes, such as cuboids or spheres. And the second is directly from a partial environment point cloud using scene collision net, which is a learned discrete classifier that outputs the probability of collision between the environment and the robot point clouds. Now, this is in contrast to SDFs, traditionally used by gradient-based approaches, which are hard to update fast in dynamically changing environments. And both these methods can run on the GPUs to enable fast collision checking with a large number of query points. Rolling out the dynamics is usually another computational bottleneck. So here we trade off accuracy for speed by using a completely tensorized kinematic model. Here, sample joint accelerations are integrated via semi-implicit Euler to compute joint velocities and positions across the horizon and trajectory samples in a completely tensorized manner. Note that this model is batched not just across the trajectory samples, but also the horizon as well. We also use a variable time steps to, again, trade off integration accuracy versus exploration horizon. The resulting joint states are then used to compute FK for different points on the robot body and end effector in a batched manner. And this allows for very fast query rates of 150 to 225 hertz, even for large number of configurations. However, we see that the GPU only provides about 5x speed up. But this difference is way more pronounced when we start incorporating collision checking as things slow down on the CPU. So here GPU acceleration actually gives us a 50 to 100 times speed up, depending on the number of queries, which is critical for complex tasks where a large number of rollouts are generally needed. And empirically, this entire model provides sufficient accuracy for reactive manipulation tasks, as we will see later. Another often overlooked aspect in practical sampling-based MPC implementations is the method used for sampling controls from the Gaussian policy. So pseudo-random sequences typically used in Monte Carlo integration exhibit this undesirable clustering of sample points, which results in empty regions. On the other hand, low discrepancy quasi-random sequences attempt to alleviate this problem by defining deterministic samplers that correlate different points to avoid groupings. In our implementation, we utilize a particular strategy called Halton sequences that have been reported to improve rate of convergence in higher dimensional problems. So we first tested STORM on a suite of tasks commonly expected of manipulators, and I will briefly go over some of the results here. The first one is an OSC kind of reaching task where the end effector must reach Cartesian poses with large orientation changes. Next, we populate the workspace with obstacles and have a robot track the end effector goals input from perception. Here, the robot tracks a red ball held by the human while avoiding collisions with obstacles. We also test on a much harder task where the robot must maintain an end effector orientation while reaching different goal positions. During these motions, the robot also avoids self-collisions and respects joint limit constraints, which makes it a very hard optimization problem. And these tasks demonstrate the storm can indeed enable robots to demonstrate a diverse repertoire of reactive behaviors within a single optimization framework. We also test whether high frequency control can overcome errors due to inaccurate dynamics and perception by using another reactive task where a Franca robot arm must center a ball on a tray grasped by the gripper. Here the ball is detected using a noisy vision-based perception system, and a simple model of a point sliding under acceleration due to gravity is used to model the motion of the ball. In this experiment, we did not perform any system identification or model friction explicitly. And there are also subtle errors due to the fact that the tray is not rigidly attached to the end effector, which are not modeled. However, we see here that our high frequency joint space controller is able to correct for these errors and center the ball with centimeter level accuracy over many trials on the real robot. In summary, we have a few key takeaways from this work. Reactive control of real-world manipulators requires reasoning over long horizons and optimizing in multiple spaces, which makes it a hard control problem. Sampling-based MPC is an effective tool for solving this problem, but scaling to reactive manipulation requires overcoming several system-level bottlenecks. And our proposed framework STORM provides a single flexible framework that enables diverse reactive behaviors by leveraging key insights for each subcomponent as well as GPU acceleration. We have open sourced the code for STORM on GitHub, and it's already being used by other researchers, which is exciting. For example, it's being used for human-robot interaction tasks, that's shown in the bottom right, for like avoiding collisions with humans and human-to-robot handovers. Please come over to our postal later if you wish to discuss more details, and also check out our paper. Thank you, and I'll be happy to take any questions now.
Thank you. Have any questions in the audience? Yes, one here.
So you mentioned the drawback of classical planning and optimization-based approach. Do you have some results on comparing to this kind of method?
Yeah, so we have some comparisons on pose-reaching tasks, but individually with like operational space control and like just like full horizon planning with something like OMPL. For a lot of these tasks, it's like really hard to run the planning and like planning plus control pipeline. So we don't really have many empirical comparisons on something like ball balancing or some like the human robot stuff.
Okay, thanks.
Okay, there's one question from the chat.
Yeah, so there's so the time complexity for halt and sequence points lies in O log n, right? So is there potential for that to become a bottleneck if the robot is running for a longer period?
Yeah, so in our implementations, we usually just sample the halt and sequence noise initially at the first time step. And then since we're doing covariance adaptation, we use that to sort of transform those sequences. So we don't have to do the sampling of the halt and sequences at every time step.
Thank you.
Okay.
I would have another question if there's no question in the audience, just real quick. So on the ball on a plane task, right, that is still there in the background, you can see like some type of foil on the plane, right? Is that to reduce friction? So it's basically friction causing troubles for the method.
Yeah, it's actually, well, sometimes like less friction can cause trouble. So that's like to like increase a little bit of friction.
Okay.
Thanks, excellent. One more question from here.
For your sample-based optimization, you use, instead of just the uncorrelated Gaussian noise, you have also some kind of correlated noise. Did you compare to colored noise that we have published last year here on the conference?
So in our experiments, we compared two different ways of inducing some sort of correlated noise. So one is once after you sample your actions, you can use some sort of like a comb filter on top of it, which is used in like a lot of implementations. And versus we also have like another method where we actually fit B-splines to sampled actions and use that for integration. We didn't like compare to the colored noise from the paper that you mentioned last year, but of these two implementations, we found that actually using the B-splines results in like much smoother acceleration trajectories, which allows the robot to ramp up its velocity like much more smoothly versus using like something naive like a comb filter.
Okay, I think this concludes the session. Thank you very much again. And I'm going to hand over to Alexandra for some announcements.
Hello. So just a little bit of the housekeeping things. We are kind of going to move now to break/poster session. Poster session starts in 5 minutes, so you might want to go. So we have poster session, lunch, and then another poster session after lunch, and we're back here at 2:20 for sponsor talk from Tingnan from Google. And then we have 2:30 starts a Blue Sky session, and later on in the afternoon we have a tutorial on social reinforcement learning and a closing ceremony where the best paper awards are going to be announced. So thank you. We'll see you a bit.
You're the life of the party, I guess. You crave all that attention. Where is everyone when it all ends? Always seems to be the question. I know you like to show it off. It's okay if it's fun, but it's not. Cause you talk about yourself too much. And people go away, they're not insane. As you think, oh no, I walk away, but I ain't losing. Oh no, I'm tired of people trying to fool me. Cause I learned the price of
colors all around, but I don't see anything but blue. Get lost in the sound, go back to the start. Let's go out of the dark. Let's go out of the dark. Into the light now. Get lost in the sound, go back to the start. Let's go out of the dark. Let's go out of the dark. Into the light now.
I wish I could lure the value, these voices inside my head. Like every time I try to face these demons, I get consumed instead. You think by now I'd learned somehow, gotten used to being underwater. But when you've been running for so long, you start to wonder why you even bother. You gotta stand your ground, 'cause only you can fight for what you deserve. Oh, don't walk away from me. I'm lost and you'll be found, 'cause only you decide what you want. Oh, don't walk away from me. Oh, don't walk away from me. Just acting against you, but it's time for you to make your move. 30 seconds in, you hit rock bottom. Now you got nothing left to lose. You think by now I'd learn somehow. You certainly shouldn't judge yourself. This is your moment. Can you see it? Oh, now you gotta stand your ground. So you can fight for what you deserve. Oh, don't walk away from me. Oh, now, are you lost or will you be found? Only you decide where you are. Oh, don't walk away from me. Oh, don't walk away from me. What you hiding from? Oh, don't walk away from me. What's your reasons? Why you leaving? Show me that I'm wrong. Oh, don't walk away. stand your ground. You gotta stand your ground. Yeah, don't walk away from me. Don't walk away. Don't walk away from me. Don't walk away from me.
Was thinking of going till I turn around, there's you. I've been looking for you, gotta know what you're going through. Baby, I'm fading now, baby, I'll take you out. Know that you see me, I think you like me. Baby, I'm trying to go, baby, you let me know. If you trying to leave, just follow me. Just follow me. Hey, I'm hoping you can stay with me all the way. Ah, I know it's fucking late, but you can make my day. Oh, first you gotta taste my high, then you gotta take the ride. I feel like I'm in space tonight. Baby, can you fade the light? I. Hey, I'm hoping you can stay with me all the way. Ah, I know it's fucking late, but you can make my day. Oh, first you gotta taste my high, then you gotta take the ride. I feel like I'm in space tonight. Baby, can you fade the light? I.
Fly away to the sky, shining bright like a shine very high like the stars, dancing through with the clouds. And everything we search a meaning, every cloud has silver lining. As long as you are still breathing, don't waste your time, keep fighting. And even if you drift and fall, look down like that still stand tall. Believe yourself and keep on running. Don't look back, stay dreaming. A meaning, every part has silver lining. As long as you are still breathing, don't waste your time, keep fighting. And even if you drift and fall, look down, look and still stand tall. Believe yourself and keep on running.
to the light. I wanna know you. 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 I wanna know who you really are, what you dream about at night. I wanna know who you really are, baby, come into the light. I wanna know you. 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 I was trying to run from my destiny. Truth is, it's hard to want what you need. Stars align without asking first. We're everything I wanted, a blessing and a curse. First time I didn't realize, second time you fed me lies. I tried to run, but I didn't get far. I was trying to run. I was trying to run from my destiny. You felt so good. Guess you scared me. Stars align without asking first. We're everything I wanted, a blessing and a curse. Now I'm here. It's as if everything has gone back to the start. Play me like a work of art. First time I didn't realize, second time you fed me lies. I tried to run, but I didn't get far. I was trying to
lost in a daze. Why do I feel like I have been here before? Find me a way, away from this place. I can't escape anymore. And I'm losing sight, unsure where I'll land. When I close my eyes, brings back who I am. Bring back who I am. Bring back who I am. I'm counting the days I have been walking, can't seem to find any door. I can't run away, stuck to the surface, can't seem to lose the floor. And I'm losing sight, unsure where I'll land. When I close my eyes, brings back who I am. Bring back who I am. Bring back who I am.
You told me that we should go our separate ways, but now you're back, begging for a place to stay. Oh, it's not right. I wanna kiss you when we fight, kiss you when we fight, kiss you when we fight. So hit the road, baby. I don't wanna see the mess you made. I don't wanna hear about your mistakes. I just wanna live my life without you. You told me that we should go our separate ways, but now you're back, begging for a place to stay. Oh, it's not right. I wanna kiss you when we fight, kiss you when we fight, kiss you when we fight. So hit the road, baby. I don't wanna see the mess you made. I don't wanna hear about your mistakes. I just wanna live my life without you.
And I know if I come any closer, I don't need to tell you that it's over. And I know if I come any closer, this is gonna be too much for us to bear. I don't need to tell you that it's over. You can probably see it in the way I stare. And I know if I come any closer, this is gonna be too much for us to bear. I don't need to tell you that it's over. You can probably see it in the way I stare. And I know if I come any closer, this is gonna be too much for us to bear. I'm just calling to say. It's gonna be too much for us to bear. I don't need to tell you that it's over. You can barely see it in the way I stare. And I know if I come any closer, this is gonna be too much for us to bear. I don't need to tell you that it's over. You can barely see it in the way I stare. And I know if I come any closer, this is gonna be too much for us to bear. I'm just calling to say. Close your eyes, only got one night. Just put your trust in me. Give me everything. I need your love tonight. So baby, please don't fight it. Put your trust in me. I'll give you everything. So hold on to me. Never let me go. Right here in your arms is where I wanna be. So hold on to me.
close your eyes. Only got one night, just put your trust in me. Give me everything, I need your love tonight. So baby, please don't fight it. Put your trust in me, I'll give you everything. So hold on to me. Never let me go. Right here in your arms is where I wanna be. So hold on to me. So hold on to me. Never let me go. Right here in your arms is where I wanna be. Where I wanna be. So hold on to me. Do you even know what you do to me? Do you even feel the way you said you did? Was that all lie? Did I fall for your lie? How is this so easy for you? How are you moving on so fine? I'm still stuck here wondering, did I ever cross the line? Love so thin, like cold pain. You can just scratch it off. I was a band-aid for your heart, and then you just tore me off. Tore me off your heart. Tore me off your heart. Tore me off your heart. You're so cold, it gets so old. You set me up for the fall, and I couldn't hold on. Why did I try for so long? Why did you keep my mind tight for so long? You never knew me too well, you never asked how I was. How come I always felt alone when I was with you? Were you even there? It hurts me more just knowing I was a band-aid. It hurts me more now that it doesn't hurt you. Love so thin, like cold pain. You can just scratch it off. I was a band-aid for your heart, and then you just tore me off. Tore me off your heart. Love so thin, like cold pain. You can just scratch it off. I was a band-aid for your heart, and then you just tore me off. Tore me off your heart. I'm lost, trying to find who's there for me, but I can't go anymore. I tried to bring my ego down, but in the end, there's no remorse. Don't be nothing at all.
water. You are the air I need to breathe. Reach to the surface from the floor. I'm still try to see beyond my dreams. As I get closer, you go far. Don't remind me of these broken promises to fall. Don't remind me of these broken promises and nothing at all. Can't stop now, but I don't have self-control. Keep wondering how I miss the sights. Oh, is that wrong to want a peace of mind? I keep asking myself how I can get you to stay. It's breaking my heart to see you again afraid. See you, babe. I got three lots to reasoning. One day at a time. Still no bottom line. I still feel your touch like ecstasy. Oh, it hits me almost like a distant dream. I'll be going down. You don't turn around. I'll be going down. I keep asking myself how I can get you to stay. It's breaking my heart to see you again afraid. See you, babe. Oh, babe, are you looking away? Oh, see you, babe. Is there a saving grace? 'Cause it's getting harder and harder to breathe. My tears release the pain, so I can make it out in one piece. Let's face the truth, our world has fallen through. My heart is yours, watch it all burn in the fire. It's over now, watch it all burn in the fire. God, it hurts the most watching you walking away. We used to be so close, but I can't bear the pain anymore. Let's face the truth, the world has fallen through. My heart is yours, watch it all burn in the fire. It's over now, watch it all burn in the watch it all burn in the fire. Watch it all burn in the fire. shot. Just stay my hand. Take me to your special place, the one where you can be yourself. You don't need to be scared of what the future will be. Just take me, baby, we will be what you don't know. You will see what I don't show. I don't want to hide from our love. I don't want to hide anymore. Oh, anymore from our love. Take me everywhere. You could say, you could set me free. You could fly with me. You could say, you could set me free. You could fly with me. I don't want to hide from our love. I don't want to hide anymore. Oh, anymore from our love. Take me everywhere. Take me to your special place, the one where you can be yourself anywhere. I don't care as long as you are by my side. Anywhere, I don't care as long as we're staying together. Oh, as long as we're staying together. You can fly with me.
Left behind, and I've lost everything. Forever living in the dark. I feel so alive. Still remembering what I want, but it ends with you. Candlelight has gone out. Some will win and some will lose. Nothing much else to say. Thought I was searching for something. Door has closed, not a sound. Take a look as I am now. Still I smile when don't speak. Will you please slow down? Slow down. Slow down. Slow Unreal intertwined, and you're not listening. It is your choice to make a little mockery, it won't do. Further down the line, still surrendering, trying harder to forgive you. Candlelight has gone out. Some will win and some will lose. Nothing much else to Slow down, slow down, slow down.
You just have to try harder than you fight. You might be lost like sunshine in the night. You know what they say, life's about to end. If you wanna be someone, you don't have to wait. You just have to change. What if I were you? Would it be easier for me to be heard and to be seen? What am I supposed to do? Is it all now up to you? I am not that strong. I don't even know where I belong. You just have to try harder than you fight. You might be lost like sunshine in the night. You know what they say, life's about to end. If you wanna be someone, you don't have to wait. You just have to try harder than you fight. You might be lost like sunshine in the night. You know what they say, life's about to end. If you wanna be someone, you don't have to wait.
There are times when I doubt the path I'm on right now. Then I think all about the time I spent, the sacrificing of vows. I know these dreams are never fading away. Oh no, I'll reach the galaxy far away, and the road is
dreams are never fading away. Oh no, you know what I mean? Won't fade away. Oh no, these dreams won't fade away. No, won't fade away. Oh, I am a dreamer today. Too long I spent here to give up my dreams there. So easy to lose, yeah. It's so hard to find, but never give up, 'cause I know I'll be fine. These dreams are never fading away. Oh no, I'll reach the galaxy far away, and the road is long, and it will be so tough, but no, these dreams are never fading away. Oh no, you know what I mean? Won't fade away. Oh no, these dreams won't fade away. No, won't fade away. Oh, I am a dreamer too. Don't give up, give up, give up, 'cause you are better than that. You'll climb to the mountaintop and you will want what you have. There is no returning to normal again, 'cause you have made your dreams today. Just think about that. Just think about that. I am a dreamer today. You know what I mean? Won't fade away. Oh no, these dreams won't fade away. No, I am a dreamer today. Won't fade away. Oh no, these dreams won't fade away.
Driven in colors I never dreamed. Oh yeah. I let you in deeper than I let anyone else before. Filling up with my broken pieces, took them all and made them yours. Didn't know what my heartbeat needed. Skipping out, no, I can't keep score. When I lose my breath, boy, you got me breathing. Oh, every little thing you do, every time you hold me, take me higher, higher. Every little thing you do, every time you hold me, take me higher, higher. Oh. Magic. No, I'm never letting go. Now that I have it with you. When you kiss me, it's like the stars fall out the sky onto my heart to cover up what I don't wanna show. I let you in deeper than I let anyone else before. Filling up with my broken pieces, took them all and made them yours. Didn't know what my heartbeat needed. Skipping out, no, I can't keep score. When I lose my breath, boy, you got me breathing. Oh, every little thing you do, every time you hold me, take me higher, higher. Every little thing you do, every time you hold me, take me higher, higher. Ooh, you take me higher, you take me higher, baby, you take me higher, you take me higher, baby, you take me higher, you take me higher, baby, you take me higher, yeah, you take me higher, baby. I'm reaching out for the stars tonight, not looking back down, 'cause it's getting dark, and I don't wanna fight my own. I don't think that I know where I'm going anymore, but I know I'm not lost, 'cause I'm not alone. If I don't find my way, I know I'll never be afraid of the dark again. So take my hand and we'll touch the sky. We'll keep fighting through the night, even if tomorrow never comes. I'm leaping out of the dark tonight, making sure I never look back. Should be scared, but I'll follow your light home. We can fly through the night, chasing our nightmares away. No place I would be here with me. I don't think that I know where I'm going anymore, but I know I'm not alone.
So take my hand and we'll touch the sky. We'll keep fighting through the night, even if tomorrow never comes.
Like a ghost out of sight, woke me from dreaming, pulling the scene away, calling me into the night, slowly revealing all that I've kept at bay. Just as a vision takes hold, hinting at flickering gold, shines a light that's here to stay. Somewhere hidden deep in the unseen, hear the voice that is calling, past the doubt and the confusion. Would you leave for a feeling? No, not sure if it's only just a beautiful illusion. Watch it like out of a movie, showing the way that it could be. Moments written in the stars. So all the ways we've been holding onto the place where we're standing, stuck in the mold of who we are. Just as a vision takes hold, every hate yell is striking gold, 'cause we know who we are. Somewhere hidden deep in the unseen, hear the voice that is calling, past the doubt and the confusion. Would you leave for a feeling? You're not sure if it's only just a beautiful illusion. Like a ghost out of sight, woke me from dreaming, pulling the scene away.
I left the lights in my heart on, if you ever wanted to come home. It's like I'm living in a sad song, I don't wanna face it on my own. So forgive me, baby, what do I say to make a difference? I'm going crazy, it's the nightmare I'm living in. I'm homesick, trying to think of something that we miss. Deep inside I know if we let it all go, we could still be friends. We could still be friends. We could still be friends.
you could stop this.
I should forget about you the same way
You did about me. Where's the solution? I need to know. I need to know. I need to know. Where's the solution? I need to know. I need to know. I need to know.
I'm hurt. What can I say? Truth be told, I know you're okay. Nothing can tear you apart. My mad heart,
You did about me. Where's the solution? I need to know. I need to know. I need to know. Where's the solution? I need to know. I need to know. I need to know.
Bittersweet and I'm walking slow. Sensitive, feel the afterglow. Looking for things that I can't control. Fear from my past, cause it always shows. Do I wanna try? Can I let it go? Running from the past, wanting to be sure. Chaos in my mind, constant deja vu. But every time, it comes back to you. Whoa, I'm still falling. Whoa, but it tastes bittersweet. Whoa, I keep on falling. Whoa, I like the taste of it. I'm still falling. Whoa, but it tastes bittersweet. Whoa, I keep on falling. Whoa, I like the taste of it. Blacking out, afraid just fading day by day. I'm reaching out for someone who can take away the pain I feel, the things I haven't done at all. I've lost my way, but how I felt I can't recall. Do I wanna try? Can I let it go? Running from the past, wanting to be sure. Chaos in my mind, constant deja vu. But every time, it comes back to you. Whoa, I'm still falling. Whoa, but it tastes bittersweet. Whoa, I keep on falling. Whoa,
teenage crime. You picked me up and get at 69 every night we snuck out. So I've been waiting by your house every night we snuck out. Till the sun will rise for the last time. Stay by your side. For you, I stay by your side. Would you stay by my side? For you, I stay by your side. Leave you, stay by my side. It's now or never. Bonnie and Clyde create a story for a different time, for the memories in which we started. Night, stay by your side. For you, I stay by your side. Would you stay by my side? For you, I stay by your side. should probably start to walk away. I'm hoping that you stop and make me have to stay. Cause I'm floating in your orbit. Yeah, I'm stuck in your space. Just my luck, push me away. You understand? There's nothing left to say. Pull me back, take my hand, call my name. You understand? Don't wanna stay. 'Cause I don't wanna walk away. I don't wanna sit here while you fall apart. Even though you told me to get back your heart, I still spin inside your orbit. Yeah. You said that I should probably start to walk away. I'm hoping that you stop and make me have to stay. Cause I'm floating in your orbit. Yeah, I'm stuck in your space. Just my luck, push me away. You understand? There's nothing left to say. Pull me back, take my hand, call my name. You understand? Don't wanna stay. 'Cause I don't wanna walk away.
Wake up to the sound of birds, they're singing out of tune. We're leaving all these lines up in the sky across the blue. The hourglass is slowly running out of things to say. Create a new distraction, only fills it up halfway. The alien grows, and everything goes. But look what it costs. Now humanity is lost. Living was defenseless. Society is restless. Fighting is together. Keep living under pressure. Feel the tension rise as we go running from the smoke. Living on the line until the road is out of hope. I look up to the sky to find myself a new UFO. Before it catches up with me and turns it in a show, the alien grows and everything goes. But look what it costs. Now humanity is lost. Living was defenseless. Society is restless. Fighting is together. Keep living under pressure. I should be more honest with myself. 'Cause I'm no good at knowing when I need help. And I'm getting tired of pushing away everybody the second I let them get close. It's like I'm afraid of a ghost I can't see. And I try to fight it, but all the damage is done. It's too late to hold in the flood. Maybe it runs in my blood.
try no more, try no more, try no more. If it's gonna break my heart, rip me apart or start a war. Is it really all my fault if I don't feel myself at all? Maybe it's not our love, maybe it's just in my blood. I'm doing my best not to let down my guard, 'cause everything seems dangerous when you're in the dark. And I'm getting tired of pushing away everybody the second I let them get close. It's like I'm afraid of a ghost I can't see. And I try to fight it, but all the damage is done. It's too late to hold in the flood. Maybe it runs in my blood. I don't wanna try no more, try no more, try no more. If it's gonna break my heart, rip me apart or start a war. Is it really all my fault if I don't feel myself at all? Maybe it's not who I love, but maybe it's just a mind. In my blood, in my blood. Maybe I just need my space. Maybe one day I can change. Maybe it's not all love. Maybe it's just in my blood. Maybe it's just in my blood. Closer, we can do it over. Remember when I told you we'd regret it when we're older? Come a little closer to me. Give me some of what we used to be. Come a little closer. We can do it over. Did you miss me? Like I missed you. Kick myself 'cause I know that I shouldn't hit you up, but you know that I couldn't stay away forever. Stay away forever. Come a little closer. We can do it over. Remember when I told you we'd regret it when we're older?
Say you found love, but I'm just staging. Oh, the fire's low, I'm broken inside. I'm still alive, I'm still alive. But you know that we might still get burned. Raging. The fire is raging. Wanna run again. With me out and let me breathe again. I'm broken inside, but I'm still alive. Yeah, I'm still alive. The fire is It's a carousel of words running around, going nowhere. How do you survive while I'm burning alive? Though the flame is there, I'm broken inside. I'm still alive. I'm still alive. But we cannot burn without nowhere. Raging. The fire is raging. Wanna run again. With me out and let me breathe again. I'm broken inside, but I'm still alive. Yeah, I'm still alive. The fire is Told myself that I'd be fine, no matter what we said last night. Trying to keep it all in line when nothing's really going right. What if I believe I can always find a way? Not afraid to be real, it's all here. What if I don't leave when I just wanna hide away? Take control of the wheel, I'm right here. Watch me fall and rise again, cold-blooded till the end. As I stand unaffected, I'm ready to rage. Feel it rushing through my veins, the force you can't command. Staying calm and collected, I am unafraid. I am unafraid. Staying calm and collected, I am unafraid. Never felt like looking back, 'cause I was in over my head. Every time I'm losing track, I choose a different road instead. What if I believe I can always find a way? Not afraid to be real, it's all here. What if I don't leave when I just wanna hide away? Take control of the wheel,
you so bad if you're there. Hold me tight and love me, baby. I wanna make you feel confused. What do you think when I shake you, baby? I wanna lead you, I wanna choose. What do you think when I shake you, baby? I wanna make you feel confused. What do you think when I shake you, baby? I wanna lead you, I wanna choose. What do you think when I shake you, baby? Something must be wrong with my brain. A fire side I've never overcame. Oh, can you feel it deep into your veins? Hold me tight and love me, baby. I wanna make you feel confused. What do you think when I shake you, baby? I wanna lead you, I wanna choose. What do you think when I shake you, baby? Something must be wrong with my brain. Like a poison I've never tried. Having you so bad if you're there. Hold me tight and love me, baby. I wanna make you feel confused. What do you think when I shake you, baby? I wanna lead you, I wanna choose. What do you think when I shake you, baby?
you'll find me. I'm not afraid of the coldest rain. Keeps me awake for the golden days. I'm not afraid, I don't feel the pain. Lead me to the golden gate. I fall right back into memories. Forgot about the past and slowly drift away. And it never really is what it seems. Feels like I'm drowning in despair, knowing that you won't be there. I'm not afraid of the coldest rain. Gives me away for the golden days. I'm not afraid, I don't feel the pain. Lead me to the golden gate. I'm not afraid of the coldest rain. Gives me away for the golden days. I'm not afraid, I don't feel the pain. Lead me to the golden gate. I'm not afraid of the coldest rain. Gives me away for the golden days. I'm not afraid, I don't feel the pain. Lead me to the golden Eyes wide, tongue-tied, midnight. You can say all that you want, but you and I were meant for this. You know, sometimes we hide behind this illusion that we're done. Oh, please see that you're wrong in this. I don't fall in love cause I'm here tonight. I don't wanna say it, but it just feels right. I feel just about the time. I wanna stay at the back of your mind. We've seen it all before, and don't get me wrong, but I'm done with these games. And I'll hold on to faith. You and I are stuck on this. I can't seem to let this go. It's not too late. Just show little faith this time. I still feel like you lied about the way that you can't love. We should have never let this go. No, we were the catch on the summer nights. Kids in the street that got it right. Every time I felt to let go. Every time I felt to let go. We've seen it all before, and don't get me wrong, but I'm done with these games. But I'll hold on to faith. You and I are stuck on this. I left to go and let it breathe. But I'll be waiting here, you see. I don't know if everything will be alright. Sometimes you gotta let go, 'cause I gotta let you go. Hold me close till I get up. Time is barely on our side. I don't wanna waste what's left. The storms we chase are leading us, and love is all we'll ever trust. Yeah, no, I don't wanna waste what's left. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. Finding life along the way, melodies we haven't played. No, I don't want no rest. Echoing around these walls, fighting to create a song. I don't wanna miss a beat. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And we'll grow in number, fueled by them to see the horizon, turn us to thousands. And on we'll go, through the wastelands, through the highways, till my shadow turns to sun rays. And on we'll go, through the wastelands, through the highways, and on we'll go. Oh yeah. Are we talking about losing control? I'm gonna show you how we lose control, baby. Watch this. Look, Marty Mark. Watch the way I start up. I've been going hard, but I can go way harder. Every beat I'm on, yeah, you know that I slaughter. And I'm always looking gorgeous, chilling with somebody's daughter. Yeah, she loving me. Say she love the way my chain sitting comfortably. And of course it says my name if you wanna wait. To let you know who's finna blow. Always win and check the scope. I'm only losing control. Oh, I like losing control. Always win and check the scope. I'm only losing control. Oh.
Write on another page and you feel like a world away. And when I go, I'll leave a light on. It breaks my heart, cause all I want is just to stay. Calling out to you in the night, knowing that it still means nothing. Will we be okay? Worlds away. I know that it's almost over, and everyone is waiting at the edge for me. So tell me why I feel no closer than before, with no clue what was yet to be. Calling out to you in the night, knowing that it still means nothing. Will we be okay? Worlds away.
star will never see. It was cold with our hands in pockets. Bitter snow in late November. If it was over, I never saw it. Where were you when it was empty? And where are you now? And around and around and around we go. But we can't fight, no we can't fight it. And away and away and away we go. No we can't stop, we'll never stop it. Never stop it. Never stop it. I'm a ghost moving through these walls, scared to see my own reflection. I feel the words tumble out my mouth. Am I better off without you? Better without we can't fight, no we can't fight it. Away and away and away we go. No we can't stop, we'll never stop it. Never I don't know what I came here for. I don't know why I came here at all. I've been taking notes, cause I don't know what to say. I've tried to let you go, but at night I stay awake. And I've been trying not to lose my mind, but I can't stop thinking about you all the time. If I called you back, would you put me first? If I told you
Issues that we have, let's get through it. We were so good, let's resume it. Maybe on the night we can prove it. We can prove it. Maybe we can do it. Issues that we have, let's get through it. We were so good, let's resume it. Maybe on the night we can prove it. Something's weighing heavy. Created too much pressure, this ain't healthy. We were all good, love was plenty. Now look at the cards, never stop me. Never stop me. Maybe we can do it. Issues that we have, let's get through it. We were so good, let's resume it. Maybe on the night we can prove it. We can prove it. We were so good, let's resume it. Maybe on the night we can prove it. Drag it out again, I'll show you there is more to me. You know what I want, I'll spell it out if I need to. Afraid of the fall, I'll spell it out if I need to. I know what I want. Do won't let you hold me back. Won't let you hold me back. Wake up, we're through, not fading out again. Faith in what is new. Blinded by guilt, you were the one to blame. Don't need you, forgot you. You know what I want, I'll spell it out if I need to. I know what I want. Won't let you hold me back. Won't let you hold me back. I've been getting out of bed these past few days. Think it's fair to be proud about it. I've quit ordering from all those fast food chains. I'm feeling better, there's no doubt about it. And my days are brighter, my shoulders are so much lighter. Just for a moment there, I thought that there was nothing more to life. I thought about it, wrote a couple songs about it. Just for a moment there, I lost myself. Mind if I be real for a minute? It's almost like everything I feel had a limit. It now gone past. Finding reasons to smile and to laugh, and whenever it's a bad day, music is my band-aid. Here the other day, I turned off all the lights. Spent an hour with my memories, and then I realized it's not all black and white. Like I was colorblind, but mentally, yeah. Now my days are brighter, just no longer feeling tighter. Don't wear my PJs every day, 'cause I would rather be outside. I thought about it, wrote a couple songs about it. Just for a moment there, I lost myself.
I can feel you underneath my skin, and you keep digging in. I know I can reach you, but I feel like I need you. Like a poison flowing through my veins, but I can't feel the pain. It's me that I'm losing in your perfect illusion. Oh, 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 wish I could hate you, but I can't blame you. Oh, 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 wish I could leave you. I know I need you. But you, but I'm, but, but I'm, but you, but I'm, but I believed you. Everything you said, like demons in my head. I keep my composure while you're pulling me closer. Trying to leave you is pulling me apart. The pieces of my heart you keep taking from me, till there's nothing left of me. Oh, 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 wish I could hate you, but I can't blame you. Oh, 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 wish I could leave you. I know I need you. I can't, but you, but I'm, but I need you. But you, but I'm, but I'm,
Keep a secret, listen close, touch me like I don't do what I'm told. You got a halo on your head, but that won't stop me. I'll make you sing again and again. Can't help myself, bad influence. Get out what's in my head. Keep you round, oh, keep you around. On your knees, won't you give me that? Give me that, give me that sweet release. And you take it from, take it from, take it from
I get you there to the moon. Resisting my love, got you fueled. You overdose on the mission. Why does it feel so good? Yeah. I put in my last into you, giving you space, so much room. You overdose on the mission. Why does it feel so good?
on your knees.
Wanna live in your light, wanna live in your light. Oh, I wanna live in your light, in the darkest night. All I wanna see is you. Pull me back, yeah. Pull me back again, yeah. Pull me back. All I wanna see is you. Pull me back, yeah. Pull me back again, yeah. Pull me back. All I wanna see is you.
There's something to be said. Don't you think it's funny that I'm giving you the time when you just left me dead? There's something to be said. Honestly, you're kinda lucky that I'm giving you a shot after the things you did. And I really think it's lovely that you really wanna love me. But you know I'm not that type. I think we burnt that bridge. I don't wanna do this any more than you. But since you left that night, I don't care what you do. Now you're messing with my head, thinking maybe it's okay now. Till you opened up your mouth when I never had a doubt. Now you're acting like the victim, really hoping for a lie, like it never meant to hurt you. How about I finish with the truth? I don't wanna be with you. Can I get you out my system? And I really think it's lovely now that you really wanna love me. But you know I'm not that type. I think we burnt that bridge. I don't wanna do this any more than you. But since you left that night, I don't care what you. I don't wanna do this any more than you. But since you left
myself from falling down. I don't know how, I'm still standing on the ground. I don't know why you keep wishing for me to change. You keep wishing for me to change. Everybody want 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 me to change.
Okay, welcome back, everybody. So we're just going to have a quick talk from Google by the representative Tingdang Zhang.
Thank you, Edward. Can people hear me? All right. So today, can I have the slides showing up there on the big screen there? No? Okay, here we go. Thank you. Thanks, Edward, for the introduction. So today, I'm going to talk on behalf of the robotics team and Google, who we are, what we're doing, what's our mission, and I'll give you some intro ideas about the cool research we're doing over there. All right, so who we are. We are a team about like 70 engineers and researchers with very diverse background from all over the world. And our mission at the robotics team is to make the robots useful in the real world through machine learning. All right, so what do we mean by that, right? If you look at today's robots, they're generally highly expensive. They're highly being constrained to specialized tasks. For example, you have the industrial robots at the lower left corner. They can only do one thing. They can do it very well, but they don't generalize to any other tasks. And we also recently have been seeing the trend of the autonomous vehicles, right? They can do much better in terms of the environment they're dealing with, but still, they are more geared towards specialized tasks. And at Robotics Google there, we're more interested to see if our robots can adapt to various environments and perform lots of different types of tasks. So what do I mean by that? All right, so for example here, there are lots of different tasks that can vary from various levels of complexity and difficulty in intelligence, right? There are some immediately useful tasks, for example, in the micro-fulfillment center where the robots is more constrained, but it has industrial value immediately. But also on the lower left, you can see there are some more open-ended questions, including if the robots can follow human instructions, like with semantic informations. And given that, I'm going to give you a little bit more overview of the teams and the tasks and the research directions we have in the robotics team. So we have a manipulation team. Their main research focus is to use a visual motor control to solve various different levels of manipulation tasks. And some of the tasks, some of our research work you probably have already been seeing here in CoRL. That includes in this kind of MT-opt, which they can use a single setting, train the manipulator to solve various different kind of tasks and skills, including, for example, follow the semantic instruction, like put that thing into the cup, etc. And since in order to be our learning, our approach to be scalable, we are a firm believer of data, right? We collect a lot of data in a scalable way, and we store them and we use them for pre-training as well as for online fine-tuning. So, and we have the infrastructure there to collect data. For example, we can collect data from remote operation, and also we can use the direct human demonstrations. And with those demonstrated data, we're able to solve complex tasks, for example, this skating task, which happens in the manufacturing. And it's really difficult for machine to infer and understand what's happening there. So far I talked about the manipulation tasks that are mostly in the more static environments. And of course, in the real world, there's a different side of a manipulation task that are highly dynamic, where the timing matters a lot, right? With demonstration data as well as self-play data, our robots actually is able to play the ping pong game as being shown here. So in order for the robots to be useful in the real world, they not only should be able to perform a manipulation task in one place, but also it'll be very useful for them to move around. So such that, for example, I want my robot to come and pick up the package from my door, or bring me a cup of drink from a refrigerator. That means we need robots to be able to safely and autonomously navigate in human-centered environments. And that also requires them to be able to interact with humans in a very social way. Last but not least, we're also interested in the outdoor environments, because humans not only live inside the home, but they also occupy a much larger area outside our home and office areas. And the locomotion platform are one such promising platforms for us to tackle these outdoor movement challenges over there. And because of their biological relevance, they're also the knowledge that we gain from those locomotion platforms may also potentially apply to assist the humans in their day-to-day walking. So we as a team, we actually very value about our research and collaboration with external collaborators. For example, for all the faculties and universities, we have many programs for them, including some research grants as well as visiting scholarship programs. And for students, we are also always welcome. There are lots of fundings, scholarships, etc. But more importantly, we're also hiring. So if you're a student and you're interested in learning more about our research, you can come and talk with me. Thank you. Thank you.
All right, thanks very much. Okay, so we're going to move on to the third and final Blue Sky session now. So we have 4 speakers. They're all going to be remote, so they'll all be up there in the virtual world. And they're going to be speaking for 5 minutes each, and then we'll have a discussion afterwards. So I think the way Ken did this yesterday was very interesting in that he asked people to try and draw together the speakers and come up with common themes that could then potentially move on to a discussion. So I think I'm going to follow something similar, but I might flip it a little bit and ask the audience for what the common themes are at the beginning of the Q&A session to see if that then leads on to a discussion rather than at the end. And then, of course, I will leave time for individual questions to individual speakers as well. So during the talks, try and think about what are the themes that draw these speakers together. Maybe are there any contentious issues or any opportunities for debate amongst the different talks. So I'm also joined by my remote co-chair, Marco Pavoni. Is he there? Hello, Marco.
Yes,
welcome.
hello everyone. I look forward to an active discussion.
So Marco is going to be monitoring the virtual questions, so please do keep posting questions on Feedloop, and I will monitor the questions here in London. So our first speaker is Kinji Lin, and the topic is RoboFlow, a data-centric workflow management system for developing AI-enhanced robots.
Hi, so let me share the screen. Okay, could everyone see the screen? I guess.
We can't see your slides just yet, but I think they're coming.
Okay, I'll wait. I think I'm sharing the screen, right? Okay.
Yeah, just bear with us, please. Are you putting the slides up on the screen?
Yep, I have already.
Sorry, that wasn't to you. That was to the AV team.
Okay.
I think we're almost there. I can watch what they're doing here. Well, you have some extra time now if you wanted to talk without your slides. If you wanted to make the most of this time to get a head start of the other speakers.
Yes. Yes. So, so while we are waiting for the slide showing, I could have like a quick introduction about our work. So our work is RoboFlow is a data-centric workflow management system for developing the AI-enhanced robot. So different than the classic workflow, we will develop a data engine, and this data engine will like abstract out all the data from the simulation, the real robot data, and the model data to the developer, and also we have a cloud-based design. All our modules are running on the like cloud. We leverage the Docker and the Kubernetes, these popular cloud resources. And yeah, I think my slide shows right.
Ah, there we go. Great. So
Yes.
we can see your slides, and I'll give you your full 5 minutes from now.
Okay, great. Okay, so everything goes well. Hi, everyone. My name is Qingjie Lin. I'm a second-year PhD student at Northwestern University. And today I'm going to present our paper, RobotFlow. It is a data-centric workflow management system for developing the AI-enhanced robots. This work is done with the cooperation with Guoye, Jiayi Wang, Tony Ro, Han Liu at Northwestern University. And let's talk about the classic workflow of AI-enhanced robot first. We summarize the workflow into 4 modules. The first module is data preparation module. This module will transform or encode our data into a state that other module can easily parse. And the second module is algorithm module. This represents the planning process of the robots. And the third module is evaluation module. This evaluates the policy based on a large-scale collected or simulated data. And the last module is deployment module. In this module, we deploy the planning policy into real-world environments. And besides these 4 modules, there are complex interaction with data in this workflow. Like here, the data preparation module will output the data set to the algorithm module. The algorithm module will output the model data to the evaluation module. And the evaluation module and the deployment module will communicate real-time data from simulation or real-world or real robots. And the property of this interacting with massive amount of data make this classic workflow hard to parallelize the development, because like here, the algorithms wait for the data set output from the data preparation, and also the evaluation module should wait for the algorithm module to output the trained model. And there are also one reason for the RoboBro is that even after we successfully deploy the trained policy into the real world, continuous modification and improvement on each module are still needed when more data get acquired. And so these two motivate us to improve the workflow by propose to design. The first is data-centric design. The second is cloud-based design. So in classic workflow, so besides these 4 modules in the classic workflow, we developed a data engine. And this data engine will abstract out the data set, the model data, the simulation data, the real robot data, and all the 4 modules in this workflow are interacting with this data engine. And the main idea of implementing this data engine is that we leverage the Glassdoor LFS and the roles to expose the data from different sources to the developer. And the developer can access the data from different sources through accessing the storage or visualizing the website or using the API interface to access the data. And besides this data engine design, we have a cloud-based design. We Dockerize each module to increase the maintainability and the reusability. We import each module into a Dockerized container. And in this way, each module can be run as an isolated single process on the system. So this enabled the RoboBro to develop each module in a parallel fashion. And also, since the Docker can record the change of each module, so it's easier for us to do the version control. And besides this Dockerization, we also introduced the Kubernetes to manage the resource for each module. like here, each module are wrapped into a Docker container, and then we leverage the Kubernetes to allocate the like GPU, CPU, memory resources for each module. And since every module here on the workflow is running on the cloud, so we also provided the graphical user interface for developer to access different modules parallelly. So here is the RoboFlow web GUI. So the configuration page allowed the developer to configure the CPU, memory, GPU source for each module. And the Jupyter Lab page allowed the user to modify the code in each module. And also in the evaluation module, we can monitor the robot behavior in the simulation. We also plot the behavior data from the simulation and let the developer to monitor the robot behavior. And also in the deployment phase, we are able to visualize the image data from the robot and monitor the behavior, the action behavior from the real robot. Yeah, that's all. Thank you.
Thanks very much, Kinji. Okay, so our second talk is from Homanga Bharadwaj, and the title is Auditing Robot Learning for Safety and Compliance During Deployment.
Thank you. Can you see my screen? Perfect.
Yes, we can see your slides.
Okay. So my name is Homanga, and I'm a PhD student at Carnegie Mellon. I'm going to be talking about auditing robot learning for safety and compliance during deployment. So let's start with the problem. The problem is that robots are becoming increasingly good at solving different tasks, often with superhuman precision. We've already seen a few examples of these from the robotics at Google Talk, so I won't go over them again. So given that robots are increasingly good, what exactly is the problem? The problem is that we don't have measures of quantitatively checking whether they're behaving in ways that we want them to. What they're good at doing is optimizing for a certain objective, but what if that objective they're optimizing for is different from that the algorithm designers originally intended? And in the catastrophic limit, what if they optimize for something that is clearly disastrous to humans? So versions of this problem has been proposed over the years. And one of the old quotations from King Midas is that we had better be quite sure that the purpose put into the machine is the purpose we really desire. Now, some familiar examples of catastrophic accidents happening, or maybe not so catastrophic accidents. For example, a robot grasping a cup of water and bringing it over to a person. So the objective is to bring the cup to the person, whereas the intended behavior is to pass it along in a way that the cup doesn't drop or the water doesn't spill on the floor. Some examples from news articles are about self-driving cars that strike pedestrians who are jaywalking, and a Facebook bot that comes up with its own secret language, which clearly it wasn't optimized for. So what is a potential solution for these kind of problems? Well, we could have rigorous testing of failure modes prior to deployment, and we could train the models such that these failures are less likely in the first place, a process we refer to as auditing. The analogy here is to, for example, industry pipelines like car manufacturing, where we have a production phase and a rigorous quality testing phase prior to deployment. Then the question becomes, how do we audit for robot learning? We need to come up with specifications that we want the robot to satisfy under different control variations of the environment and the task. The aim here is to encode preferences about what is safe versus unsafe and what is compliant with human preferences versus uncompliant. To do this, we can't have purely didactic objectives wherein a human specifies a command or an objective function a priori, and the robot needs to optimize for that. This is because humans themselves are usually unsure of their preferences concretely. We cannot come up with a crisp objective function that distills everything we want the robot to be doing. This is true both for imitation learning-based approaches where you have expert demonstrations, or reinforcement learning objectives, reinforcement learning-based approaches where you have a reward function as the objective. So the alternative to this is a human in the loop process for learning. This sounds like a natural solution, and based on this, we could come up with the design of an initial auditing framework where we have a pool of human auditors, a bag of objective functions where each objective function is likely imperfect, but there's a whole bunch of them, and a set of tasks or settings where we want the robot to be ultimately deployed in. Then the verification process is for the human auditors to examine temporal sequences of the robot's trajectory and determine whether each trajectory is unsafe or uncompliant. Based on this rating, we can pool this across the human auditors and come up with an aggregate score. Based on verification, we can come up with a verified training phase where you do this verification inside the training loop. In this case, when the auditors determine whether a temporal sequence is unsafe or uncompliant, we swap the objective function with another in the bag. The idea is that each objective function is likely imperfect, but during this iterative process, we could distill human preferences about what behavior is desired from the robot by swapping the function. And we repeat this over training. Finally, the most important phase is deployment, where we tabulate the results of the verification and we release a specification sheet along with the deployed model. This sheet should include the details of all the tasks and settings the robot was evaluated in for auditing and the human auditor scores that was assigned for each task. An example of this for the task we saw earlier could be different tasks could be different shapes of the curb, different types of floor the robot needs to walk in, and so on. The ultimate aim of this framework is to make quantifications of such failure modes in a large number of settings by humans the standard for inclusion in a specification sheet prior to deployment of the trained robot learning algorithms. In summary, my main aim was to bring ideas from the AI alignment community about objective misalignment into the robot learning community and try to formalize the necessity for auditing. The framework that I described is definitely not practical for implementation as is, but we as a community should probably think about ways you could develop and implement mechanisms for auditing robot learning systems before deployment. Do shoot me an email if you have any thoughts or follow-up points. Thank you.
All right, thank you very much for the talk. Our next talk is going to be given by Sergey Levin from UC Berkeley, and the talk is titled Understanding the World Through Action.
All right. So why does deep learning work at a very high level? Well, if you have a very large model and a large data set, then you can get learn models that generalize very well. But of course, conventionally, the data set needs to be labeled, and that's where a lot of trouble comes in, that we need to obtain these large labeled data sets. And a big reason for the explosive growth in self-supervised learning recently is that with self-supervised learning, in principle, you could have a smaller labeled data set and a giant unlabeled data set of this kind of low quality garbage data that you can just find off the internet. And self-supervised learning allows you to incorporate that. And that's grown tremendously in NLP and computer vision and other fields. But what do these techniques actually learn from? Where do they get their knowledge? The classic view is, well, maybe we're doing unsupervised learning. We have some kind of density estimation problem. That's great because it's purely data-driven. It's principled. You can do lots of math in your papers. But ultimately, it's just learning from whoever collected the data. So if you have a classic static data set like ImageNet, which was collected by Flickr users, you're learning from whoever chose to photograph the things and put it on Flickr. If you're learning from garbage data off the internet, then you're learning from whoever threw out their garbage, and that doesn't sound very appealing. Indeed, this is not actually the recipe that ended up working so well. The current most popular approaches to self-supervised learning are all based around some version of data augmentation, which works really well, has much less math, but you're learning from the smart researcher who designed those data augmentation rules. So that also doesn't seem so appealing because really the knowledge is just put in there by another engineer. Stepping back a little bit, if we want to design a more principled approach to large-scale self-supervised learning, we could start by asking, why do we need machine learning anyway? And we could start with an even more basic question, why do we need brains? Let's ask Professor Daniel Walpert. He's a world expert on brains, and he has this to say. We have a brain for one reason and one reason only, and that's to produce adaptable and complex movements. Movement is the only way we have of affecting the world around us. I believe that to understand movement is to understand the whole brain. I would put forward a postulate about machine learning inspired by this. Perhaps we need machine learning for one reason and one reason only, and that's to produce adaptable and complex decisions. Let me try to defend this postulate. For all of us here, we work on robotics. In that context, it's fairly clear how our learned models output decisions. Your robots will decide how to move their joints or how to steer a car. But even if we're thinking about things like image classifiers, they also make decisions. Their decision is not the image label. It's actually the thing that happens afterwards. So if you have your system running for a website that will tag users' photos, the decision might have implications about how the user then interacts with that system, whether they're happy with that interaction, and so on. So all these outputs, even for supervised learning systems, are decisions, and they have consequences in the real world. So what if we think about a self-supervised learning framework that is rooted in decision-making? The basic principle is that if the goal is to eventually make decisions, let's pre-train the models to be good at making decisions. A decision, you can think of that as an action that leads to some outcome. So what if we learn how to take actions to produce any possible outcome? If the point of machine learning is to make decisions, this seems like a great recipe for pre-training. This is essentially a goal-conditioned or task-conditioned reinforcement learning problem. So you could have your agent essentially playing in the garbage dump, learning about how the world works. The problem is that with naive RL, this is a very costly interactive process if done in the real world. It kind of defeats the point. We want to gather all this garbage data that's already available, not introduce another costly online learning loop. So if self-supervised learning is about cheap data, this somewhat defeats the point. So that's why we need the second part. We need to bring in offline reinforcement learning, which can leverage data that is already there, but then use it for this self-supervised reinforcement learning process to learn how to make decisions. So let's learn to make all possible decisions using offline RL from plentiful data that we've already collected, and use this as universal pre-training to help us make other task-directed decisions for downstream tasks. So the recipe is you take your low-quality data, which could be all the data from past interactions your agent has had, use it for self-supervised reinforcement learning, like goal-conditioned RL, and then use this to learn downstream tasks. And remember, this doesn't have to be a downstream RL task. It could actually be a downstream classification task. So really quickly, an example of something that gets at this point in some of our recent work. This is a paper by Yepi and Chebatar called Actionable Models. This is a goal-conditioned robotic manipulation system. So there's no reward function. The goal is just to match a goal image. It's going to use offline RL, CQL in this case, and train entirely on prior data that we had collected for other previous projects. Now, the resulting system is good at matching goal images, but that's kind of not the point. The point is that then we can use it for downstream tasks, almost like a robotics version of BERT. So you train with your self-supervised objective to accomplish goals, and then you can fine-tune with a task reward. In reality, it's a joint training process, not a pre-training process, but that's kind of a detail. And then it accelerates downstream tasks. So just to conclude, this is not just about robotics. Self-supervised offline RL can be applied to any domain where we need machine learning to make decisions. And there's lots of missing pieces left to figure out. What's the right self-supervised objective, the best algorithm? How do you transfer to downstream tasks, utilize diverse data sources, etc.? But if we can figure out these questions, we can develop powerful and principled self-supervised learning methods that will prepare our learned models for precisely the thing we need them to do most, make intelligent and adaptable decisions in the real world. Thank you.
All right, thank you very much, Sergey. Our next and final talk for this session is going to be given by Vika Antonova. And her talk is titled Learning to be Multimodal, Co-Evolving Sensory Modalities and Sensor Properties.
All right, hello. I'm wondering whether the slides are showing up yet. Not yet?
Yes. Yeah.
Yes.
There's a little bit of
Perfect.
delay, but they're going to
Okay.
come.
All right. Let me try to set it up here. Okay, so yes, we're going to talk about learning to be multimodal. And if we look at the impressive variety of sensors that animals have evolved in nature, we see vision beyond the visible light spectrum, perception for a wide range of sound frequencies. Some animals use electroreception for underwater localization, and some birds even figured out how to use Earth's magnetic field to do long distance navigation. So if more is better were the main law of sensing, then we would see an impressive agglomeration of sensory capabilities in the more advanced animals, such as us humans. But instead, we see that sensors are specialized, and our guess is that sensor choices co-evolved with the organisms and were subject to the constraints of energy, size, and the target tasks. And likewise, in robotics, we face the need to select a subset of sensors to address the budget, size, and energy constraints. But it is difficult to select the subset because we, these days, need to look at what the downstream learning methods are basically getting from the sensor data, and that determines what is necessary and sufficient. And another note is that using high-dimensional sensor data is not suitable in all cases. We might have tight energy constraints, we might have compute bandwidth and storage limitations. So sometimes we need smart hardware that is capable of targeting sensing and selecting the kind of a way to compress the sensor data. So making a single sensory modality precise and robust to get a human level performance and autonomy, that could be very expensive or even intractable. And so a promising direction is to use multiple sensory modalities, but it is very easy to settle into a local optimum of just using a common existing generic combination. And another issue is that we usually in this view treat the sensor properties as fixed, something that is just given by the manufacturer. So our main idea here is to co-evolve the sensor hardware design and the choice of the sensory modalities together with the learning methods that use the sensor data to solve a set of target tasks. So how can we do this? We can start by sampling a batch of sensory modalities, for example, vision and touch here, and then sample their sensor properties, for example, low resolution vision and high resolution tactile array. Then we can train to solve a set of target tasks and infer the utility of the combination of the sensor based on the task performance. And then we can maintain a global posterior that models utility of various sensor combinations and use this some data efficient approaches like Bayesian optimization, for example, to select the most promising candidate to try next, and so on and so forth. So updating the hardware design on each iteration, that would be very expensive. So we can instead start by creating approximate models of various sensors in simulation and then feed the synthetic data to the learning methods and update the posterior, then update the sensor design, the simulated sensor design, and so on. We can also use hardware data, so collect data from real sensors that are expensive, for example, high-speed cameras, high-resolution tactile array, and then subsample the signal to identify the maximum level of degradation that is still acceptable to solve the tasks. So about 10 years ago, it was shown that high-speed vision and actuation allows to solve very challenging tasks such as dynamic cloth folding and in-the-air knot tying. But the hardware that is used for this is not widely adopted for solving these tasks. So what can we do? We can identify maybe a lower frame rate is sufficient and lower the cost. We can also experiment with different predictive methods to see if the high-speed control can be replaced. Another thing that we can do is we can experiment with skin sensors, for example, infer the optimal coverage of the skin for the robot's body for various areas, and also understand what sensitivity is necessary, and also explore with data compression methods. And it is useful to note that combining vision and tactile and other sensors can be done effectively even with low-cost solution. For example, here, an exploratory hand can allow us to estimate object properties with minimal object displacement. We can also combine various sensors to get robustness against external forces, perturbations, movement of the target, and even camera occlusions. And so overall, we note that there are some immediate benefits of lowering the costs and finding optimal combinations of sensors to solve a given task, and also long-term effects where we can guide the research and development with this overall coevolution approach. All right, thank you.
Thank you very much. Now it's a discussion time.
Yeah, thanks very much, Rika. Okay, so I said before the session started that it would be interesting to see if anybody can come up with any common themes across all the 4 talks. So does anybody have any brave ideas as to what those themes might be? So one of the themes that I thought was consistent across, certainly in the first 3 talks, was the issue of scalability. How can we actually design a system that in some way scales either with using pre-training on offline data sets, or modularizing a workflow, or using people in the wild to label data sets. So there was a common theme there. And I was wondering about Rika's talk. So how, with this scalability idea in mind, how perpetual do you think this kind of co-design of sensors and using machine learning to design sensors, how perpetual do you think that could be? Could it be done autonomously, or would there always need to be a human in the loop? And if there needs to be a human in the loop, would that then actually be better than the human just designing those sensors using their own brain rather than the machine learning brain?
Yeah, that's like an interesting next step, right? We think that the sensor design involves the human in the loop, at least when you're doing the hardware modifications. And for example, right now, if we're doing co-design of morphological changes, right, then somebody needs to go and 3D print this, right? And for the sensor design, we think that it would be even more kind of like human knowledge and priors involved, because like some hardware engineer would need to go and wire something, make the new blueprint and so on. So yeah, I guess that's the next step, to figure out how to autonomously evolve the hardware design so that the system itself can update everything along with the hardware. So that would be interesting. Then that would be really scalable, yes. And for now, you're right. I think in this co-evolution design, the one bottleneck could be that, all right, you can do a lot of things in simulation, right? Everything is scalable, we can do massive compute, but after you're actually decided, okay, now I will update my hardware sensor, then yeah, there needs to be some sort of a human engineer in the loop to do this. So yeah, that's a good point, good next step, I think.
So do you think, like, building upon that idea, do you think, if you're just developing new algorithms and testing them out in simulation, then you're kind of safe that that's just going to be an algorithm developed inside the computer. But if the hardware itself is evolving, are you worried that you'll turn up one day and a monster has appeared that you were not predicting?
So the thing here to note is that, for example, the way that we thought about this co-design is this is co-evolving with the learning methods that we choose and the target tasks that we choose. And so here, I think we are bringing the point back home to saying, if we have designed the loss for the task to be correct, then ultimately this whole system is going to evolve to solve these tasks. And of course, if we observe some of the artifacts like what we kind of see in RL, where we specify the task and then some sort of behavior arises that we didn't expect, then this precisely would be kind of the point where the difficulties would arise. But the hardware itself here, since it's for sensing, it doesn't seem like that is the big danger here, because it's less for changing actions or changing embodiment of the agent, but it's more for changing what the agent is perceiving. So I would say that this particular line of work is a little bit safer. But again, now here, since it's targeting at solving these tasks, if the tasks objectives are misspecified, then we would basically have a better system for solving these tasks. And yeah, we have to agree with the reward or the objective function for these set of tasks.
Yeah, so it's up to us as the engineers to limit what can evolve autonomously and what cannot. I guess that relates back to the talk on auditing. I guess you could bring in, you could have humans watching the sensors evolve and then saying, okay, stop there because that's going to become dangerous if it continues evolving in that way. Yeah. So let's see, Marco, are there any questions on feed loop or any thoughts on any of the themes that have emerged?
Yeah, there is a question from Andrew at Johns Hopkins University. And the question is as follows. With this co-evolution concept, what about accounting for human diversity, such as disabilities?
What about accounting for it?
Yeah.
Is that the question?
Yes.
So I think the good part, of course, is since we are hopefully going to be lowering costs in many different areas, that usually is something that is key to addressing, for example, people with disabilities or certain groups of people who maybe have characteristics that are not extremely common. And I think this is one of the enabling powers here. One of my most favorite examples is the Open Hand project. I think this is the name, not entirely sure, but basically what they're doing is they're trying to have open source designs for prosthetic hands. And that allows to bring the costs down dramatically, and also allows the users themselves to evolve a little bit, basically customize the hardware based on what they need. Because the design is accessible, they can do it kind of personalized to what it is they need in their family, in their situation. So I think this is one of the key areas where this could really help, that you, instead of having just the standard sensors that address very, very standard situations, you can have a range of sensors that address very particular situations, and they can be targeted a bit better to the individual situation.
Thank you.
All right, any questions from people in London, or any general thoughts? Ivan.
Hi, so thanks everybody for your talks. This is a question mainly for Sergey. So I'm wondering about your view on the issue of how much of the robot learning process should happen in the lab versus in the user's environment after the robot is deployed. Because if you're focusing on unsupervised learning, as you talked about, then that opens up the opportunity of doing both without putting too much of a burden on the user, right?
Yeah, that's a good comment, and I think that's exactly right. So basically, I think a big part of the promise of techniques like this is that you actually don't have to be very picky about getting just the right data, but rather switch into a mode where you're using any data that you have available. And I think that the ideal thing is actually a kind of virtuous cycle where it's not about selecting between data in the lab or data from deployments, but actually getting the best system you can, deploying it, and getting data from deployment. But the other thing is that I think that self-supervised reinforcement learning methods, if set up correctly, they don't even have to rely entirely on data collected by your robotic system. It can be any data that is structured appropriately, sequential data where there's some notion of intervention that can be treated as action. So in some domains, this is obvious. So if you have, for example, dash cam videos of people driving cars, you can extract some notion of action from changes in global direction. Conceivably, you could even figure out how to do that from YouTube videos, as long as you have something that you can label as an intervention or action for the algorithm to reason over. It doesn't have to be a real action, it could be a virtual one. So I think in that sense, it should be possible to do this with very broad sources of data, including ones that are far outside the lab. But of course, to my knowledge, that hasn't really been done yet, so this is very speculative.
Jackie, yeah.
Hi, thanks for all these talks. It was great. I have two questions. Is that okay?
Yeah,
okay.
Sure.
The first one is sort of like a comment about Sergey's presentation on the actionable models. I think that it's actually a bit of a generalization to say that the difference between fine-tuning from like a pre-trained representation versus joint optimization is the same. Like it really would make a difference in deployment if you're like shipping a pre-trained representation to like many different robots who are doing different tasks.
Yeah, I agree with that. Yeah. I think it would be much better if it was pre-training and more scalable. But I think there's the distinction there is between the verifying that it's scalable and verifying that there's even knowledge to be transferred. So I would view that as an experiment that confirms that there is something to transfer. As to how to do it, I think that's still very much an open problem, and I agree with you on that.
And my second question is sort of, I think, for all the speakers, but like Rika specified like Bayesian optimization and GPs, probably because that's her specialty. But I guess that, that speaks to scale, like the amount of data you have. And Bayesian optimization makes sense in this case of coevolution of hardware, because you might have like very little data and collecting that is expensive. You can also make these simulators, but then there, like, I think often, like, and also like a lot of what like Sergey's work is in deep learning at a huge scale, right? So how do you reconcile this? Do the other speakers have opinions on techniques and with what they're trying to accomplish?
I could make a comment here. I guess one of the issues with learning from large data is related to what I spoke about. So it's very difficult to regulate about the behaviors that emerge from the algorithms. So that could be something, I guess, to think about how do we inject useful priors to the models in addition to self-supervised reinforcement learning, for example, from large data. So I guess that's just one of the comments about that. Curious if you have thoughts about that. Yeah.
I can also make a comment. So right now we can scale GPs pretty well. Still, neural nets, various versions of them are maybe arguably more scalable. But I think the reason why I brought up specifically Bayesian optimization there and GPs is because we have uncertainty estimates there. And so in that case, it wasn't only about the data efficiency, but it was also about the fact that if we want to make a change in the real world, if let's say we learn from simulation or from some pre-collected data that we sparsify, then we want to sort of be somehow certain that it is worth doing this change. It is worth investing time and resources into doing that. And so I think any model, if we want to scale it up, let's say with some neural nets, maybe Bayesian neural nets, maybe some ensemble approaches, something that can estimate uncertainty for us, that brings additional benefits. So one is we maybe are now sure that it is something that is worth looking at because we have collected enough data. And another thing is that we have kind of a more global view of what is happening overall because we have uncertainty estimates from various kind of parts of the space as opposed to just looking at one particular guess. Okay, this is the one thing that maybe we are after. So that's how the GPs came into the play, because previously they have been sort of the standard for getting good uncertainty estimates. And right now they're pretty scalable, although there are other competing approaches that could be neural net based that also offer this functionality.
Okay, Marco, how are things in the virtual world? Do you have any questions?
We do have a new question. So this question is from Hermano at Dyson Technologies. The question is as follows. Still in the direction of scalability and perhaps practical considerations for concrete domestic applications, I was curious of what are your thoughts on how we could also take into account uncertainty in model predictions and or auto-distribution scenarios in order to bootstrap continuous improvement of learned robotic skills. So it's basically a question about how we can account for uncertainty in model predictions and auto-distribution scenarios to bootstrap improvement in learned skills. Any takers?
I think I've already argued for using models that can estimate uncertainty. I would say, and I would maybe ask other speakers to comment on that, the challenge that we have right now, I think we all agree that, oh yes, having uncertainty estimates is good, but especially in the times where we're doing a lot of things with neural nets and we're doing a lot of things with various approximations, we have developed a lot of techniques that can return uncertainty estimates, but I think we haven't fully analyzed how good those uncertainty estimates are. And so I think this is like one of the major challenges right now, that the analysis of, because we are scaling, right? We can't anymore look at the small toy examples that we can fully kind of comprehend what the outcomes here should be. And so we get some uncertainty estimates and we don't necessarily evaluate their quality in practice. And so we might not know, this outer distribution performance, for example. We might say, oh yes, I can do this because my model is more sophisticated and I can sort of say something interesting about it. But can we actually, do we have enough in terms of doing this analysis? And maybe in your view, what are the next steps for us to be able to get more of this?
Yes, I think this is a great point. The point of calibration of uncertainties is something that is critical for many applications.
I can maybe comment on that a little bit. This might be a little too much in the weeds, but in regard to scalable uncertainty estimates with deep nets, I think one important factor, one important consideration to have is that typically we don't actually need uncertainty. We need whatever comes afterwards, which would be an upper confidence bound or lower confidence bound or something like that. And oftentimes it's actually a lot more scalable with large models, just directly learn that thing instead of learning a full posterior. Certainly in reinforcement learning, we've seen that in both exploration and offline RL. In exploration, it's a lot easier to get upper confidence bounds with bonuses. And in offline RL, it's a lot easier to get lower confidence bounds with some kind of pessimistic method. So for anyone who's frustrated about how difficult it is to train Bayesian neural nets, what I would suggest is to consider what you want to actually do with the uncertainty and just directly learn the thing you ultimately need.
I wanted to add a bit to the part about exploration that the question mentioned. So when the robot is trained, for example, in a domain and it needs to collect data in an out of distribution setting, then one of the challenges could be that we don't even have a good policy to start exploration in that domain to collect useful data. And this is where I guess the thing about unsupervised pre-training that Sergey mentioned could really help, because that could help us get some useful initial policy, for example, even in the out of distribution domain. And the robot could start from there in order to collect more data. So I guess that is one of the ways of ensuring that the data collected in the out of distribution domain is not completely garbage and so on. And that could actually help in bootstrapping the learning of the robot.
And I do have a question for Sergey. So my question is, the paradigm that you have discussed is of course general and in principle applicable to any sequential decision-making problem. I was wondering if you have any insights on some specific application domains where you think it might be more feasible or promising to apply this paradigm to.
Yeah, so I think I can certainly speculate about specifics, but I want to also, maybe elaborate a little bit on why I think it's general. It's, I gave an example of this stuff doing something sensible in robotics context, but I think actually the big promise is, we often think about pre-training on other settings, making robotic learning better in that way. But we could think about the opposite. How can interaction data that an autonomous system, like a robot or an autonomous car gathers, how can that be useful for other machine learning applications? I think that's actually, that's also a really fascinating area where this could make a big difference. Maybe we could in the future, instead of thinking about pre-training on ImageNet to make our robots better, think about pre-training on robots to make ImageNet classification better. And insofar as the purpose of these machine learning systems is to make decisions, perhaps pre-training them with ways that teach them to make better decisions will actually make them better at other tasks, better at reasoning about the actual consequences and the actual causal factors of variation and things like that, because of the way that they were pre-trained. So I think that actually that kind of stuff is one of the more interesting hypotheses that could be explored in the future, to say like, well, can learning with an aim towards decision making make you better at picking up on causal factors for downstream tasks that are not necessarily explicitly reinforcement learning tasks. So I would be very curious to see if that pans out.
And I also have a question for Homanga about the auditing framework proposed. I think it's very interesting and perhaps really needed, for example, for safety critical applications. But I was wondering if you have any insights on how this auditing approach would work in those settings where a mistake might have detrimental consequences. For example, in the case of an autonomous car, a mistake could be a collision that could lead to an injury. How would you tailor or apply your forensic approach to those types of safety critical scenarios?
Right. I guess in those settings, we would not sort of wait for the auditors to assess when a failure has occurred, for example, but to assess that a failure is likely to occur. For example, in the self-driving car, if a human is sitting inside the car and a failure is sort of likely, for example, the car is likely to drift out of the road or is likely to collide, for example, then the human auditor could sound a bell and maybe take over control of the car and record that as a failure of the robot in that particular setting. So in very high stakes applications, obviously this is kind of challenging, but that could be one of the ways of assessing the capabilities of the car in terms of auditing. So not wait for a failure to occur, but assess impending failure, essentially. And because a human is doing that, so that might be easier to do it compared to assessing it automatically. Yeah. Does that answer your question?
Yes, it does. Of course, this assumes that you have enough control authority to basically stop your system before something bad really happens.
Yeah.
Okay, do we have any questions here in London? Yeah.
Yeah, I have a question for Sergey. So how do you see online learning in your framework? So like if you have the robot pre-trained, it's pretty good, but maybe it does certain mistakes, but then it would continue these mistakes all along because it wouldn't sort of learn from the current experience. Do you see this problem, or how would you circumvent it?
Yeah, I think that's a very good comment, and certainly I wouldn't view this as being in exclusion to online learning. I think the point is rather that in the same way that self-supervised learning now gives us a good starting point, the point is to get that good starting point. So in the example that I showed from Yevgen's paper on actionable models, he wasn't, the point was not just to take a model that was pre-trained on goal reaching and just directly use it to do stuff. The point was to then combine it with a downstream task objective, and that did employ online learning. So I think that's basically the right recipe, is to get this basis for generalization, this foundation to build on from plentiful prior data. And then once you've got that foundation, then you can more rapidly and effectively acquire a task. And that task should also generalize better because you have the right representations to work with. So this is not to the exclusion of online learning. It's just to essentially bootstrap it more effectively.
So I have a question for Kinji and also Sergey. So Kinji, in your proposed framework, you have this modular idea where evaluation and deployment are treated differently. So on this theme of scalability, do you think that is limiting in that you wouldn't then be using the deployment data to train the robots? And then Sergey, a follow-up question is, where do you see this fine-tuning in terms of this modular pipeline? Would you see it as part of evaluation, or would you see it as part of deployment? So for example, would you be comfortable selling a robot to a factory and then that robot fine-tuning in that factory itself as part of the deployment, or would you only want to do that fine-tuning inside the lab? So Kinji, perhaps you can start this.
Yep, that's a good question. So I think for your questions, I would say our data-centric design, our proposed data engine, make it possible for the algorithm, for the policy to be continuously developed from the data, not only from the simulation, but also from the real robot. Our data engine, including the data from the simulation, also when we are deploying the robot, the data engine also will expose the robot from the data from the real robot. In that case, the algorithm module and the evaluation module had access to the data engine. So in these ways, we are able, in our workflow, the data engine propose, so make it possible for the evaluation module, algorithm module to continuously develop the model from the data.
Yes, so Sergey, if your fine-tuning was part of the deployment, would that make you comfortable, or would you want that to be only done in the lab?
Yeah, that's a good question. So I guess I have a boring technical answer and then maybe a more controversial, more speculative answer. So the boring technical answer is, well, in some ways it comes down to an empirical choice, like, is it better to do joint training or fine tuning or whatever? They both have pros and cons in various ways, and it'll probably be whatever works best. But in regard to, would I be comfortable? There's something loaded in that question. To kind of get at the spirit of what you're asking, I think actually a system with appropriate pre-training should make us much more comfortable than a system that is learning from scratch. Because besides learning a good foundation, a good representation, you should also figure out which kinds of behaviors are more reasonable and which kinds of behaviors are less reasonable. So if you pre-train on a lot of data of various drivers driving around, well, you should at least figure out some basics like, suddenly driving into a concrete wall is just not something that happens a lot in the data. It's not something that you can make reasonable counterfactual inferences about. So you probably should not do that, all else being equal. It's certainly not a ironclad method for safety. It's not like addressing the stuff that Hamanga discussed. But I think in the balance, a pre-trained system should be better and we should be more comfortable with it than one that is not pre-trained.
Yeah, so it's all about how, it improves your comfort, but it's difficult to say absolutely where that cutoff is. So we have time for a couple more questions, I think. Yeah, one here.
And there is also one more question from the...
Yeah, Marco, I'll go back to you in a moment for the final question.
Yeah, this is also for Sergey and the idea of self-supervision from large amounts of data. So from what I know from the GPT-3 work, they said that they had to filter out their large-scale text corpus to make it work properly. So I was curious whether you thought for the applications in robotics or in general, really, how important it is to filter out or clean out the data, even though it's been used only for pre-training?
That's a really great question. Since this is the blue sky session, I feel like that kind of gives me license to just make some stuff up without needing to substantiate it with evidence. So I'll make something up, but I'll preface this by saying this might be nonsense. My answer here would be the following. I think this should be much more of a problem for generative methods like GPT than for a method that trains for decision making. And the reason is that a language model learns to do what was done in the data. So it becomes very important then what the distribution of data is. Remember at the beginning of my talk, I talk about this P of X, right? Unsupervised learning learns P of X, so it's learning from whoever collected that data. And there's a really big difference between that and learning to make decisions. When you're learning to make decisions, you're really asking counterfactuals. What would have happened if I did something else? And I think that might actually end up being a huge difference in practice. And it might, and this is the really speculative part, I don't have any evidence to substantiate this, it might actually make you more resilient to including bad data, because when you include bad data to the decision-making system, it is evidence that bad stuff could happen, that undesirable things could take place. To GPT, it's evidence that this is something you should do, because that's what you're training, that's how you're training the model. But again, I just want to make it clear that I don't have any evidence to back this up.
Thanks, Sergey. So Marco, would you like to ask the final question?
Sure, a question again for Sergey. What unsupervised reward formulations do you find most promising? And what is a good measure for being a good unsupervised reward?
Sorry, was that a question for me?
Yes.
Okay. I think that's a really important open question, actually. So, there's some easy answers like we should do goal reaching, but I find that a little unsatisfying because there isn't any seemingly fundamental reason why that should be the case. There are also much more elegant methods for unsupervised skill discovery that take a more information theoretic approach to the problem. And we actually have some recent work led by Benjamin Eisenbach from CMU that analyzes some of the theoretical properties of these things. But from a practical standpoint, so far those methods have been a little tougher to get to work well. So I think in general, this is a really interesting open problem. And for those of you that are interested in this stuff, I would encourage you to work on that, because I think there's probably some pretty cool things that you can discover in the next year or two there.
And one more question, since we have still 1 minute left. Again, for Sergey, do you think the large data set, the pre-training model, will restrict the creativity of the policy? And the argument is that since training from scratch could lead to a policy that has never existed in human experience, but it's also useful for the task.
That's a great question, actually. Yeah, I think, my first instinct was that I need to defend the thing I presented. But actually, I think there's a point there, and it is true that if you use prior data, especially data that came from humans, you are sort of loading the model up with that prior, and it will probably cause it to do things that are more similar to that. So yeah, I guess you could imagine that if there's some task where you want a totally novel solution, it's better to start from scratch. I guess the classic advice that sometimes is given to starting PhD students is like, you should read papers, but don't read like too many papers because you want to still like come up with original ideas.
Yeah.
And maybe that's true for our robots tutor degree. So I think there's a point to that.
Thank you.
All right, so it's 3:30 here in London, so I think we should draw to an end here in the Blue Sky session. Thanks so much to all 4 speakers for joining us. So we're going to a break now, and then we have the tutorial in half an hour.
Will you meet me halfway down? Somewhere between heaven and the ground. 'Cause I know you what I really wanna climb my way up to the top and jump right off the highest heights. Falling, falling, falling. I'm falling, falling, falling. Can't hold back on trying. 'Cause my body is all in. Though my conscience is calling. Oh, I'll just keep falling. I'll just keep falling. Oh, I'll just keep falling. I'll just keep falling. I'll just keep falling. Why would you say that you want me if you don't know me at all? Thought I knew who you were, but you showed me someone else. Now you know, sitting here thinking that I misled with love. That in my dreams, know that I'm bleeding bloody. share with us. Getting my feelings. Don't you know that I'm bleeding badly? You're the one broke this straw. Rhapsody, can't you see? I forgot the color blue. Whisk across the universe, lead through. Stop and stare, first flight, and I feel it in my bones. Lost in deep space, not far from home. In this great design, got our roles to play. With the script this time of the day. There, birds fly. Deep space nine, great design. Bring this time of the day. There, birds fly. Deep space nine, great design. Bring this time of the day. My desire, stoke the fire. You can't ever put this out. Starting gun, you're the one broke this drought. Rhapsody, can't you see? I forgot the color blue. Whisk across the universe, lead through. Stop and stare, birds fly, and I feel it in my bones. Lost in deep space, not far from home. In this great design, got our roles to play. With the script this time of the day. There, birds fly. Deep space nine, great design. Bring this time of the day. There, birds fly. Deep space nine, great design. Bring this time of the day.
You pour me a new drink, and you don't ask me what I'm thinking. With so many things trying me, and so many keep crying. If there's anything I've noticed, if I know anything I know this, you show me that I'm wanted. You show me that I've got you. Wherever you go, you got me high or low. Wherever you go, you got me high or low. You got me high or low. Wherever you go, you got me high or low. So many inside jokes, just how to light my smoke. Allow me to be less, allow me to learn lessons. And even when I get abrasive, well, that is when you get embracive. You show me that I'm wanted. You show me that I've got you. Wherever you go, you got me high or low. Wherever you go, you got me high or low. You got me high or low.
alone. Wherever you go, you got me high alone. Wherever you go, you got me high alone. When things get heavy and I'm not okay, you grab me by the chin and lift my face, so I'm there for you wherever you go. You got me high or low. Wherever you go, you got me high or low. Wherever you go, you got me high or low. Wherever you go, you got me high or low. Wherever you go, you got me high or low. Wherever you go, you got me high or low. You got me high or low. I'm crashing down and rising up, but always seem to fall behind. And all the lights and all the tunnels faded out and left me blind. 'Cause in the wild I was getting drunk with something I don't know. Oh my, oh. The queen of love promised me that I'll be fine by tomorrow. Oh my, oh. Flutter on the wings of a butterfly. I can take you high, I can take you high. Flutter on the wings of a butterfly. I can take you high, I can take you high. I can take you high, I can take you high. I can take you high, I can take you high. Of a butterfly.
stay with you, whether you know it. I'm gonna stay with you. No rain, no fear can take us away or break us. No words said in anger tears us apart. I know it. If you will go, I will go with you. Whoa. If you will go, then I will go with you. Whoa. Whether you know it.
Okay, welcome back. So we're going to move into the final tutorial for CoRL 2021. And we'd like to welcome Natasha Jakes, who will be talking on social reinforcement learning.
Thank you
Hi,
so
Natasha.
much. Thanks. I'm excited to be here. So I'm going to be talking about social reinforcement learning. I think most of us are familiar with reinforcement learning as a paradigm. So you have an agent taking a series of actions to maximize its long-term reward. And hopefully a lot of us are on board that deep reinforcement learning is pretty promising and has been showing some impressive results, especially in robotics. But we're also aware that it has a few issues. So some salient ones that come to mind are the computational complexity. If we look at AlphaGo 0, it needed to play 5 million games of Go to reach proficiency, which is about 560 years of human playtime. The other big issue is generalization, right? So the big joke is RL is the only machine learning area where you can train on the test set, right? We consistently see issues with RL algorithms generalizing to even slight modifications of their training environment, which of course is a huge problem if you want to do something like robotics where you have to operate in the real world. So the focus that my research asks is, what could social learning do for reinforcement learning? So what do I mean social learning? Basically, I mean a pretty broad definition, which just means learning from other intelligent agents that are in your environment. So this could happen through direct interaction and feedback from those agents, like if a human is providing feedback. It could happen when you're trying to cooperate or compete with agents, or it could also just happen when agents are coexist in your environment. So if you think about autonomous driving, there are lots of other cars on the road that might have valuable expertise that you could learn from, but you have to be careful about who and what you're learning from. So the reason I think social learning could be this really powerful mechanism is because we see all the time that it helps humans and animals do really valuable things, like generalize to new environments. So even this little 1-inch fish can locate safe sources of food in a dangerous new environment by looking at where the other fish are gathering and using that as a social cue. And in the UK, they have this nice example of birds learning to open milk top bottles, not because they each independently discovered this behavior, but because they were able to learn by observing other birds. And a lot of authors have argued that the key differentiator that sets humans apart from other animals is actually that we've taken these social learning abilities to the next level. And that's the driver of our intense, like, cognitive, cultural, and technological development. So I think social learning could provide a lot of these benefits to RL agents. So the first one is obvious. We know that individual exploration is incredibly expensive and time consuming. So you would never think about, starting with the technology of rubbing two sticks together and exploring randomly and hoping to discover the Large Hadron Collider. Like, that idea is almost laughable. And yet that's how we train our RL agents a lot of the time. Like, if we want to train this Mujoko cheetah to be able to walk, we have it randomly wiggle around until it discovers a policy about how to walk. But in contrast, social learning lets you stand on the shoulders of giants and learn by observing or building on what other people have already discovered. The other issue is that individual exploration can be really dangerous. So if you think about, let's say we were to train a robot that we want to operate in human environments, and we want to deploy it into a new neighborhood. If that robot randomly explores that neighborhood, it could put itself in a dangerous situation. So I actually managed to find an image on the internet of a robot getting hit with a car that I was very proud of. Kind of illustrates what could happen. But in contrast, if the robot could use social learning to look at where human pedestrians are walking, it can be more likely to be able to find safe places that it can explore. So I think this could be really powerful. Basically, I think social learning could help RL agents learn more complex behavior, adapt to new environments, coordinate with other agents, and ultimately improve human AI interaction. So this is what I'd like to convince you of today. When I say social learning, I do want to emphasize that I'm talking about both multi-agent interaction and human AI interaction. And I'm going to be focusing mainly on the first part today, but I'll briefly touch on the second part. So for today, I'm going to be talking first about coordination in multi-agent systems, and then about multi-agent training as a tool to actually improve single agent learning and generalization. So basically showing that multi-agent learning can go beyond coordination, can actually be useful for just improving RL agents in general. And then I'll briefly touch on trying to learn from human AI interactions using similar techniques. So first, let's talk about the problem of trying to get multiple agents to coordinate with each other. So what do I actually mean by that? Well, a good example is thinking about trying to play robot soccer. We want multiple agents on the team to be able to coordinate their behavior to win the game, which might involve taking moves like passing the ball to each other. Now, there are a couple of issues with trying to do this. So if we think about how we could do this, one option would be, let's just learn a mega policy that decides the action for each soccer player on the field. So it's like some meta controller that controls everyone. The issue with this is that now your action space of the meta controller becomes exponentially larger in the number of agents you're trying to control. And this huge action space is really intractable. It's going to be difficult to collect enough data to learn this policy. So this is pretty hard. The other alternative would be to learn fully decentralized policies. So each agent is learning its own policy. The defender is just trying to learn how to do that. But the problem is that because all the agents are learning at the same time, they make the environment non-stationary. Like if I learn that your policy tends to put you over here at this time, so I'm going to pass to you, but then you update your policy, that's no longer valid, right? And the problem with the environment being non-stationary is that the convergence guarantees of a lot of RL algorithms are based on a stationary environment. So you lose a lot of those guarantees. So that's a hard problem. So one approach that's been commonly taken in the literature is kind of the mix of two. It's called centralized training, decentralized execution, or CTDE. So I'll explain a bit more what I mean by that. A really canonical example of a CTDE algorithm is MADDPG. So the idea here is that we want at test time to be able to have fully decentralized policies that can operate independently. But we know that if we try to train in a fully decentralized way, that's really non-stationary and that's too hard. So what MADDPG does is says, let's have a centralized critic, basically a value estimate that we can use during training in the policy gradients training to be able to stabilize training, learn more effectively. But then at test time, we can remove the critic because it was only used for computing our gradient updates, and we can just operate in a fully decentralized way. So this paper has been massively popular. It's been built on a lot with many centralized critic methods. And one of the most popular of those is called QMix. So QMix basically had this insight that what we want from our decentralized policies is that if each agent learns its own value estimate and greedily takes the maximum of that when it's deciding how to act, we want the joint action chosen by each agent independently to be consistent with what we would get if we actually were able to estimate the joint value function and take the max over that. So that's the insight. The way that QMix enforces this, it says, okay, let's have each agent estimate its own value function, and let's combine those using this mixing network that enforces a monotonicity constraint. And so that gives us this nice property that we want. So QMix has been really successful. A lot of papers have built on QMix. But for my own work, I actually was very interested in this question of could we train the agents in a fully decentralized way? And the reason I think that that's interesting is, if you think about real world problems of multi-agent coordination, I tend to think about something like autonomous driving, right? And so in that setting, you're not able to train with all the other cars on the road. The other cars are not sharing parameters with you or any privileged information. If you're the Tesla car, the Waymo car isn't going to send you information about its proprietary reward function. But what you can observe about those other cars is what actions they take in the environment. So I could observe if the Waymo car turns left, right? So what could we learn? How can we learn a coordinated policy in that setting? Now, we also had the intuition that maybe rewarding mutual information between agents' actions would create a bias towards learning coordinated behavior. So if you think about it, if two agents are coordinating, let's say two robots are coordinating to lift a heavy box or a piece of furniture. If one robot lifts the box faster, the other robot is going to have to as well to compensate, right? So they are exhibiting high mutual information between their actions when they are coordinating. So what we propose to do in this work was to give agents an intrinsic social motivation for having a causal influence on the actions of other agents. So what do I mean by that? How did that work? Well, first we took our normal DeepRL agent and we augmented it with a series of sub-module basically that's predicting the next action that every other agent will take, conditioned on the action of the agent itself and the other agents. And we just train this with supervised learning on the trajectories that the agent observes. What that allows the agent to do is simulate counterfactual actions. So it can ask itself, what do I predict this other agent would do if I had taken this action instead? And using that, it can sample a bunch of counterfactual actions and sum over them to get the marginal policy of the other agent, or the marginal policy of agent B. This is basically what agent B would do if it weren't considering agent A. And the divergence between that marginal policy and the policy of B actually conditioned on A's action is a measure of the causal influence of A's action on B's action. And if you don't believe me that it's causal, you can check out this causal diagram on the right. We see that causality can't pass through an unconditioned on collider node like state at t+1. And so we know that there's only a causal path between action of agent A and action of agent B at t+1. But look, the causality stuff is kind of semantics. If you don't care about that, the punchline is that we are going to give this as a reward to agent A. Basically, agent A is going to get a reward if it takes an action that causes agent B to do something differently. Now, there's a pretty big problem with this. So I'm going to give you guys a second to think about what could be an issue with this. And I'm going to ask you to let me know after the end of the next slide. So think on what could go wrong here. I do want to point out that this is related to the mutual information. So if you look at the influence reward, you can see that it's this inner term of the mutual information between agent A's action, agent B's action. But the mutual information involves summing over the probability of the state and the probability of A's action. But of course, when we randomly sample many trajectories from the environment, we actually do bake in those probabilities. So we can show that in expectation, the influence is increasing the influence is going to increase the mutual information between agents' actions. And if you think about it, previous intrinsic motivations have often been in the category of empowerment, which asks an agent to increase the mutual information between its actions and its future state. You can think of this as a form of social empowerment. But okay, I'm going to pause here. So I dropped that question. Can anyone point out the very obvious issue with what could go wrong if agent A gets a reward for causing agent B to change its action?
Anybody in London fancy having a go at this? Yes, over there.
That it can eventually force the other agent to do something? Sorry. That it can eventually force the other agent to do something rather than observing its actions?
That's correct. Thank you, exactly. So, if I just stood in your way, I could force you to do something differently. You have to walk around me, but I haven't helped you. So how is this going to help us coordinate or play soccer or whatever? So we basically take two approaches to overcome this issue in this paper. And the first is to test in environments where cooperation is actually the hard problem. So what you're looking at here is a tragedy of the commons environment on the top, where agents are trying to eat these delicious apples. And if they eat the apples too quickly, they'll become depleted and not grow back. And so every agent greedily wants to eat more apples, but if they all do that, they'll all suffer. Similarly, in this cleanup environment, the agent has to clean the river in order to make apples appear. While it's busy doing that, other agents can exploit it or defect by eating the apples that it's farming. So we can prove that these are hard cooperation problems by looking at the shelling diagrams. So what you see here is the payoff you can expect to get if you follow a defecting or exploitive policy in red or a cooperative policy in blue, based on the number of other agents that are cooperating with you out of 5. So on the far right of the graphs, every agent is cooperating. On the far left, no one is cooperating. And what you can see is that as an individual, you can almost always get a higher payoff by sort of defecting on your little agent compatriots. But of course, if all the agents follow that strategy, then the payoff will be very low for everyone. And vanilla multi-agent RL algorithms have a lot of trouble finding this trade-off to be able to figure out that the cooperative strategy will give them a better payoff. And so what we see is that if we add this influence reward, the agents are actually able to cooperate more effectively as measured in terms of the total collective reward achieved, even though they're only individually maximizing their own rewards. So how is this possible? And I should mention that this actually exceeds the performance of prior work, which did have access to other agents' rewards. Let's look at how this works. So in this video, you see that the purple agent is the only one that's been trained with the influence reward. And the policy it's following looks a little different than the other agents. So when there are no apples, all the other agents continue to explore around to collect apples, but the purple agent stays still. And in fact, it actually only ever moves if there is an apple nearby. So how does that allow it to gain influence? Well, it turns out, let's look at a moment where it's able to influence this yellow agent. So the yellow agent can only see what's in that red box because the world is partially observed. So it can't see that delicious green apple that's outside of its field of view. But when the purple agent chooses to move towards that apple, which again, it only ever does if there is food present, it actually signals about the presence of food to the yellow agent, which changes the yellow agent's intended behavior and allows the purple agent to gain influence. And similarly here, you can see that the pink agent has been busy cleaning the river, but it can't see if any apples have appeared. When the purple agent chooses to stay still, that signals reliably that there are no apples, so the pink agent should keep cleaning the river. And what's interesting about that is basically now the purple agent has made it easier for the pink agent to follow a cooperative policy but still get rewards by signaling about this extra information that the pink agent didn't have. So essentially, this agent learned to use its actions to communicate about the presence of food in order to gain influence. So by giving information, it gained influence. And so what we thought, of course, is let's try to train an explicit communication protocol with this influence reward. So here we equip agents with a second policy that decides which of a set of discrete symbols to emit on a cheap talk channel. And we train that policy with the influence reward. So you get a reward if you say a symbol that causes another agent to change its intended action. Now, the agent's actions that they actually execute in the environment are only trained with the environment reward. So the only reason this self-interested agent should change its behavior as a result of a message is if that message helps it maximize its reward. So we think this is the second way of overcoming that difficulty that you identified earlier, which is that influence may not always benefit the other individual. In the case of cheap talk, we think that influential communication should benefit the listener. So let's see if that turns out to be true. I should mention that cheap talk between self-interested agents doesn't usually work. We know theoretically that as agents' interests diverge, the amount of information placed on the channel goes to 0. And we know empirically that this doesn't tend to work out. But when we add the influence reward, we can see that not only do the agents achieve higher collective returns, so they're managing to cooperate, they learn more meaningful communication protocols, so they're speaking about what they're doing or things that are in the environment. But this is my favorite slide, basically. What you see here is the degree of influence between agents on the y-axis and the agents being influenced on the x-axis. And you can see that agents that are more easily influenced or better listeners tend to get higher reward. And this is actually a very strong effect across hundreds of hyperparameter settings in both environments. So we see that being influenced tends to get you higher reward. We think that's because influential communication is providing you valuable information that lets you maximize your own reward. So I do want to raise a couple discussion points. Whether the action influence is pro-social is going to depend on the environment. So we think that in our environment, communicating information may be one of the cheapest ways to gain influence while still maximizing your own reward. Like if you want to pick up apples, you can't just be getting in that person's way all the time. You actually have to go pick up apples. So this is, we think, why that arose. We think that influence on self-interested agents via cheap talk should benefit the listener, or should be pro-social, if you will. But of course, that depends on the agents interacting repeatedly. So if we had a communication protocol where I could communicate with a new agent that I might never see again, I could potentially lie to gain influence. All right, so in conclusion, I think of social influence as a unified method for promoting both coordination and communication in multi-agent settings. And it enables agents to learn socially, but train independently. So it doesn't require access to other agents' rewards or a centralized controller, as in previous work. Now, there's been a few follow-ups on this. This paper proposed 2 new methods for computing influence that work a little better. And this is a recent paper that benchmarked a bunch of state-of-the-art multi-agent algorithms in Google Research Football, which is the soccer environment. And you see that actually in this case, some of these influence methods are outperforming even QMix and Qplex. So that's kind of cool. But in all honesty, I couldn't recommend you use any of those methods because I've been playing around with Google Research Football and other multi-agent environments recently. And what I found works the best is actually just independent PPO. So basically separate independent copies of PPO agents. What you're seeing here is they absolutely crush those results in Google Research Football. Now this plot is actually unpublished. The only place I published this is to my email and this talk right now. And the reason I haven't published this result is because there's already several papers showing that independent PPO or even PPO with a centralized critic performs surprisingly well or amazingly well in a bunch of multi-agent benchmarks. So why is that? So it's actually the second paper that goes into this. Basically, they make the case through careful ablation studies that it's the stable updates in PPO that are based on inheriting like trust regions that make learning in PPO so stable that it's easier for other agents to learn with the other agents. So basically, I'm trying to learn to pass you in soccer. Are you going to be where I think you're going to be more likely to be yes because your learning is more stable? So I think that's really interesting. So I have to say, if I were recommending a multi-agent coordination algorithm today, I would actually say independent PPO. So I do want to, the next part of the talk is going to go into how multi-agent training actually goes beyond training agents to coordinate. But I want to pause here in case anyone has questions about multi-agent coordination in general.
Yeah, question over there.
Hey, Natasha. Thanks for that interesting result. So I'm actually a little confused about why trust region with independent PPO does well, because if I understand correctly, wouldn't the trust region apply to only the policy's current policy distribution? How would it know about the kind of updates that another policy is doing?
Right. It's basically saying the other policy that I'm learning against, it's updating more slowly and more smoothly. So when I'm trying to coordinate with it, I have a better idea about how to do that because it's not that its policy isn't jumping all over the place. So it's easier for us to discover and continue to benefit from coordinated actions, right? Essentially, it's just making the whole non-stationarity issue less severe. Like the environment is changing. If you think of other agents as the environment is changing more stably. Does that make sense?
Yep, thanks very much.
I have another question regarding the intrinsic motivation. So you mentioned this mutual information between your action and the action of the other agent given the current state. And you also mentioned empowerment. And people have been showing that empowerment, if you just compute the empowerment of the other agent, then you also perform cooperatively because you sort of help the other agent. So did you try this, or did anybody try this in this domain of deep reinforcement?
They have. So there's a couple of great papers by, the first author is Guckelsberger. I could be saying that wrong, but they're really nice papers. And they focus on minimizing or maximizing the empowerment of another agent, which is quite interesting. The one paper I'm thinking of, he says, I think it's called New and Surprising Ways to Be Mean. And they're making a video game adversary that minimizes the empowerment of the player. And they actually end up with this like sadistic agent that wants to, throw the human player in like a lava pit, but won't actually let the human die. They'll pull the human out just before he dies and then push it back in to just continue to minimize the human's empowerment. So very interesting paper, definitely something you can do and is worth exploring. I prefer maybe assistance via empowerment is another paper by Yu Ching. I'm sorry, I'm forgetting her last name, but you can check it out. It's called AVE, Assistance via Empowerment. And the idea there is to increase the human's empowerment, to be a good assistant to the human.
There is also a question from the online audience. The question is, but if the independent PPO got another communication channel that is their enabled chip talk, it could get even better, right?
Well, presumably, you could guess that, but I actually, yeah. So this MAPPO paper here that I'm showing at the top, it does use a centralized critic, but instead of using like DDPG agents underneath or using a Q-learning based thing, just uses PPO. And it shows to be pretty effective. I wonder, I think there's a paper to be made that bakes off having MAPPO or having fully decentralized PPO and just see what works better and maybe exploring that.
And there is a related question from Panag at Google. Just to make sure I understand, is the lesson that PPO agents training independently with social influence and chip talk is the best way?
Ooh, that'd be cool. That sounds fun. Let's write that paper.
Okay.
All right, I do want to go
in touch with the Panag at Google, so it should be a colleague of yours.
There you go, yeah. Yeah, I haven't tested that, so who knows. All right, so I do want to go on to the next part of the talk, because I think that's actually quite exciting. This is more cutting edge, I think. So I want to say that multi-agent training or social learning can actually go beyond just solving multi-agent problems like coordination. I think it can actually be this really useful tool for improving single agent learning and generalization. So this is a paper that I really liked. It's a thought piece paper, a position paper, and it goes through sort of the human psychology and cultural and sociology writing, and said that talks, there's another paper that I'm not citing here called The Social Function of Intellect. But a lot of these papers argue that what drove human cognitive development is the pressure of being in social communities, right? So both intergroup competition and cooperation within a group drove these ratcheting cycles that pushed us to develop our cognitive abilities farther and farther and farther. So essentially this paper is saying, could this form of multi-agent pressure induce the same kind of complexity in agent populations? And you might think, okay, this is a little far-fetched, maybe it's a little, AGI or whatever, but we've seen this, right? So this is this well-known paper from OpenAI that trained multi-agent teams to play hide and seek, and what they saw is interesting behaviors emerge even that they didn't expect. So in the bottom figures, you're seeing the agents have learned to surf on boxes, which is a consequence of the physics engine that the engineers who built it didn't even realize the agents could do. So if you're getting abilities that you didn't anticipate and didn't have to build in, perhaps that's quite exciting. Another great example, which I'm sure this community is familiar with, is asymmetric self-play. So here we have two agents competing, where Alice is trying to execute the shortest possible trajectory that Bob can't imitate or reverse. And so what that does is it makes a nice curriculum, because Alice is always trying to keep the trajectory simple if possible, but still out of Bob's range. The cool part about this is it was extended very successfully into the robotics world. So this is this asymmetric self-play for automatic goal discovery and robotic manipulation. So both of these are pretty exciting, and I'm really excited about the idea of competing agents to be able to discover and set goals for each other. I think it's also quite exciting to think about how multi-agent can aid in generalization and transfer. So obviously you guys are the real robotics expert, and I don't do that much with robots, but you're probably familiar with this example of the OpenAI hand solving the Rubik's Cube. And you'll probably know that the way they did this was they say, look, sim to real transfer is hard. We don't know exactly what the parameters of the real world are. So let's just make a simulator and randomize the parameters and create such a wide randomized distribution that we'll be able to train on the real world parameters that we'll eventually have to transfer to. And obviously this worked pretty well, but I'm going to show you that even in simple cases, this domain randomization approach can break down. So what you're seeing here is this agent is trying to walk to this green goal across a bunch of blocks. And we're using domain randomization to create a series of training environments where we randomize the position of the start state, the goal state, and the blocks. And what we can see is that when we transfer an agent trained with this procedure to this simple 4 rooms environment, we actually discovered that it hasn't learned a key skill, which is just walking around walls. Can't deal with walls, which is interesting because of course walls are very salient to us. And they could be sampled randomly. They're within the distribution of things that could be sampled with domain randomization, but evidently they're not sampled enough for the agent to learn this behavior. So it wasted a ton of time training on very similar environments to the thing you see on the left, and then isn't able to handle this use case that we care about on the right. And look, maybe you don't believe me. You guys are roboticists. Domain randomization is really powerful. Maybe you say, look, if I want to train a robot to walk upstairs, and I take my simulator and I randomize the height of the stairs, the width of the stairs, the texture, everything. And I train in simulation, and I'm able to transfer my robot to this staircase and it walks up the stairs. And you say, great, okay, I'm ready to train a household robot that can walk up the stairs in everybody's house. Well, guess what? The real world has a lot of weird staircases, right? And so could we really have anticipated that we would need to build some of these stairs into our simulator? I would argue that if like what we actually need is we want these complex training environments that can prepare us for the real world. And we want to cover these unknown challenges, but we don't want to have to anticipate them. Basically, we don't want to have to program in all the things we might encounter in the real world into the simulator ourselves by hand. Because that's just going to be really brittle. We're going to miss things. It's going to be time consuming. I don't think this is the right approach. So let's maybe take some inspiration about what other things have been going on in the multi-agent community. So this is this paper, Adversarial Policies, you've probably seen, where they were able to show that an agent trained with self-play is actually pretty brittle. So if you train an adversary to exploit that agent to just minimize its performance, it can do weird things by just falling on the ground. And this just totally breaks the policy. And if you continue to train with this in a feedback loop, you could potentially make that player agent more robust, right? So this is again tackling this idea of generalization. So what if we take this into the environment generation context? So keeping with the analogy of domain randomization, which was randomly setting environment parameters, what if we adversarially build environments or set those parameters to minimize the performance of a player agent? All right, so what can anyone see a drawback with this, a potential drawback? So here we have an adversary trying to minimize the agent's performance.
Is that for me?
Oh, is it? Do you have an answer? I thought you were putting your hand up.
Yeah, impossible to solve environment.
Impossible to solve environments, exactly. So you can see that happening in this video, right? So the adversary has built an environment where the player just can't reach the goal. So it's succeeded in its task, it's minimized the performance of the player, but the player has no learning opportunity. So again, we're just wasting computation. So what's been done in the literature to handle this problem? Let me talk for a second about RARL, or Robust Adversarial RL. So what they're doing here is they're having an adversary apply forces to different Mujoko agents that are trying to learn how to move. And these destabilizing forces, by the agent having to adjust to them, it makes the agent more robust. But the way that RARL handled this problem of the adversary, I mean, if the adversary applies too much force, it can just make the task impossible, right? And so the way RARL handled this is coming up with hand-tuned constraints that limit the amount of force the adversary can apply. And those have to be specific to each environment. So you're kind of in this realm of doing a lot of hand tuning again, which maybe we want to get away from. Another paper that I really love is called Poet. You might have seen it. And what they're doing is they're having a population of agent and adversary pairs, and the adversary is building the environment for the agent to try to learn in. And What they do is they periodically replace underperforming agents with the agent from another environment, and they're constantly evolving the agents and environments together, and they end up with this really nice emergent complexity of quite interesting environments and agents that have some impressive skills. I will point out that this paper doesn't focus on testing generalization, although I think that's something they could do with their algorithm, but they focus on this idea of like automatic curriculum through multi-agent and emergent complexity. But they still run into this issue of the adversary being able to create environments that are impossible or just too hard. And so what they did in this original paper is they manually test every agent in every environment, and they discard environments that are too hard or too easy, again, using thresholds that they have to tune. So maybe what we want is kind of a more elegant way to ensure the adversary doesn't create impossible environments. And ideally, we want environments that are tailored to the current skill level of the agent. So we want an automatic curriculum that increases in complexity with the skill of the agent. Okay, so I've been saying the way to solve all of our problems is with multi-agent. So maybe the idea is we just didn't have enough agents yet. Let's just add more agents, and that's going to solve the problem. So that's actually the idea behind this paired algorithm that I'm going to talk about from our own work. And here what we're doing is we're having an adversary generate an environment. And instead of having a single player agent play it, we're going to constrain the adversary using the performance of a second agent in the same environment. So we're going to take our player and rename it a protagonist, introduce the second agent an antagonist, and we're going to have the adversary build environments that maximize the difference in performance between them, or this regret. So now the adversary is incentivized to create environments where they're possible because at least the antagonist can do well, but they still minimize the protagonist performance. So they're still exploiting weaknesses in the protagonist. So we call this protagonist-antagonist induced regret environment design, which is a huge mouthful, but we think of it as paired because that accurately reflects how we're using this pair of agents to play every environment. So what's really cool is that Michael Dennis noticed that all of these methods I've discussed before are connected to the decision-making under uncertainty or decision-making under ignorance literature. You can think of domain randomization as actually following the principle of insufficient reason, minimax as following the maxi-min principle, pretty obvious, and paired as minimax regret. And the way we can show this is by introducing this new formalism, which we called unsupervised environment design. And so what we're doing is we're saying, instead of a normal POM-DP, we want to talk about an underspecified POM-DP, which has this additional set of parameters theta. So if you think of the U-POM-DP as the space of all possible grid worlds, then if you then specify a theta, which is the assignment of blocks to certain positions, then you obtain the POM-DP out of it. And when you think about how to define a policy, which defines a distribution over how to set that theta, then depending on how you define it, you can recover each of these previous works, which we think is quite neat. We were able to show in the paper that our protagonist should end up playing the minimax regret policy, but this depends on the assumption that the adversary and the antagonist are basically acting as a team, they're coordinating. And then it becomes a two-player zero-sum game where if the game reaches a Nash equilibrium, then the protagonist is playing the minimax regret policy. We have a proof in the paper that relaxes this assumption, so if you're interested, definitely check it out. One of the cool things about this is that we want to say that regret is going to be a good objective for robustness because it's going to train an agent that succeeds whenever it's possible to succeed. And what we mean by that is if you can partition the distribution of rewards into two distinct modes, where success is a set of rewards that don't overlap with failure, then regret will choose the succeeding policy when it can. So this is going to be, let's get this a little more interactive. So what you're seeing in this middle matrix is a set of policies and the payoffs they get for each of these different environment parameterizations, theta. Now, if I'm doing domain randomization, I'm training an agent that just wants to maximize its average performance. So can anyone tell me what policy would a domain randomization agent pick?
I think my math is right. It would be 400 divided by 5, so any of the other rows except the first one?
Yes, you are correct. Exactly. Now, since you're on a roll, can you guess what the minimax regret policy would be? Now, minimax regret is minimizing the worst case difference from the optimal policy.
The policy pi a, because that gets 75 on every task or every environment.
Beautiful. Exactly. Very nice. So domain randomization is going to maximize average case performance, so it's going to fail sometimes, and that makes it not robust. Whereas regret is going to choose policy A. It's going to succeed whenever it can. So we'll see a similar example here. If we use minimax, which is minimizing the worst case performance, that minimax policy is going to be really afraid of the policy B because it doesn't like the -1. So it's going to choose policy A. Whereas regret, again, is going to choose policy B. So you can see that regret is going to choose successful policies where it's possible. So we think it's a good objective for robustness. I also think it's a good objective for curriculum design. So what I'm going to argue to you is that regret is going to incentivize the adversary to create the easiest possible environment that the protagonist cannot yet solve. So to make that case, assume that the protagonist is getting 0 because the adversary has succeeded in minimizing its performance. So then which environment should the adversary pick? Now, in many RL environments, including the one we talk about here, there's often a reward for finishing the task faster or in fewer steps. So if you want to just maximize the antagonist reward while keeping the protagonist reward 0, then you should pick an environment that can be solved in very few steps, aka an easy environment, right? So to think about this, you can say your regret for failing at a task is going to be higher if the task is really easy. It's very intuitive, right? So this is making the adversary continue to pose tasks that, yes, the protagonist is failing, but they're the easiest possible task that it's still failing on. So you can think of this as proposing tasks in the protagonist's zone of proximal development, which is a task that it can't do yet, but it can with some scaffolding or training on that task. All right, I want to be super clear about what we actually did for the paired algorithm, because the implementation would make a slight modification to the theory. So we randomly initialize all the agents, and then until convergence, we have the adversary generate some environment parameters theta. We have the protagonist select several trajectories in that same theta, as well as the antagonist. And using those multiple trajectories, we can get this better estimate of the regret where we take the max over the antagonist performance. So that gets it a little closer to the optimal policy, which is the true regret. And then we subtract the mean of the protagonist performance. So we think this is just a bit better. It's more of a stable estimate of the regret that tends to stay positive and not jump around as much, which makes it easier for the adversary to maximize the regret. And then what you can do with the antagonist and the protagonist is just train them as normal. They're just RL agents, they're maximizing their environment reward. So that's the algorithm. I want to jump into showing you some results, but are there any questions before I show the results?
Yeah, we have one question here from London.
Thanks. I'm just curious if you ever observed the protagonist and the antagonist learning basically the same thing. Like, how do you avoid them, if they're trained as RL agents, like collapsing to the same capabilities?
We actually see that the protagonist tends to be more robust because the training algorithm is basically going to, the adversary is constantly going to be seeking environments where the antagonist does well, but the protagonist does poorly, right? So if they're performing about the same, the adversary should seek out a new environment. So the whole algorithm is only going to robustify, if you will, the protagonist, not guaranteed to make the antagonist more robust. Now we have explored population-based approaches to estimating the regret, where you can take the max of a population minus the mean of a population. And that I'm going to talk about in a little bit.
Marco, do you have any questions from your side?
I can also keep going to the beautiful plot.
Yeah, back to you, Natasha.
Okay, so these are the environments that were actually generated from the different techniques that we talked about. So in the case of domain randomization, we see that it generates unstructured environments that aren't tailored to the agent skill level. Minimax can tailor to the agent skill level, but it can trivially create impossible environments. And paired is our Goldilocks method. It can create structured environments that are challenging, but they're still possible to complete. So if we look at the results of the generated environments throughout training, that's on the left, we can measure different characteristics. I think most interesting is the passable path length there in figure C. So this is the shortest path between the start state and the goal, and it becomes 0 if it's an impossible environment. So what you see here is that paired continues to increase this metric. The environments are becoming more complicated, but the mini-max population-based training is driving it to 0. Now, if we look in figure D at what the agents actually learned, we see that the paired agents are solving more complex environments, whereas the other methods are not. And what's cool about this is nowhere was an agent trained to maximize path length, right? This is an emergent property of the system. It's kind of neat. But I think the really interesting part is what happens when we try to transfer this to a set of test environments that are increasingly challenging. So if we look at paired compared to the baselines, when the environments look more like a domain randomized environment, like the empty or the 50 blocks, the performance is pretty similar. But as the environments get more complex, only paired is able to have any hope of solving them. And so we think this is quite promising that paired could potentially increase generalization performance. So now this is all about grid worlds. I'm sure as roboticists, you're like, this is so toy, what's going on here? So I'm not promising this next is too much less toy, but I think it's interesting. When I was working at Google, there was some talk that my work should have some type of, real world product impact. And I was like, well, how are these grid worlds ever going to do that? But luckily, Sandra actually realized that paired could potentially be useful for this idea of training agents to navigate web pages. So what Google would like is you could say something like, okay, Google, go buy me a keyboard, or okay, Google, book me a flight to Los Angeles leaving on Friday. And the agent will be able to traverse these websites and put in your information and do that transaction on your behalf. But that's actually a really hard reinforcement learning problem. There's a huge action space. It's very complicated, and the websites are constantly changing. So I'll talk more about that in a second. The way the team had originally approached this was hand programming a curriculum of easy, medium, hard, and harder websites. And what you see is not only do they have to do a lot of work to do that, but the agents aren't actually succeeding on the hardest websites. And so we thought maybe paired could be used to automatically generate this curriculum. But I think the benefit goes a bit beyond that, right? Because if you're hand programming this curriculum based on the current Delta website to book flights, and we know that your algorithm is not going to generalize very well because RL algorithms have problems with that, what happens if Delta updates your website? Like, does your whole thing go down until you can retrain? How do we solve that? So maybe if you have this robustness objective, you could actually get better generalization to changes or different websites, because the internet is just so diverse. So we parameterized a paired adversary that could construct websites out of a set of components. And we saw that during training, it does generate this interesting curriculum where early in training, it generates websites with many pages, but each page has fewer components. So that makes it an easier decision problem for the agent on each page. Later in training, it shoves all the components onto one page and the agent has to solve a more complicated task. And at test time, we test the agents on a set of standardized web navigation environments. And we found pretty good results. So this is actually a population-based version of paired. And we also introduced an explicit difficulty incentive based on the number of components it added to the website. And we see that that method is actually 4 times more successful than the prior state of the art in both web navigation and environment generation. And it actually reaches more than 95% task success across the difficulty levels in the benchmark. We went a step further and we applied this to real websites that we want to use with this product team. Obviously, the performance does go down from the simulated benchmark, but we are seeing some promising results there, and we're going to continue to pursue them. All right, so in conclusion, I think of unsupervised environment design as a good way to think about improving transfer and generalization for RL agents. I think paired is an interesting way to do UED because you can use this second agent as a flexible measure of the kind of performance that could be reasonably expected from your agent as you're training. And that helps you make this curriculum of feasible yet challenging environments. We think regret is a good objective for making agents robust and for creating this curriculum. All right, so I do want to briefly touch on this other thing, but I want to take questions.
Okay, so we have one question from London.
Hey, thank you so much for this talk. Jeff Clune on Monday kind of mentioned that working towards environments are like one of the 3 pillars towards like AGI, so I'm glad that someone's working on this. I was wondering what you thought about, you kind of mentioned using like, having like a population of agents kind of like navigating these like environments as they evolve. Have you considered like auxiliary tasks, for example, to kind of help with generalization, for example, instead of having the population just kind of work towards the main objective, but by having these auxiliary tasks, you could get better generalization on the main task, for example.
Yeah, that sounds really interesting. Were you thinking of a particular type of auxiliary task? Or he already sat back down? I can't.
Not in particular, but just from the papers that I remember that do auxiliary tasks, this could help, like with the example that you gave, with the websites kind of always changing. If the agents are solving auxiliary tasks, like for example, being able to navigate to a button as the button changes around. I'm just kind of throwing these out there, but like as the button changes around in like the XY coordinate space of the web page, having these like smaller auxiliary tasks for the population of agents to learn would maybe then better generalize to like, you know, these dynamic websites.
That makes sense. Yeah, that makes sense. I will say, and I actually am working on a follow-up to this that is in the language space, and we are thinking about auxiliary tasks in that space. So definitely a cool idea, and maybe it makes your population more diverse, and there's interesting benefits there. I will say one thing we hope to get out of paired is that, let's say in order to learn to navigate a complicated website, you must first navigate to the button. We would expect, and we actually do see, that the adversary would increasingly decrease the complexity of the task until it does the minimum task that some agent starts solving. And so maybe the adversary would automatically learn to start with like moving the button around. That would be the dream, right? So.
Marco, do you have any quick questions? One quick question from the virtual side?
No question yet.
Okay, I think we better hand back to Natasha for the final part of the tutorial.
I only have a couple more minutes, so there'll still be time. But I just want to briefly touch on this idea of using this type of social learning in human AI interaction, which really fascinates me. So I think it's easy to make the case that you want to learn from human signals. So this is a real conversation of someone talking to their, I can't, Alexa, because my thing was talking to me, but they're talking to their device and they say, what's the right way to Walmart? And it responds, the right way to spell Walmart is W-A-L, blah, blah, blah. So this is obviously the wrong answer. I would bet you anything that the user's response contains some hint that they're frustrated, like whether it's their tone of voice, the words they chose, or their facial expression. There's some cue there that we could potentially learn from. And I think learning from this type of implicit cue is going to work better than relying on people to manually train their algorithms. So I don't know how many people has ever bothered to train a Google algorithm by giving it feedback about whether it provided the right result. But typically, people don't tend to do this. But I wonder how many of you might have used a frustrated tone with one of your devices, right? So this type of social feedback is rich, ubiquitous, natural. You're getting it for free. Why not try to learn from it? So that's something I've explored in a few different papers. This is a paper on using offline RL to improve dialogue systems, where what we did was we built a web interface where we deployed a bunch of pre-trained dialogue models to talk to people. And we tried to collect implicit signals like their sentiment. So when the conversation was going badly, you can see the user says, that didn't make sense. We can detect that that's a negative signal and train the model to try to reduce that type of feedback. Similarly, when the conversation is going well, that can be a positive signal. So this was pretty interesting. We've done some follow-ups and we were able to learn offline with the scale control method to be able to increase eliciting positive sentiment from humans. Another paper that's kind of fun was improving the output of SketchRNN by showing people samples from the model and recording their facial expression response. So actually with only 67 or 69 examples of doing this procedure, we can see that the model significantly improves the way it draws cats in the top right there and rhinoceroses. So the rhinoceroses were pretty abstract, but after only a very small amount of feedback from humans, you can improve their ability to draw credible rhinoceroses. So I think this is an exciting direction, and I'd like to explore that more as future work. So I'll end there, and I'll just re-emphasize why I think social learning or multi-agent systems, multi-agent approaches could be really beneficial. I think it helps you learn and complex behavior, generalize better, coordinate, and ultimately interact better with humans. All right, so I promise I'm done showing slides now, so please ask me any questions.
Wonderful. Thanks so much, Natasha. And thanks for bringing the audience in with those interesting questions. That was fun. So we have a question here, Jackie.
I have two questions, but since we're short on time, maybe I'll limit it. In the going back to the first part with the results about independent PPO, which is super interesting. Do you think so? Like the Google football environment, I'm not that familiar with it, but it doesn't seem like it's like a mixed motive game, like the tragedy of the commons environment, where seemingly the motives of the RL agents kind of conflict. Like they're self-interested, but if they coordinate, then they get higher reward eventually. So do you think that result would still hold in a tragedy of the commons?
I actually have tried independent PPO in a number of different environments, and I'm pretty bought in. It tends to work really, really well. I would point out the soccer environment is interesting. Where am I trying to go? So this paper, what they actually showed is that what happens in soccer is the agents don't discover diverse enough policies to do interesting strategies. So what they did is explicitly incentivize each agent to learn a different policy than the other agent with a divergence objective. So this is the celebrating diversity paper. They get really good results. But I think independent PPO, because it's fully decentralized, also enables this. Agents can learn independent policies, so in that sense, be diverse. But what's interesting is I think the diversity objective at some point may work against the game objective. Like once you've got this diverse mode, maybe you then want to optimize, whereas PPO is free to fully optimize the game reward once it's discovered different policies. So that's kind of why potentially it could be quite good in this environment, but I actually think independent PPO is quite solid. The other thing, I don't know if you saw this paper from a few years ago, which was showing that PPO is just much more stable and easy to train than other algorithms, like even than SAC. So it just works across a broader set of hyperparameter settings and tends to be really reliable. So that might be why it's still a good choice if you're just getting started in multi-agent, because it's easy to get working.
Thank you. Marco, do you have any questions on your side? Just
yes,
time for one.
Yes, there is a question. So for the rhinoceros case, how did you measure if the face expression is a positive or negative signal for the drawing agent?
That's a great question. Actually, we used we distilled their facial expressions into things like smiling and frowning and stuff like that, and we assumed that we want to maximize smiling and I don't know, smirking or something, I forget what exactly were, and minimize frowning and concentration. So it turns out concentration often looks like the person is just unimpressed with this thing. The way we actually established this, though, I should say, is we did extensive UX studies. So we actually worked with the whole UX team. We did user studies in the beginning to have people interact with SketchRNN, looked at what the detector was detecting and correlated that with their ratings of the sketches. So we didn't just make this up. We actually did the groundwork to establish what is the relationship between people's actual perception and their face. So.
Great, thank you.
All right, and we'll finish with one final question from London.
Thanks a lot for this really interesting talk. So with paired, one of the things that just thinking about how we take it further and be able to use it in robotics, I guess, is how would you be able to scale up kind of the way the environmental encoding is? So with your maze, I guess, sort of automatically generating it, but as we want to move into perhaps more complex and more realistic 3D environments, how do you think you'd be able to encode the environment, kind of lets paired use and explore the environment in a way that we kind of can see and as meaningful as we train the agent?
That's a great question. And I think there's a lot of complexity there. You might be just passing the buck of all the hand coding I was complaining about into the parameterizing of the adversary. But I actually think anytime you could be applying domain randomization, you've already got a set of environment parameters that you're randomizing where you could apply paired, right? The other thing, and you could tell me if this is a crazy or a bad idea that I was thinking about, is what if you could parameterize, if you're interested in like object manipulation, what if you could parameterize an environment so that you could build new objects? And then you can get a manipulation policy that's robust to many types of objects. So like maybe you can stick different components of objects together and get something new for the agent to manipulate. But I don't know if that's a bad idea.
No, I don't know a lot about sort of the object manipulation side of things, but I think it makes a lot of sense to have your environment be parameterized and something that maybe the designer already knows is a useful thing to get behaviors out of, right? Because it's maybe a way to put information we already know about how we want the behaviors to behave beforehand, perhaps.
Yeah, that makes sense. That's a great point.
Cool, thanks a lot.
All right, so it's 5 o'clock here in London, so we'll have to end there. And Natasha, thanks so much for joining us and for your wonderful tutorial.
Thank you.
Thank you very much.
So we'll now go into the final poster and demo session, and then at 6 o'clock, we'll have the award ceremony back in here.
Me to see you too. I wish that I could say it to your face. Thought she could love like you. Trust another thing you used to say. Take care now, it sounded so unusual. Last few words I'm holding on to you. Though no one else can ever find a love like this. Love like this. Drink rosé right off the bottle. If we don't wake up tomorrow, could we just talk? What would you say about us? Tell me not to meet your father, cause he'll talk and we'll get ugly. Could we just stop? Could we just take a breath? And you got me under your love, and you right there. Drink rosé right out the bottle. If we don't wake up tomorrow, could we just talk? What would you say about us? What would you say about us? I remember that night when I last saw you. It was a night of, you were crying in all the photos. Life hadn't turned out like we thought it would, and you were sick of the choices you made. I was hoping that you might change your mind, that time away would bring us back to life. But now we're living in a different shadow, trying to make it back home. I don't know how to breathe when I'm not with you. Why did you leave without warning? From the second you were gone, I was just old news. Like we were nothing, just an excuse. I was hoping that you might change your mind. The time away would paint it in a better light. But now we're living under different shadows, missing every phone call. But I still feel it. Your heart close to mine. I still need this. Your hands wrapped in mine. I still miss you. I think of you all the time. I search for this day and night. But a love like yours is hard to find.
I could wait 1,000 days. You never wait for me. You never wait for me. Even when I ran away, you're all that I could see. You're all that I could see when I could hardly walk on my own. I had to lift myself out of the trench below. Haven't I suffered enough to let you go? Let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. I could wait 1,000 days. You never wait for me. You never wait for me. Even when I ran away, you're all that I could see. You're all that I could see when I could hardly walk on my own. I had to lift myself out of the trench below. Haven't I suffered enough to let you go? Let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now. Let you go, let you go, let you go now.
make me a lie. If I say goodbye, then make me a lie. If I say goodbye, then make me a lie. Make me a lie. My heart's heating up. This love is on fire. Love is on fire. On fire. On fire. Every day I'm drifting, cast away like a ship in the sea. 'Cause I don't know where to go, feeling low, and I do think about it. Every day, things are shifting, feeling lost with no answer inside. 'Cause I still cannot see how my life's gonna be, so I hide away. But when the storm begins to fade, I see my path, I am not afraid. And in the break of day, the light that shakes my shadows away. Perhaps the sky is clear someday. Every day I set direction, no longer worried I won't find my way. 'Cause now I know where to go, it was long ago since the darkest days. 'Cause when the storm begins to fade, I see my path, I am not afraid. And in the break of day, the light that shakes my shadows away. Perhaps the sky is clear someday. Sometimes it feels like I'm just walking on an endless road, like I got somewhere to go. Sometimes I'm feeling scared, but I don't wanna walk alone. You're the hand I wanna hold, 'cause you are everything to me, babe. I don't wanna see you hurt. You should know your worth. You are everything I need, babe. I don't wanna see you frown. I wanna let you down, 'cause Walking on an endless road, like I got somewhere to go. Sometimes I'm feeling scared, but I don't wanna walk alone. You're the hand I wanna hold, 'cause you are everything to me, babe. I don't wanna see you hurt. You should know your worth. You are everything I need, babe. I don't wanna see you frown. I wanna let you down, 'cause it's only you. No one compares to you, no. I'll keep fighting and I'll never let you go. Whoa. It's only you. No one compares to you, no. Let me love you and I'll never let you go. Whoa.
Drew with the finest of colors. We were like crayons, never meant to last. Our colorful clothing all washed out. Hope we could find our way out of the monochrome painting on the wall. The colorful clothing all washed out. We live in gray, dreaming of the colors fading away. Can you see, we're washed out. Washed out. We're washed out. We need to turn our pages, sharpen our pencils and start again. The colorful feelings are washed out. Where should we keep our stories? Stories of moments we can't forget. The colorful feelings are washed out.